Perfect. All right. So let's begin this beautiful morning out here. And as I begin, I would like to start with a beautiful quote that actually stands true for the event that we are actually organizing today. So, as I start, I just want all of you to pay attention. Discovery consists not just in seeking new lands, but in seeking it with a new vision. And this vision stands true here because today we are going to talk about so much. There will be so many valuable insights. There will be so much fun. There's so much planned for all you guys, and I don't want to, feed you with all the information right now. I would request all of you to stay throughout this event and witness this for yourself. The room is set, the schedule is set, and I think so are we. So namaste, ciao, ni hao, shalom, bonjour, hello, and a very, very good morning, and welcome to the much awaited IEEE Data and Storage Symposium 2021. This symposium is organized by IEEE Bangalore Section in association with IEEE Computer Society Bangalore Chapter, an industry flagship event connecting technology leaders across various segments of data management and storage world. So before I begin, let me introduce myself. This is Mini Divan, your host, taking charge for the day to make sure that you all have a super day ahead. But before we begin, I want all of you to welcome yourself and one another with a huge round of applause. Now, I understand that today we are virtual and you all must be wondering then how is it even possible? So when our spirits are so high, I think every little thing is possible. All you need to do is open your chat box or this way exactly, or you can use this emoji. I want everyone to do it in sync so that we can feel some energy, some turbulence here in the room as we begin this beautiful morning. I can see some people already doing it. I would also request the other people to do it. It will be great if all of us can do it. Yes, perfect. Super. Now I can feel some turbulence here in the energy. So this is the house rule for today. I know that I cannot see you, I cannot communicate with you, but this is how we are going to communicate. Thanks to technology, thanks to science. Whenever I ask you to talk to me, or whenever I ask you to raise your hand, or whenever I ask you to clap and motivate the speakers who will be coming from across the world today, this is how you're going to do this so that both of us can connect with each other. So please don't make me feel alone. Please be part of the family. Please be together and please stick around throughout the day because there's so much that I'm sure will excite you. Moving ahead, let me brief you a little about this event. Um, all right, so this is an industry flagship event connecting technology leaders, as I've mentioned, across the world. And what makes it even more glorious is today we have all the respected dignitaries, all the organizational members, all the leaders, innovators, entrepreneurs together as one big family today in this room from across different time zones, across the world. Once again, the beauty of science, that even in a situation which is so rough, which is so tough out there, we are in a middle of pandemic. And yet, we all can come together to be a part of this day filled with lots of fun, lots of value addition, and as we have top-notch speakers, industry experts who will address the impactful problems by turning ideas into solutions and will share their vision on future technologies and how they will impact our way of living in future. I'm sure this is something which excites me, and I hope that you are looking forward to it as well. So expect nothing but the absolute best today. So now that I've already felt some energy, I think I've talked a lot, I think I've briefed you a little, and I really, really hope that you're looking forward towards all the amazing sessions that we have planned for you guys. But to begin with, now, without much further ado, it gives me immense pleasure to invite our first speaker here. So please put your hands together for someone who's the part and parcel of the IEEE family. Someone who's here, who has been here with all of us throughout, right from the very beginning. So please welcome none other than Mr. Bindu Madhava, the Chair IEEE Bangalore Section, to present the welcome address. Welcome, sir. Are you here with us?
Yeah.
Pleasure to have you, sir. Over to you.
So good morning, everybody. Good morning, good afternoon, good evening because of the time zones. So the greetings for all of you from IEEE Global and particularly with IEEE Bangalore Section. I being the chair of Bangalore Section, I'm extremely happy to have this industry event, a symposium, which is very apt and relevant in the current context. So I'll come to the topic later. First of all, I just wanted to tell that IEEE Bangalore section is one of the most vibrant sections in the world. So the engagement, what you are having is one of the most vibrant sections in the world. And we conduct a lot of symposiums which are of interest and current and relevant for the days this one. I'm extremely happy that our team is able to bring up this particular symposium in a very short span and which has got really good speakers who are who is who in this particular domain. So first of all, I would like to congratulate the team which has put up this particular symposium today. So this doesn't stop with this particular symposium. We are trying to sort of have a series of symposium on this particular topic, which is of very relevant. And then subsequently, we would like to also culminate into a international conference where we'll threadbare discuss on the research innovations which are happening in this particular area. So this is just a recap of what I just wanted to sort of what we have got in stores in this particular area of very much important. So coming to the topic itself, I think basically if you see worldwide, people have been talking the cost which is involved in the data will be equivalent to the oil cost, or it is called data economy. So much of importance has been given to the data because there is a lot of data available. But if the data is not sort of made into a meaningful information for decision making, then it doesn't have any sense. So that is why there is a lot of tools and technologies which are required for data, for storage, and then subsequently for the data analysis and coming out with some meaningful information. So the technologies, whatever has been sort of current, will be used for development of the tools. The main thing will be the architecture and the domain at which the data will be archived and presented to the or rendered into different form factors. So with this particular thing, the data storage and the data management and then subsequently the data analysis on that particular thing becomes very important. So newer architectures, newer tools, which ultimately sort of culminate into giving high performance output. So I think the domains which are of challenging and which is require such things are in the space of energy, especially where the smart grids of the innovations happening in the smart grids becomes a killer application for this particular whatever the data management and data analysis which has to be done. Because starting from a small form factor of an application with an app to a larger as a high performance computing where you have to do some sort of a faster than real time simulations. So with that particular application being on the top, of course, there are a lot of life science applications, healthcare, and weather, and the allied this ones. So when it becomes a coupled models which has to be solved, and the response times windows which are very narrow, then the tools which goes into this data management and storage and the architectures becomes very apt. So with this particular background, I think there are stalwarts who are experienced in this particular domain uh, who will be talking. I only request all the participants to take the best out of this, whatever the symposium we have arranged. And please do have an interactive session and then subsequently make full use of this particular thing, which is sort of arranged for you. Thank you. And I would like to welcome the first speaker. It is my privilege to welcome Mr. Isaac, Chief Executive Officer of Huawei India. In his 2 decades of association with Huawei, he has been instrumental in engineering and leading a series of products in IT domain, especially storage systems. So he is an expert in storage systems. So basically, we should make best use of his knowledge in the community, what we are trying to sort of conduct this particular event. Under his leadership, Huawei storage products have attained great commercial success. And Mr. Isaac strongly believes in promoting the culture of innovation. Yeah, I think I agree with Isaac's background. Innovation has to be there. Otherwise, the whole thing comes to standstill. And to solve most important challenges of the technology world. So, and basically the applications, what is being thought of is really the challenging applications which require such technologies. So I would like to welcome Mr. Isaac to this particular forum and deliver his opening address. Thank you.
Thanks. Okay, so good morning. Good morning, distinguished speakers, participants, friends, and colleagues. So it's my pleasure to welcome you all to the second edition of our IEEE Data and Storage Symposium 2021. So today, my job is to warm you up for the upcoming sessions and set the tone of this symposium. For all of us, actually, these are very pretty, challenging times indeed. Modern high performance applications in areas like health and life science, energy and weather are getting ever demanding, and the storage technology need to be future ready. So the theme of this edition of Symposia is getting high performance storage ready for the demanding high performance applications. Today we have 3 main sessions. First, we have invited talks for distinguished speakers talking about emerging technology challenges and researches for high performance computing. So the second is roundtable and panel discussion for thoughtful exchange of ideas on HPC, HPDA, research challenges to storage and whether computational storage and near data processing offer a way forward. Third, the last short talks or lightning talk, as we talk, from young researchers, some professors from the university, and their recent past work. So no event is successful without an engaged audience. So I'm very sure all the participants here will pay their full attention to the sessions. And I hope the organizers will keep the session lively and interactive as much as possible. So I thank and welcome each all of you to join today virtually in the IEEE Data and Storage Symposium 2021. Wish you a great learning experience. Without any further delay, let me take the opportunity to welcome our next and distinguished speaker, Tom, to deliver the keynote. So good night. Over to you, Tom. Tom, you're not audible.
Oh, I'm sorry. Can you hear me now?
Yeah.
Okay. Thank you very much, and it's a pleasure to be able to join you folks virtually in Bangalore. I'm here in Silicon Valley. Let's see if I can get the share working. let's see. Can you see the presentation mode? Can you see my presentation?
Yes, we can see.
Good.
Okay, great. Okay, thank you, folks. So I'm going to talk to you today about digital storage and memory with a lot of look at applications that involve artificial intelligence from the edge to the data center. And there we go. And here's an outline of my talk. I'm going to first of all talk about what's driving the use of emerging memory technologies, especially these non-volatile memory technologies, and how that's tied into changes in the whole way that we do computing. We'll talk a bit about some of these memory technologies, these emerging memories. We'll talk about who's using them, how they're being made in fabs and that sort of thing, and then we'll look at some real-life applications. Finally, an outlook on where things seem to be going for the future and a summary and some references at the end. So first of all, let's talk about why we need emerging memories. Something very interesting is happening in the memory market. Although there have always been numerous alternatives to today's leading memory technologies, waiting outside, essentially trying to get into the market, they have never had the opportunity that has recently developed. Until now, these memories, 4 of which we're going to examine in some depth today, have been waiting at the door, if you will, while the market's dominant technologies, DRAM, NAND flash, SRAM, and NOR flash, have kept them out through their lower prices because of their higher manufacturing volumes. Now let's look at why things are changing and why the market has changed in a way that will provide opportunities for new technologies to replace their entrenched competition. So first of all, there's a lot of data being generated. Projections of data generation, IDC, for instance, talks about 175 zettabytes of data generated annually by 2025, which they say is up from about 59 zettabytes generated in 2020. Now, a lot of this is being, data would be generated by sensors, cameras, various sorts of things on IoT devices and infrastructure, etc. Or for instance, in automobiles, for example, that has the most value when processed real time, so you can make real time decisions. And that will increase the need to store and process data in a device, or at least close to the device in the network edge. And probably only a few % of all this data that's being generated will ultimately end up being stored for long term. So there's greater use of AI in devices. In fact, it's being used for all manner of things, even being used now for managing storage itself. It'll be used at the network edge and at data centers, and that's increasing memory requirements to do this capabilities. In addition to the growth of data being processed, power consumption as well as latency and data rates are important characteristics in future system design. In particular, if you're in places where you're running out of battery or some other energy constrained situation. So this leads us to look at the memory technologies that are going to enable us to handle this data tsunami that's coming down on us. So the semiconductor industry is being forced to change which memory technologies are used in embedded applications like MCUs, ASICs, and other system on chips. And that's because flash memory, the NOR flash in particular, can't scale to keep pace with CMOS logic process advances. Scaling was also a problem with NAND flash. Planar NAND flash stopped scaling at about 15 nanometers. So the industry adopted a 3D structure in order to continue to provide Moore's law type cost reductions. System on chips used NOR flash, and NOR flash stopped scaling at about 28 nanometers with the adoption of the FinFET. Some sort of new memory technology is needed to support these chips' code storage requirements, and that is suddenly providing an opportunity for some technology to replace NOR flash for all processes below 28 nanometers. But it's not just NOR flash that's heading for replacement. SoCs use SRAM to store temporary data, and this SRAM is poised to stop scaling, or at least slow dramatically, around 14 nanometers. Now, there will be side benefits of this change. Alternative memories not only scale past the limits of these established technologies, making them cheaper to produce ultimately, but they are also persistent and have more balanced read and write speeds, particularly compared to flash. And this will impact the way that systems and software are configured. So we're going to discuss these changes during this presentation. First of all, let's just look at some of these scaling problems. That's a chart we can use to illustrate this issue of scaling. It shows 2 lines that represent NOR flash and some new emerging memory technology. So process shrinks have been been able to reduce costs for the entire history of the semiconductor market. The process nodes run along the bottom, shrinking as you move from left to right. And the relative cost on the vertical axis is always declined in proportion to each process shrink. But flash memory has a problem after the 28 nanometer node. NOR flash, which is that non-volatile memory that the industry has been used to store code in microcontrollers, ASICs, and other SoCs, stops scaling at 28 nanometers. And that causes its cost decline to cease, as this red line shows, by abruptly going horizontal at a roughly 28 nanometers. Now, manufacturers are addressing that issue by migrating to new memory technologies, which continue to scale and allow further cost reductions as a consequence. Those memory technologies are represented by this black line on the chart. Although today they are more costly than NOR flash, their cost will eventually fall below that of flash because of the flash isn't scaling anymore. And after 28 nanometers, you start to see the new technologies actually become more cost effective than the older technology. SRAM has a similar problem. Its scaling slows or seems to stop around 14 nanometers. So this is a similar chart, but it plots a cell area for SRAM designs presented at an IEEE conference over the past few years. The cell area, which is proportional to the cost, is measured on the vertical axis, and the process geometry again runs along the horizontal axis. The cell area has been shrinking to keep pace with the process, but it abruptly stops shrinking at about 14 nanometers, according to this research. In addition, SRAM is much larger than all of these persistent memory candidates. Now, this leveling off makes SRAM a reasonable candidate to be replaced by some alternative memory technology. The emerging memory will increase the wafer cost over that of a standard CMOS wafer, but the die size for some chips will be smaller, thanks to the fact that the emerging memory technology will consume a smaller area than the SRAM. So that reduces the cost of these chips, making the design based on the emerging memory more economical than its SRAM-based counterpart. That's going to drive future chips to migrate to an emerging memory as an alternative to SRAM. And finally, DRAM is working memory, of course, used in all electronic devices from consumer to industry and enterprise applications. Like many semiconductor technologies, it has become more difficult to continue the pace of lithographic shrinking and increasing transistor density than it was in past decades. And this figure shows the slowing of DRAM scaling since about 2008. Although there are variations in supply and demand, you can see here there's like many semiconductor memory technology, there's boom and bust cycles in terms of the price. The DRAM price scaling basically was declining at an average of roughly 37% annually for 37 years. And then it slowed more recently since about 2008 to about 8% annual reduction. Now, to show what the scaling thing means to chip sizes and costs, I'm going to present you an animated graphic. So this is a photograph of a Intel processor chip made on a 45 nanometer process. You can see two very different parts of the layout. The less regular part of the chip at the top is the logic, and the lower half has very regular patterns. That's the SRAM used for the on-chip caches. In the past, the entire chip would scale with process shrinks, as is illustrated here. As the process moves from node to node, from 45 nanometer to 32, 22, and finally 14 nanometer, the die area and cost would be half that of the prior generation. It follows a very nice scaling law. This assumes that the SRAM keeps pace with the process technology, though, and the prior slide, of course, shows this doesn't happen after that 14 nanometer node. So we'll use the same chip again. Again, keeping in mind that the top half is logic, which will scale in proportion to the process, and the bottom half is SRAM, which will scale less aggressively. You can see in this series that the top half of the chip gets pretty small towards the end and only accounts for about 20% of the total die area at the smallest process node. Yet the SRAM doesn't scale, resulting in a pretty large chip. In fact, the die size trend starts to level off at the end. This black line only indicates the height. The area of the chip, of course, will be roughly equivalent to the square of this figure, and that indicates a very significant difference between these two trends. The SRAM is causing the chip to be larger and thus more expensive. If mature emerging memory were readily available, then that SRAM would already have been replaced and we wouldn't be calling it out as a concern for future chips. So let's talk, we talked about the scaling issues and why, and the growth in demand. Let's talk about changes in the computing model. So today there's a lot of excitement about using emerging memory in standard computing systems. Not only is an emerging memory attractive as a new layer in the memory storage hierarchy, but it also provides a path to interesting architectural innovations. In particular, innovations that solve data motion issues, such as since an von Neumann computer, as we show on the left-hand side here, there's lots of energy and time wasted moving data around from one place to another. These energy and time issues can be addressed by moving from a von Neumann architecture to a memory-centric approach, as illustrated on the right. This approach has led to new protocols like OpenCAPI, CXL, C6, and Gen Z. These approaches support memory disaggregation by removing some memory from behind the processor, memory pooling and sharing to more efficiently use storage and memory to address new problem classes, and heterogeneous computing, which allows data to be processed by a variety of different types of accelerators located close to the memory. Note that the memory-centric system includes a DRAM connected directly to the CPU, near memory, and far memory at the center of the diagram, which is labeled SCM, or storage class memory. Since the far memory is shared, its data path to the CPU must be arbitrated, and this adds some latency, thus the term near and far. The near has low latency, the far has somewhat higher latency. The industry is slowly converging on a preferred mix of these solutions to solve today and tomorrow's problems. So let's take a look at one of these in particular, the CXL. It's being backed by a big consortium. Will be a switch memory channel that enables pooling in its heterogeneous memory and computing resources. There's actually the first storage devices with CXL, or the first memory devices with CXL interface has already been announced, and the CXL folks in the CXL consortium are talking about the first products, actually system level products, being available in 2022 next year. You'll continue to have DDR channels to be used for low latency memory, at least through DDR5. And what happens beyond DDR5, as the data rates get very high, how well can we move to DDR6 or even beyond that at some point? So in Gen Z is another. So the relationships kind of developed in this consortium is in the box you'll be doing CXL type fabric for the memory, and between boxes Gen Z, and so then there's different types of, for memory, the industry appears to be moving towards a mix divided by whether that memory again is near or far memory. CXL is gaining popularity for pooling heterogeneous memory or memory with mixed latencies and data rates, for instance, Optane and DRAM, and the memory on accelerator cards within a box. Gen Z is likely to be using it to connect storage boxes and racks together. And near memory has three candidates in the running. One is this DDR channel, which is a conventional approach, which should continue to be used for near memory systems, at least through DDR5, and also the LPDDR in mobile devices. High bandwidth memory, which provides more bandwidth than DDR, but it's less flexible and it's much more costly. And then there's another one called OMI, which is the OpenCAPI memory interface, currently used by IBM to power processors and certain FPGAs. Let's have a quick closer look at these near memory interfaces and compare them to each other. So this chart illustrates the operating spaces of those near memory interfaces just mentioned, DDR4 here, as well as 5, high bandwidth memory, HBM, and also OMI. DDR provides a satisfactory solution for near memory in PCs and smartphones, but then it falls short if you're doing for high-end server and accelerator cards. So many accelerator cards use high bandwidth memory, especially if they can operate in the limited memory space afforded by HBM, because HBM high bandwidth memories are stacks of DRAM chips that present about 1,000 to 2,000 parallel signal paths to the processor. This can improve performance, but the processor and the high bandwidth memory must be intimately connected. And it's used in applications that accept high bandwidth memory at significantly higher price in return for its blazing speed, for instance, in mini GPU type devices. Although HBM is a help, it's considerably more expensive than standard DDR DRAM, and it's available in stacks of no more than 12 chips, which limits its use to low capacity memory arrays. This open memory interface, or OMI, uses existing high-speed serial signaling PHYs with a custom protocol to connect the processor to its DIMMs. So these DDIMMs, or differential DIMMs, are made up of standard low-cost DDR DRAMs and an OMI transceiver chip that can provide near HBM bandwidth at a DDR-like capacity and price. So that's what we're trying to show in this chart here. So let's look at some of these emerging memories now. So there are many emerging memory types, and they're vying to replace NOR flash, and as you saw before, SRAM and possibly DRAM. They all share some similar attributes. They all have a small single element bit cell that promises to scale smaller than current technologies in order to support small, inexpensive die and 3D stacking. They also promise to be easier to use than flash memory by supporting write-in-place with no need for a block erase, and they have therefore more symmetrical read and write speeds. And finally, they're all non-volatile. They're all persistent. When the power goes off, the data doesn't disappear, and they can all be used as persistent memory. So the new memories are necessary for us to continue something like a Moore's law type scaling. And the memories we're talking about here primarily are ferroelectric RAM, magnetic random access memory, resistive random access memory, and phase change memory. An example of that was Intel, and until recently, Micron's 3D crosspoint, Intel's Optane memory. So MRAM technologies are already shipping. Many of these technologies are shipping. They're in low volumes today. Over the history of the technology of MRAM, they shipped over 120 million standalone MRAM chips, mostly small buffers and caches. The company has a partnership with Global Foundries, who's building 300 millimeter wafers for Everspin and offers MRAM to other customers for embedded memory applications and system on chips. So we've listed some high profile applications for Everspin's MRAMs here. Another company, Renesas, is shipping an MRAM chip that it inherited through its acquisition of IDT. Other foundries now offer an MRAM option to their SoC clients. They include Global Foundries, TSMC, and Samsung, and probably all the other foundries eventually as well. Now, phase change memory, or PCM, is another technology that is shipping in volume. The most widely known rendition of this is Intel's Optane 3D crosspoint memory, which it ships in SSDs as well as in DIMM modules. This builds on technology that Intel has in development for over 50 years. Their first Optane SSDs shipped in 2017, and the first DIMMs shipped at the end of the following year. Both are currently used in storage systems and other computing applications. Intel's been using Micron Technology as its manufacturing partner for this technology, but recently Micron decided to exit this business and is going to sell the plant that's using to make the 3D crosspoint. Intel, Micron, and Samsung all tried to sell PCM chips into the standalone NOR flash market over a decade ago, but that market never developed. ST Microelectronics currently produces phase change memory-based microcontrollers for use in automotive applications. Resistive RAM, our third technology, is also in production, but in a quiet way. It has been shipping by Adesto, now a part of Dialog Semiconductor, since 2013. Dialog plans to license its CB-RAM, its version of this resistive RAM technology, to Global Foundries to be offered as an embedded non-volatile memory option in its 22FDX platform and in future platforms. ARM announced the spin-out of Surfy Labs to develop and license new types of non-volatile memories based upon correlated electron materials, or CERAM, in a joint development project with Symmetrics Corporation. Other companies currently ship resistive RAM into both commercial and military and aerospace applications, and leading foundries are supporting resistive RAM as another alternative to embedded NOR flash, in addition to MRAM. Finally, we come to the oldest emerging memory technology, ferroelectric memory, or FRAM. Surprisingly enough, this technology predates the development of the integrated circuit. The photo on this slide was published by Bell Labs in Scientific American in 1955, and it shows a single SBT crystal with vertical and horizontal metal traces that could be used as a non-volatile memory. From the perspective of unit shipments, FRAM has also shipped more than all other emerging memory technologies combined, having found its way into over 4 billion chips. It's most commonly used in RFID cards, thanks to its extraordinarily low write energy requirements. Until recently, FRAMs were based on unfriendly materials like lead and bismuth that most fab managers resisted putting into their factories. But in 2011, NAMLab in Dresden, Germany, found that a crystalline form of hafnium oxide has strong ferroelectric properties. This has created new life for ferroelectric memory. Hafnium oxide is commonly used as a high K dielectric in leading-edge CMOS processes. Fab managers understand how to make it in high volume. Besides its use in ferroelectric memory, this form of hafnium oxide is being investigated for making longer retention DRAMs. Researchers have used it to produce a 3D DRAM, similar process, and also used it to produce a 3D DRAM, similar in process to standard 3D NAND flash. So interesting things around that ferroelectric memory. Let's talk about what's out there. Who's making these non-volatile memories today? So the leading foundries, those with processors finer than 28 nanometers, now offer emerging memory technologies to their customers. They include TSMC, Samsung, GlobalFoundries, and UMC. These companies offer spin tunnel torque MRAM today, and many of them are looking at offering spin orbit torque MRAM and other MRAM technologies. There's lower energy or lower right energy MRAM technologies that are faster out there as well. Although today's products aim to replace embedded NOR flash, newer technologies could compete against SRAM and possibly DRAM. Now, the other companies are offering resistive RAM and FRAM today, including in these foundries. Now, MRAM is interesting because it saves power while reducing the chip size and cost. So here we're comparing MRAM with eFlash, that's the NOR flash, and SRAM. Embedded MRAM will shrink smaller than SRAM and flash. So 1T, 2T MRAM bit cell is smaller than a standard 6-transistor SRAM bit cell. In NOR flash, again, hits a scaling limit after 28 nanometers, so it helps in terms of the size of things. MRAM can replace embedded SRAM and NOR since it offers lower power, lower cost, and higher density. Now, the type of MRAM that is used can be tuned for the application, optimized for data retention, endurance, and capacity. In fact, I've seen some cases where people have made MRAM that has maybe a second of endurance, that they're using it to replace a cache in a camera, a buffer rather, a cache in a camera, you know, that had been SRAM. It has longer endurance than SRAM, but not very high endurance, and they're using that to trading it off with the data rate. GlobalFoundries has shared its roadmap for eMRAM and eResistive RAM in a system on chips. With its 22 nanometer node, it's offering its flash ERAM, ERAM-F, as a replacement for embedded flash. This ERAM offers higher memory density at sub-nanometer processors and higher endurance than NOR flash, and it's targeted at code storage and SoCs for automotives, industrial grade MCUs, and Internet of Things applications. The technology provides a 100,000 cycle endurance and a 10-year data retention from -40 degrees to 125 degrees C. ERAM and eResistive RAM are offered as low density configuration memory starting at this 22 nanometer node. At its 14 nanometer node, GlobalFoundries is developing an SRAM type MRAM to replace SRAM and SoCs. That's scheduled to be available sometimes towards the end of this year or maybe into next year. Even faster MRAM scheduled for later on. Other major foundries such as TSMC have similar plans for product introductions. High endurance non-volatile memories will allow less data movement, support higher performance, and provide more memory on a fixed chip size, all of which are important for AI inference applications. It also enables more power off states for power constrained applications. And that leads us to looking at some of these real life examples using these emerging memory technologies. So this is a block diagram of Ambic's 4th generation Apollo system on chip, which is being used for consumer applications. It serves as both an application processor and a coprocessor, ultra-low power battery operated IoT endpoint devices. If you look at the lower left corner, you will see the system memory subsystem, which is made of MRAM and SRAM. And so that shows you what that looked like. The chip pairs a 2 megabyte MRAM with a 1 megabyte SRAM, and therefore provides more memory. So another device that is shipping with embedded MRAM is made using memory technology by Newman, which is an MRAM IP house. This chip is used by NASA, the particular one we're showing here, for distributed computing in space. MRAM is naturally less sensitive to radiation than flash or DRAM. Its high endurance and non-volatility both help to reduce the energy requirements. So each of these deep neural network accelerator chips has from 1 to 32 processing engines, 32 to 1024 ALUs, in order to perform efficient processing for matrix multiplication, convolution, etc. Again, for things in space that have to make their own decisions on what they're going to be doing because the latency of communicating back to Earth can be very long. MRAM is also being used in Sony's GPS receiver, which can be found in Huawei's GT2 smartwatch. Built on Samsung's 28 nanometer FD-SOI process, this IoT endpoint includes 8 megabits of embedded MRAM. So there's a lot of other emerging memory devices that ship in volume in production today. Also includes an MRAM microcontroller from NXP, a phase change memory-based microcontroller from ST Microelectronics, ferroelectric memory-based MCUs from Texas Instrument, as well as Fujitsu. There's two emerging memory technologies, resistive RAM and phase change memory, have been extensively investigated for use in artificial intelligence applications. In particular, they lend themselves to linear weighting configuration in an architecture commonly known as neural networks, which are made to model the way that our nerves work. They're a very simplified type of, they can provide very simplified type of inference, AI inference that can perform an enormous amount of math at low precision in a very short time, and they can be quite useful for some applications. So with all these devices coming online, let's take a look at outlook for the markets. This is I do a report with a colleague on emerging memories, and so this next slide is from that report. The report's called Emerging Memories Find Their Direction, and it shows that the total emerging memory market, MRAM and 3D XPoint in particular, that we modeled here, could exceed $36 billion by 2030. This chart shows how shipment growth could affect that number. This figure compares the current and projected capacity shipments for the next 10 years for various emerging non-volatile memory technologies represented by MRAM and 3D XPoint versus DRAM and NAND. And the assumptions are that 3D XPoint is adopted widely by Intel customers and Xeon servers, and embedded MRAM replaces most SoC, NOR, and SRAM, and that MRAM has strong appeal for artificial intelligence applications, particularly on endpoints and endpoint devices and at the edge. And this MRAM, of course, includes both standalone as well as embedded applications. So in summary, NOR flash and SRAM have basically stopped scaling, and even DRAM scaling has slowed down. And new non-volatile memories will fill the void and provide capabilities that, for instance, SRAM and DRAM are not as volatile memories. That will lead to new memory-centric computer architectures, and will essentially change the storage and memory hierarchy. And there's four leading candidates of these emerging non-volatile memories. They're magnetic random access memory, phase change memory, resistive RAM, as well as ferroelectric RAM. And leading foundries are already supporting these new memories, and they're in use today. And MRAM, and our projection is that MRAM and phase change memory revenue should exceed $36 billion by 2030. So with that, just to let you know, this is the report that Jim Handy and I did. He's my colleague. And a lot of the information from this presentation was gotten from this report. And the report includes forecasts of emerging memory consumption for embedded as well as discrete applications. And if you're interested in this, there's a URL at the bottom of the slide to learn more. With that, here's also some references that might be interesting to look at. And I want to thank you. And if there is a little bit of time, and if you guys allow that, I'm willing to take some questions.
Definitely. Thank you so much, Tom. I think this was a wonderful session. What a start. Amazing. I would also like to thank Mr. Bindu Madhava and Mr. Isaac for joining us. I think this was amazing. And since you mentioned Tom, why not? Let's ask the audience if there's any question. Let's open the room to the audience now. Guys, you can type your question on the chat box, and let's see if there are any questions. Bring it on.
So yeah, actually with the virtual setting, it's sort of hard to get the questions from each and every person. So I'm going to route the questions across to you. So these are not specifically my questions, but then from the audience. It's always fun to hear you out, Tom, and thanks for joining in. So some of the questions that are pouring in, and it's actually a big list now. So. Okay. All right. So the first question I want to put across to you is, with phase change memory, the specific implementation from Intel, the Intel Optane. Mm-hmm. So Intel has been keeping close guard and making it work with their own processor and infra. So do you see in future that Intel might open it up, or what's the future do you see with Optane? Or is it going to stay with Intel?
Intel was in partnership with Micron, but as I indicated, and you probably know, Micron has dropped out of that partnership. So the question is, would somebody else enter that market to support the needs for 3D XPoint to have a second supplier at least? And that's a good question. What's going to happen there? Intel recently agreed to sell its NAND flash business to SK Hynix. So You know, maybe that's a possibility. They might do a partnership with them on the 3D Crosspoint as well. Just speculating there. I don't know anything. Don't buy SK Hynix because of that. Intel has offered both the SSDs, which are not tied necessarily to their chips, but in particular the DIMM-based technology, the persistent memory DIMMs are. And the reason why they have done that is because they feel it gives them an advantage for those advanced server chips compared to their competition. So, but of course, it always helps if people feel like they can get a second source for those products as well. And Intel has basically been subsidizing their Optane memory business because they feel that it'll help them to sell the processors, which sell at a much higher margin. At least I interpret what's been happening there like that. So it'll be really interesting to see what happens now that Micron has dropped out. Will somebody else come in and help to provide a second source?
So I'll just select one more quick question. There are others which I'll share across to you maybe offline. So another one is, as application and developers who use these technologies. So a big question that comes across to all of us at times, because these are emerging. So we don't have workloads or applications already in place who can fully utilize. What's the kind of applications do you see who can justify putting in persistent memories or these emerging memory technologies? Who will be the users?
So there's as you saw from the example I showed, there seems to be a lot of interest in endpoint devices. You know, consumer devices, in particular those that are particularly those that look like they're going to have an inference engine built into them. Well, first of all, to replace the NOR flash for code storage, but then ultimately perhaps and really driving the volume to replace the SRAM cache for instance, weighting functions for an inference engine, for example. But besides that, also there may be applications that move further up into the data center even that might benefit from a non-volatile memory technology. You know, it provides energy savings, especially if it's built into. I think that's one place where you'll see, for instance, these CXL and other advanced memory fabrics being developed. And it'll be interesting to see what goes on in that space. But I think that could also drive the need for different types of memory. It already is driving, and this is why Intel, I think, has been really getting into it, the heterogeneous memory capability of CXL allows you to use Optane as well as DRAM, even though they have different speeds. You know, it allows you to be able to work with that. But it also potentially could allow you to use other types of memory in that kind of a fabric as well, which could include, for instance, resistive memory or MRAM, or that they could be a part of another component, you know, with some kind of memory hierarchy.
Sure. That was great listening to you, Tom. I think it's a pity that we are running out of time and can't ask you more questions. But thank you so much for your wonderful insight. Back to you, Minnie.
Thank you for the invitation. Take care.
Once again, thank you so much. I think it's an honor for all of us to have you here with us today. And what a great session. I think I speak on behalf of all the attendees here, all the participants here. I'm speaking on behalf of all the 200 people that have joined us here in the room. Yeah. Wow. Thank you so much.
Thank you for the virtual award. Take care.
I think that's what it calls for. Thanks a lot.
Thank you.
All right. Okay. So I think this was a beautiful start. And as I told you that we have planned some amazing sessions throughout the day, and you have just seen a glimpse of it. And I hope you are enjoying already. Now for all the participants that have joined in, there's a special announcement for all of you. I think we are close to 200 people now, and there's a surprise for all of you. So we'll be playing some fun trivia questions for all of you throughout the day, and you have a chance to win rupees 1,000 Indian rupees today per question if you answer the question correctly and well on time. Well, to give little more details about it, I think I'll further, brief you more about this as we proceed. But for now, without any further ado, I want to move ahead towards our next session, which is going to be super, super, super insightful. I'm excited already. All right, so let me now introduce you to our next session, where we'll talk about the challenges emerging from high performance application to new generation computer architecture. And to talk more about this, we have with us the technology expert, HPC storage duration, none other than Mr. Arun Ramakrishnan. So welcome, sir. It's a pleasure to have you here. Are you here with us? Ramakrishnan, sir, are you here with us? I think you're on mute. We can't hear you.
Your mic is mute.
Oh, okay. Yeah, sorry. I'm here.
Yes, we can hear you. It's a pleasure to have you here. Welcome to IEEE Symposium 2021, and we are really looking forward towards your session. Over to you, sir.
Yeah.
So Arun Chengappa here. So you have the share access. Okay. All right. Yeah.
Yeah. Are you able to see it now?
Yes. You can go to slideshow mode. And
Yeah. One second. Give me a second. It's just getting a bit of latency. Yeah. All right.
All good.
Okay.
Yep.
Yeah. Okay. Good morning to you all. I'm here to talk about something that we are all going to face here as the data comes towards us. Let me start with something unusual. Starting with a quote from Charlie Munger, who says, like, invert, always invert in every domain. The key to understanding and designing any architecture as such is basically trying to understand the data that underlies the user applications and the workflow that are going to scale up, and then basically going to present you a data tsunami that's coming towards you. How do you deal with this? How do you handle this in the coming days is what is going to be the crux of this talk. So trying to build up like a lattice work of mental models here, let's start with basically the data, the nature of the data, right? What we all know is we have lots of data, petabytes of unstructured data. We have billions of objects on which the data is being distributed upon. And then on top of that, the present scale workflows now need something that would require, say 50 million, 100 million IOPS on that whole scale and on that whole data spectrum as such, right? Now, what is going to add to this problem is that people don't want to throw away the data. They want to keep it forever for much longer periods than before. And they don't want to get locked into any particular solution, architecture, vendor, etc. And they also want to access this data through not just one particular domain or channel, but through various kinds of channels, right? So just getting a snippet of the data that our actual customers holding for the past 50 years or so here, what is happening is that they wrote the first version of the data into our one particular system over 20 years ago, and they still want access to that piece of data. They don't want to change their code. It wants to be in situ, in place, all protected, but still they want to access it in the same way. So what we are seeing is that the retention period for data and the assurances needed for reliability of that data is growing over time. And this on top of the volume of data that is increasing in the coming years as new applications come and try to process that very same repository of data, right? So when we want to take a look at the whole workflow as kind of like a tiered model, where basically we have on top of the tier or the triangle, however you want to call it, we have the codes that operate out of memory, right? So we start out with the supercomputing and technical applications, which will probably use something like POSIX or an MPI/IO, which are basically file-based and kind of a collective-based IO model. Then we had particular kinds of weather modeling code or data analysis code that was using high performance Fortran data frames, Then we came to Spark. Then we had customers who wanted to use the data over a bulk RPC interface, for example, like parallel NFS. And now we come to the latest set of like microservices and data repositories, where basically we want to look at things like GraphQL and API models of accessing the data, kind of a new one, which are kind of unconventional in some senses, but of course we need to provide the customers access to this whole thing, right? So so this is all about the top tier or the codes that are running in memory. So what do we do? These all talk to a file system based interface that is conventionally called as a tier 0 or the active data tier. Now, what we have here is basically very large amounts of random IO performance, probably scaling up to say 100 to 300, 400 million objects, etc. But then users want random access to this very convenient, right? And then we have the bottommost tier in the conventional sense, where the data basically goes into a cold or a dormant mode, where people want their namespace to now expand to say 10, 50, 100 billion, 200 billion objects. They want strong data protection over time. They want durability of the media format, and they also want something like a good streaming performance over the data. Now, that part, the streaming part, is also changing, where people's needs of getting random access to their core data is also now kind of trickling down into the bottommost tier, but that's kind of where the whole industry is heading towards. And all of this is basically being enabled upon physical storage systems, right? It could be tapes, it could be disk, it could be cloud storage, etc. To now build upon things like geo-replication, backup, multi-site, and all of the and other things on top of this, right? So this was kind of the tiering model of data, where basically you had the namespaces on top, and then kind of like a bulk object store at the bottommost layer, right? Now, when you want to look at the storage models that we have been using, right? We have transitioned basically from like an inline, a NAS or a compute-based model, basically to an out-of-band I/O and metadata being separated out in out-of-band channels, kind of a parallel file system model. What that gives us basically is scaling not only horizontally in kind of like CC NUMA architectures, but it also kind of gives you scaling horizontally across, like, say, data centers and clusters, etc. Right? So if you want to formalize a kind of a goal for data management as such, some of the things we're trying to do here is basically say, like, we want to protect data, where we want to say, like, we want to do backups, we want to do namespace recovery as quickly as possible. Then we want to enable movement of data between any of these layers, right? So it could be from a file system to a cold storage to an in-memory thing. So the tiers are not strictly going to have hierarchical flows. You can have data skipping a tier and moving on to the upper tier or the lower tier directly too. And what people also want is basically unlimited oversubscription to their primary storage. They want to give a notion to the users that their fast primary expensive storage is kind of unlimited in nature. So how do you expand that namespace without the users manually trying to work across the tiers as such, right? So one framework that we have worked with, basically is where you have your top layer, which has the HPC and the servers and your AI ML applications, be it middleware like Globus or etc. Right? So what they're all going to do is they're going to talk to this active tier of data, which is like called as the front end or the hot data part, right? So the active tier could be like your NAS, but in a scale out mode. It could be like something like a burst buffer, which is like all flash conglomeration of very fast NVMe storage, but then all aggregated into a namespace that users can use as if it's like a memory buffer, right? Or it could be any custom parallel file system like IBM Spectrum scale, or like a cluster store with respect to Lustre, or it could be like clustered XFS like that we have. So it could be any one of these things. And then what we want to do is enable automated file management and namespace management on this tier, right? So what we're going to do is we're going to put like a data management framework that's going to sit one level below this storage. And what it is going to do is it's going to do a lot of things that are transferring to the user. In terms of namespace, in terms of like lifecycle management, in terms of how do you get the data flowing between the top and the bottom tier, etc. But all of that being transferred to the user. All the user sees is just the namespace on the file system. He doesn't know that the data could sit basically in a data center somewhere across the world. It could sit in local storage. It could sit in memory buffers. The application wouldn't need to care about that, right? And then on top of it, now we have another goal where we want to say, at the perpetual or the lowermost tier, we want to basically optimize for cost. So it could be something like Chase. It could be a thing like 0-watt storage. That is nothing but a power managed spinning disk configuration, where basically we spin up disks on a need to access basis, and then we shut the rest of the racks down when the access is not needed to those disks, thereby reducing the power requirements. And also we can do some tricks with respect to using much cheaper disks when compared to, say, normal spinning ones or SSDs, for example. And then we also have solutions enabling object storage using stacks like Ceph or Scality, etc. And these are going to solve the need of storing your data at a lowest cost for the user here. Okay. Yeah. Okay. So one of the things we need to look at is having a tiered model like this means that now we need to see what kind of use cases that we can enable for a particular organization or for a research vertical as such, right? So a typical research center, like a supercomputing one, or like say a defense installation, or say a genomics customer, for example, they would have literally tens of hundreds of petabytes of research data that they need to store, right? You can't put all of them on a fast storage. So one solution is basically where we can have parts of the data sitting on the fast storage, but then shunt the rest of the out to the backend system. And whenever the research application kind of spins up, you give them access to the data, right? Now, what we also need is a data management solution that not only looks at the workflow from a data perspective, but also what it has to do now is it has to agglomerate and tie up all the namespaces together. It has to tie up all the computer architectures together, right? So ranging from a cloud to a burst buffer in memory to an NVMe disk to a local storage to a 0-watt storage, etc. These are all different technologies with very different latency characteristics, very different bandwidth characteristics. And yet, when a user tries to read a particular file in a file system, we shouldn't care about any of this. Or what we need to then do is kind of anticipate the workflow and kind of like stage or destage the data and then give them access in the most efficient possible way. So it becomes like a data agglomeration problem, a scheduling problem, etc. And then we want to give this on a namespace that is very familiar to user, right? So it could be like a GraphQL graph API where you have a node that is representing the data. It could be a database where you have a table that represents the data. It could be like a data lake, a data warehouse, or it could be something like a pandas data frame that is there, right? So we are trying to look at the whole system as such and kind of combine all of them together. And then we want to say, like, look, if the user really has a need where, let us say, 100,000 MPI processes suddenly want to do a collective barrier operation and then resume IO, how do you enable that? Because none of your traditional IO channels can cope up with such bursty loads, right? So what we are looking at is from a bandwidth or an IOPS perspective, what we could do is enable kind of a namespace segmentation where some part of it sits in a burst buffer, and then we basically enable some tricks in dynamic namespace management in order to do this, right? So some of the daily challenges when we see a data management system is along some familiar verticals, right? So the first thing we need to do is, of course, we need to optimize for storage utilization, because the most expensive tier now has to be utilized the most. While we want to put as much data as possible into the coldest tier in order to save the customer costs of maintaining his data. And remember, now data is stored in the system for very long periods of time, like say 20, 30, 40 years. So we want to look at the amortized cost over an entire life cycle of the system. Now, what we also want to do is, of course, not, end up losing the customer's data and scratch our head here 10 years down the line just because the tape technology changed under it. So, of course, we want to not only give protection at a bit level to the data, etc., but we also want to give protection against obsolescence of the data, right? We are looking at data, the initial tapes that were hardly, say, 400, 500 megabytes look nothing like the modern, T15K, T20K tapes, right? Which basically are such high performance devices with so much capacity. And yet the interface all seems to be all the same to the user, right? So we want to protect against that. What we also want to do is basically have a simplified set of management. We don't want to burden the user or the middleware to basically do manual shunting of the data between these different tiers in order to actually enable workflows. So once the user or the particular application needs a large amount of data, the data comes in automatically, transparently, and then when the user is done with the data gets transferred back out. Or if it is just a cache copy of the data, we just invalidate the cache and move on to the next working set of the customer, right? So this is one way in which we can accelerate the workflow. And of course, we don't need any manual intervention of the data. And we did talk about, given the longevity of the data nowadays, we want to basically also protect against the storage cost escalations over time, right? So kind of building up a lattice work of mental models of what we were trying to discuss here. I tried to put all of these ideas together in one place. This slide is a bit busy, but then I'm trying to show that, what is the nature of data here, right? So it could be ephemeral data that sits in a burst buffer here. It could be like a distributed parallel file system solutions, like a Lustre. It could be a hybrid solution, or it could be an object storage, right, on top, right? And on the bottom, we could have like tapes and 0-watt storage and clouds and any sort of backend that will help you replicate the data, right? But all the value right now that we want to add to the customer and all the evolution or the challenges that takes place, that is now going to happen in this middle layer, right? So what we are trying to do is we are going to give users the scalable IO channels to his data. We are going to give him the namespaces with respect to the data. But then the user applications have also evolved to the next generation where what they're saying now is like, look, I want to have, say, thousands of objects, thousands of object versions. I want to basically have now full metadata of that object being entrusted to you. We don't want the metadata to sit in 5 different parallel file systems. We want the complete metadata to be reflected in your system. We want to search for this metadata. We want to search for the data also. And we want to do it in a scalable fashion, even if you have 100 billion objects there, right? So things like Elasticsearch, how do you integrate with it? How do you integrate with the next generation of say, semantic graph nodes, for example? Those are kind of the challenges we see. Another type of challenge that we typically see in a data system now is what is called a change or a versioning or a change log system as such, where not only do people want multiple versions of their object, now they also want to see how their namespace is evolving over time. Like for example, let's say you have a file system X. What are the files being added? What are the files being deleted? What are the new projects being created, etc. So what we call as change log, right? And then because most of these data regimens are unstructured, what we also want to do is now have some way to basically enable policies that can help the user manage this, right? So the user might say, take all the versions of my objects on file system Z and then put them in cold storage, right? Or if the user is a cloud customer saying, I have a high priority and a high paying customer whose research data always needs to have, let's say, a 10 millisecond SLA, what we need to now have a policy saying like the moment the user account comes back online on the cloud system, what we want is a policy that can quickly get back the data into the namespace, right? So these are kind of the mental models in which we are trying to evolve this system, both vertically and horizontally. And also what we want to do is not build a monolith, but what we want to build is kind of like a pluggable framework where we can plug in different aspects, like say search, or say for example metadata management systems, etc., and then evolve with the data over time, rather than saying like, look, you need to buy another system that will pull data out of this data archive and then do stuff with it, right? So just building up a little bit of clarity on some of the things that we discussed before. What we see as the online part of the data is kind of like the iceberg that Titanic saw, right? If we make our decisions on the visible part of this data, one day our whole organization is going to get hit with the invisible portion of this data, because management of that is far more important with respect to reliability, with respect to performance, etc. Right? So it's quite important that way. People also nowadays expect what is called as continuous protection on top of deep protection, right? They want to say like, look, I don't care if suddenly my file system has a disk failure. Yes, sure, you can have modern file systems built on top of layers with redundancies at the storage level, at the file systems level. You can do checksums, etc. But then what people are saying is like, look, I don't, I need a level of continuous protection on top of those. So people who are familiar with, say, ZWS snapshot or BTRFS snapshot, for example, they would know that yes, they offer definitely a kind of a protection over time. But now people want to take this and apply it to their entire namespace. They don't care if it is a BTRFS, if it's a cloud, if it is a tape, for example, etc. And they want to basically have continuous protection across the chain. So which means that now we have to find ways in order to protect both the data as well as the namespace of that data, right? So and also what they also want to say is like, not only should you protect my data, let us say that some subsection of my storage architecture blows up due to some, for example, this was literally happening at a customer site back in Australia, where a flash flood came and drowned out their radar arrays, for example. Now, what do you do with this, right? The customer says like, okay, look, I know I lost radar arrays, etc., but then I want to be back online within say 6 hours, for example, right? So what we want to now do is have a paradigm where you cannot, of course, wait for, say, 50 petabytes of data to come online. Nothing can rescue you from that situation. So what we have enabled now is a system where basically the namespace and kind of the metadata comes online very fast. And then as the user is accessing these pieces of metadata, it could be like a file open, a file access, or whatever it is, the policies would basically now run ahead on the background and start getting the most important pieces of data together. Which means that now your recovery point in time is now almost looks kind of instantaneous or near instantaneous to the customer, as opposed to waiting 4 days for the data to come online, right? So basically, what we call as rehydration of the data assets, right? And then users also want to say, like, look, depending upon various needs like monetary considerations, or let us say sometimes, for example, let us say when the some kind of a airline crash occurs, and then we have agencies now trying to look at, let us say, all the crash data. What they did was basically they took all the data and put it on one of our systems. And then now we have to say, look, this data is the highest priority. It does not matter, right? So what we did was like literally give that particular workload all the CPU cycles, all the IO storage cycles, everything that they needed to basically get a report out to the people who needed the answers, right? So what we need now is quick horizontal data movement where it can skip the tiers, and then let us say if due to some reason you lose a data center, there's some kind of an interruption, etc. When the next part of the data comes online, you automatically have that part kind of resuming from where it left off, right? And then we also now look at people saying, like, I want to look at data as not an individual set of namespaces like files or directories or file systems, etc. I want to have an agglomeration that is logical, and on top of it, kind of reflecting my needs, right? So we can have kind of like this data set concept, which can have anything underneath. It can have 5 tapes to AWS repositories. It can have anything on it. And then the customer now builds up his policies based on a particular data set, right? And then, of course, then there, a lot of, especially with technical computing workloads, we see this where basically we want to also do conflict resolution.
I'm
right?
so sorry, sir. Actually, we're short on time.
Yeah,
Just
I'm done. Yes.
Thank you.
Yeah. So that was kind of an idea into the different ways in which we can do data management to fit the emergent needs as such. Thank you so much.
Thank you so much, sir. Thank you so much. It was an honor for us to have you here. I think it was a great session, and I know for a fact that a lot of people out here must be having a lot of queries. So now I would request Mr. Ankit to come in and open the room for the Q&A.
Yeah, thank you so much for your session, Arun. And so we have a couple of questions, but due to lack of time, I will just stick to one. So you talked about emerging technologies and newer architecture. So how do you see, like, with so much of data, people are talking about redundancy, resiliency, and they might keep so many systems online to make this work. But then the energy also becomes a big concern. So how do you see that going into the design?
Right. So one of the things that we encourage people to do is basically have an architecture where the bulk of your data actually sits in cold storage. Cold storage is literally things that can be powered down. Like, for example, ZWS is one solution where it is disk but powered down disk, for example. Or it could be tape, it could be a remote data center, etc. as such. So what we are trying to design here is where about 99% of the data can actually sit in cold storage. consuming literally no memory. And literally when the user starts accessing his data set, he opens it up, all the data now streams online. So that way, all he needs to do is make sure that he has policies in place where the data can flow in between the cold and the energy guzzling hot gears aspect. But other than that, this system kind of eliminates the need to have systems that are commensurate with the size of your data. Your data can be, 5 million x the size of your active system, for example.
Sure. Thank you so much for getting your views on such an important topic and think for the future. Back to you, Minnie. Minnie, no audio on your end.
I'm so sorry. I think that's how virtual life is supposed to be. Thank you so much, Ankit, and thank you so much once again, Mr. Ramakrishnan, for sharing such wonderful insights with all of us. And without much further ado, I think since we're short on time, I'll quickly move on to our next segment. And it's time for me to introduce you to our next speaker for the day, who has an extensive industry experience in software development in the field of data and storage management. Someone who holds 24 patents and has co-authored about half a dozen research papers that were published in the top tier international conference. Please welcome the founder of Airsoft, SNIA board member, High PC, none other than Mr. Siddhartha Nandi. So thank you so much for joining in today, sir. It's a pleasure to have you here with us. Mr. Siddhartha is going to talk about the trends and the challenges of HPS. Hi, sir. Welcome on board. Are you here with us?
I'm with you, but will you enable sharing?
Absolutely. Chingappa, sir, please enable sharing, and we're looking forward towards your session, sir. Over to you.
Sharing is enabled. Could you try bringing up this link, sir? Yeah.
It's enabled, sir. Over to you now.
No, I'm facing some challenge in sharing my window.
Yeah, that happens again. Part and parcel of the virtual life.
Siddhartha, just try the command tab on your keyboard. Command and just press tab to find the right window.
No, okay. How do I bring my PowerPoint application to share?
So
I
you're seeing
think
your full
your
screen.
screen is already been shared. So I think you just move to PowerPoint presentation and just open the presentation. I think it will be visible for all of us if I'm not wrong.
Can you see it now?
Please correct me here if I'm wrong.
Siddhartha, just click on that yellow button on the top left of this window. The middle button. The middle button, as soon as you click on the window, it will turn into a yellow shade. Just, it will minimize this.
Can you share my application screen?
Chingappa sir, can you do it for him while he talks? Is that possible?
Yes, so it is saying that participants can see. Can you see my screen?
Yes, we can.
So I can start?
Yes. But you have to click on your presentation, so we can just see the WebEx window as of now.
So the presentation is not visible?
No, not yet, sir. Chingappa sir, can you just come in and maybe operate it for him if you have the sharing rights as well? Is that possible?
He has the sharing rights.
Oh,
Can you do it? Since he's facing some troubles, if you can operate the slide
I
while
can
he
do
talks,
that.
is that possible?
Ankit, have you received the slides? Ankit?
Not on my end.
Sir, if you can share that right away to my email ID, I can share it from my side. So you can respond to the same email invite which I had shared with you.
okay.
For now, you can stop sharing the screen.
So I guess that will be a great option if you share your slides with Chingappa ji.
Siddhartha, can you try clicking outside this window in the white space around this window? Outside the window. Yeah, just click here.
No, it doesn't happen. So I'm sending it.
Sure. All right.
Yeah, I think it will be better if you send it.
Chengappa, you can take away the sharing rights and then you can take over.
Yeah. Just let us know once you receive the presentation, Chingappa sir.
I will do that. Yeah.
Yeah. So once again, I think it's part of the virtual thing that we are doing today. Meanwhile, while we are getting your presentation on board, sir, please tell us something about your research, the
I
topic that
will
you're
continue with the introduction of this. Okay.
Yeah, just share something in brief
Yes.
so that the audience knows. Yeah.
Yeah. Actually, I'm quite happy. First of all, sorry for all these inconveniences, and I'm really,
Please don't be sorry. That happens.
yeah, I'm really pleased to see that the invitation from this IEEE Bangalore chapter for giving me an opportunity to express my views on high performance storage, and I'm also seeing that 200 people are attending it wherever you are. Good morning, good afternoon, good evening, whatever is applicable, and welcome to my talk. I'll be talking about high performance storage. Uh, it is not to be confused with high performance storage for high performance computing. Usually high performance is associated with HPC, but this is more of an enterprise level high performance storage what I'll be talking about. And I'm really happy to see that it's a continuation of the talks which we had two of them in the morning, Thomas's talk and Arun's talk. Both of them have got significant no, impact on my talk also, though we never talk to each other. So it is sort of a coincidence. So high performance storage systems, I'm calling it an HPSS, is what, in my opinion, is what industry needs today for its enterprise data management. Generally the high performance storage systems has been associated with speed and feed, but that's changing, and because it is also handling only a few mission critical applications, and it's very much customized, and it is location constrained, mostly handling no data in a certain locations, and it's also giving rise to number of data islands because of this, and then you find out customized solutions for connecting these data islands. All these are changing because this growing importance of unstructured data as well as metadata, and availability of cheap cloud storage is significantly disrupting the storage industry, as we know. Then there is another factor is there, which in the morning Thomas articulated so well, is.
And with that, we also have your slides
Yeah, sure.
here.
Okay, thanks.
Perfect. Please continue.
Is this now visible? The slide is visible?
Absolutely, sir. Absolutely.
Okay. Yeah, thanks. I'm on the first slide. So, there's a very inspiring talk from Thomas on this, how this storage technology is changing. I'm also going to add that other parts of the storage technologies, which are also coming into being, for example, computational storage. And there is an interesting panel session in the afternoon on that. So there are multiple multiple hardware technology options are also on the horizon. So that also to be included in the overall storage architecture. And since this new paradigm has come now, which is in a cliche way said, mentioned about data is new oil. So wherever or whatever data you have in the enterprise, every piece of data is to be utilized to its maximum value. So that kind of creates a different type of pressure on the architecture. So on this basis, so first I will be talking about what are the change drivers for this change in stance of the HPSS. And then I will be talking about a proposed architecture for this kind of system. Next slide, please. So this is my idea of next generation HPSS. Will combine speed and feed with share and protect. Okay, so data has become so valuable assets. So naturally, we would like to share it as much as possible to extract its value using different types of applications. And also these data are really the critical assets of the corporate. So we'll share and protect by providing data anywhere and process anywhere functionalities at optimal cost of storage of enterprise-wide data. So this is a kind of a vision statement I have. The idea is that you cannot have in this geographically distributed enterprises that data is always present or data is generated where your compute is present. So naturally, data could be anywhere and process could be somewhere else. And how do you kind of combine them? And keeping in mind the cost of the system. Next slide, please. Thank you. High performance storage in cloud era. So that this is the first slide for the change drivers one. I have got 3 such slides. First change driver, of course, is start with the user and economic side of the enterprise. Data sets are too large nowadays. We have seen enough number of data points on this, and you cannot fit most of the high performance systems wanted to fit it in the memory, at least most part of it, the data, so that it give the highest performance. And data is also not available in one place, so there will be huge movement of data. So how do you kind of keep your compute busy while moving the data? And then multi-cloud data storage. People initially started with cloud data storage in a sort of skeptical way, and then they found out that This is also another kind of vendor lock-in possibility if you are dependent on only one cloud. So naturally there will be there is a strong case, and there is also good adoption in the industry about multi-cloud storage, and that gives you a better price performance of the cloud storage also. Then there is this mainstreaming of big data. Big data used to be a niche application in the corporate world, so you could have specialized systems for that. But now everything is considered to be part of the big data. So that also kind of to be integrated in the HPSS systems. Then there are these technological advances which I briefly mentioned, is high-speed interconnect and SSDs, which we know already. Storage class memory, I think in the morning there was a very nice talk about that. Now the storage class memories is initially it was very exciting because it was byte addressable, and it is still is the byte addressable version is available, but it requires significant change in the software stack, which I will talk about later. So initial, like Intel is shipping those kind of memory as a disk drive form factor initially, but now they are kind of discontinuing to encourage people to use it in byte addressable form. But there are other challenges in this storage class memories, which I'll talk about that. This computational storage is another new kind of storage that is coming into picture, which is a combination of CPU and memory, so that your data movement is reduced wherever data is processed and data is in the same place. Processing and data is in the same place. And so flash technology is also diversified. It's kind of various manufacturing techniques, various flash techniques, and that has actually improved. It has increased the scope of its applicability. Initially, flash was only considered for the high performance systems, but now some version of the flash can be used as even the archive tier, and it has also got some advantages over there. Next slide, please. Then there is a changing workload. Enterprise workloads are now consisting significantly of AI/ML workload, multimedia workload, and IoT, which is streaming data plus another characteristics which are important in IoT is that data comes in small packets and with lots of redundancy because they are mostly sensor data, and sensors are not always all that reliable. So you would like to have multiple sensors sending same type of data. Then there is this new type of processing, which is graph processing, which becoming quite important for the large enterprises. For example, semantic graph and knowledge graph or whatever you call it. Then there is changing data access methods. Traditionally, high performance systems were POSIX based systems. So I hear also a lot of file system terminologies there. But object interface is becoming quite important in the enterprise systems. Most of these AI/ML workloads or big data processing uses kind of an object interfaces. And there are other types of interfaces also kind of rearing their heads, like for example, KV store. And then RDMS is yielding position to dominance to NoSQL DB, and that's also a big shift. And then there is key value store also perhaps more important than next slide, please. This is my last slide on the change drivers. So it's also kind of value proposition of the data is changing. Earlier, it was mostly the processing of the data and extracting inferences from those data was important. But now equally important is the metadata and unstructured data, because of the structured data is becoming only a minuscule of a large unstructured or metadata. And this data, geo-distributed data challenges among is another interesting problem, because you cannot have the strong acid property when you have got a geo-distributed data. And how do you live with weak consistency? Metadata perceived as valuable as data. So there is separate metadata management systems are appearing in the industry, which will kind of answer your question of where is my data, because using metadata you can keep data tracking, you keep the data well tracked, and you can see that how your data is used and how your data is being stored in various places, and that can lead to various types of optimization techniques of how to store data in an optimal way. And one more thing I want to point out is that, which is often missed, that the data security perception is changing. Now we need, in a way, we are going for more and more secured environment, but our data security is still mostly dependent on the network security. But given that your geographically distributed nature of the data systems, you do not have really a perimeter of your data center which you can protect. So in this perimeterless data center world, how do you protect data? So best way to have your security of the data associated with the data items itself. So security should be integrated as a part of the data systems, and that's kind of going to change the world significantly. Next slide, please. So given all these considerations, so I thought of thinking the system in terms of these 4 layers. Performance layer, which is responsible for the high performance computing part of the system, and then data transformation layer, which will ingest the various data and kind of responsible for transforming the data for the appropriate applications without duplicating the data items, which I'll talk about in the next slide. Then there is the active archive layer. Many of these nowadays the data has become valuable. So as someone also mentioned, that people are not willing to delete any data. And so naturally, these data are not used often, so they are reused very rarely. So those type of applications can use this active archive layer, which is kind of a warm storage, write once, read many times. And then there is this long-term data retention layer, which is required probably from various compliance requirement, and this is really the forever tier of the data, you can say. And these are kind of controlled by, on the one hand, the data protection, which includes the traditional data management and data security, and on the other side is the data management, which I'm kind of separating out from this traditional view of data management equal to data protection. And then there is the layers, of course, have got this characteristics that as you go up the layer, performance will go up, and as you come down the layer, the capacity goes up. Next slide, please. So now I'll have brief descriptions of the layers and the challenges due to the various technological considerations. Performance layer data and compute close. So if you want to get a good performance out of the system, you have to have the compute and data close to each other. And so, and this is where you kind of optimize your IOPS or bandwidth. This layer will have little play for HDD. Traditionally, HDD has been there with various types of this one. So mostly this has been already adopted by the industry with NVMe SSD and NVMe over Fabric as the interconnects, but it is still kind of early days. So here actually persistent memory can have a big role, but coexistence, this is the kind of definition of the layer, that coexistence of both POSIX as well as object interface and with some amount of KB store interfaces. This is what the characteristics of the layer is. But these are more or less self-concerned, self-sufficient systems. They will have little connection to the other layers to avoid performance bottlenecks. And even to an extent that that HA possibility, high availability functionalities may get implemented outside of this layer to once again concentrate on the performance of the layer. But this data transformation layer will be very important for such kind of things, because there has to be just-in-time data staging from transformation layer is needed, so that this data movement doesn't block the compute performance. Next slide, please. The challenges are significant, because multiple data access methods are not supported quite well in one integrated system. And if you have got multiple systems, there is a possibility of data duplication, which will increase the cost of the system. IBM Spectrum supports POSIX and object interface both for the same set of data, but it has got some caveats. For example, through file system, you may have access to a data, but the object ACL may not allow you. Now, is it a limitation or is it a feature? That's kind of debate, because if you can do certain applications, you can run your applications using file data, but you may not be able to extract value of the data using the application which uses object interfaces. But now the question arises, of course, whether this data access method is what the user's rights, access rights are, or data is what the user's access rights are about. So there will be, if you include other kinds of interfaces, there will be such kind of conflicting requirements, which needs to be investigated and find a user-friendly solution for it. Then these PMEMs, I think morning talks were quite detailed about the future of PMEM. But one point is I want to point out is that current PMEMs are kind of retrofitted within the existing file system stack. And if you do that, then there is an anomaly, because the current file system stack is about 100 microsecond latency, and whereas this high-speed devices has a latency of a few microseconds. So it kind of you lose all the advantage of high-speed, low latency access of these devices if you go through the traditional file system stack. And on the other hand, if some of these new file systems based using the direct access to the physical device, those are used, they are not matured enough. So the maturity of the regular file systems gives you a lot of features which they may not have these newer file systems, what is called direct access file systems. So those file systems, for example, even HA is not well entrenched into those kind of file systems. And sometimes the recovery is also a problem because permanent storage gives rise to both types of problems. It's a interesting storage technology so that you don't have to serialize your data structure for storing hard disk, which saves you a lot of computation. But at the same time, if you store kind of complex data structure directly onto the physical memory, there could be problems if you have some data corruption. So there are certain challenges there, and these are good research topics, and there has been a lot of research going on in that space. So what we need is a byte addressable, well integrated memory systems for high performance layer of what we are envisaging here. Next slide, please. Minnie, how much time we have?
I was actually just about to say this, so we are already over time, sir.
Because I started late, but anyway.
Yeah.
So data transfer. So I will just talk about the data transformation layer, this slide, and then I will stop.
Sure, sir. Sure.
So yeah. So this is a kind of a layer not generally called out in the traditional storage system stack, because, but I think this is actually at the heart of the HPSS. It is the data management layer. It is also providing data protection and data staging. The data staging in a geo-distributed systems is very important. And not only that, this will also kind of help the system to have less number of data copies, because traditionally the systems have been that when you it is going by the ETL philosophy, extract, transform, and load kind of thing. So when you have to access data in different data access methods, whereas this can kind of do that on the fly, and so that the data copy can be avoided. So metadata is important in this layer, and this is actually a good place to have a metadata management systems here. So this is also kind of a layer which will provide the, as they mentioned, just-in-time data staging using AI, ML, or analytics. This I have mentioned already, the storage architecture performance. So with that, there are two more layers, active archive layers and transform and this long-term retention. Active archive is a kind of a warm storage. I won't go to the, I don't have time for this. So will you please next slide? Next slide, please. Thank you. So these are the challenges. I will point out that this layer may benefit from homomorphic encryption, because this is the layer which will probably have to be responsible for data encryption, and there it will expose data from of different sensitivities. So it will be good to have homomorphic encryption when they become available. Microsoft has released some libraries, and so has IBM. So one may look at those kind of libraries to see how they are useful in this layer. And then computational, because this is a widely distributed layer, so computational storage is another interesting options for this layer. Next slide, please. Hello. Next slide, please. Yeah, thank you. So this is, yeah, okay, thank you. So this is the active archive. So many of the applications, particularly AI ML applications, will compute on the recent data sets but sometimes they will also refresh the model with their older data sets. So you will require this kind of write once, read many times kind of layers. So here the volume of data is quite high. So, and they are mostly at rest, they are not accessed often. So, and this is too large a data to kind of do disk scrubbing kind of techniques to maintain data integrity. So there could be other ways of checking data integrities, for example, RDA, remote data auditing, where you just sample a small percentage of data and do some statistical calculation to kind of ensure that your data is 99.59 or 69 kind of corruption free. Provenance is another factor here. I will not be able to go into details because of the time constraint. So next slide, please. I think yeah, next slide, please. Yeah, thank you. So this is about, I will not talk with the regular archive layer, but there are certain challenges because of compliance requirements. And also there is no standardization in the compliance place. So I'll like to see that there is some work happening in the compliance standardization so that people can provide as sort of today it is mostly described as a process. It is not kind of programmatically implemented as a standard interfaces so that corporates can use it. Next slide, please. This is a summary. So I would like to point out that an academic research community, which they should be looking at very in depth from the certain aspects of this storage system stack, and all parts of the storage system stacks are being looked at, but there is no kind of saying that how we can integrate all these various stacks with various types of trade-offs. Maybe the industrial researchers can do that. And I'm expecting some of the people who are attending the conference today can look at some of these problems which are listed here. Intelligent data management horizontally as well as vertically, and data security in a geo distributed environment, which are listed here, and interface standardization areas of data management, for example, compliance.
So we are 15 minutes up
Yes,
the time,
yes.
so I would request
Yeah,
you
we
to.
are done. I think thanks Minnie for the extra time. I'm done. So
Thank
if
you
you
so much.
permit, I can take a few questions.
Thank you so much. So, sir, for your questions, we have received multiple questions right now, and I think all of these questions are pretty important. So, we would really request you if we can do the Q&A in our breakout session, which will be in, I think, say about after some time. So, if you could just come back and respond and revert to the questions then.
So that's fine. So when is that breakout session?
Breakout session will be in next. Let me just confirm you. I think next 1 to 1.5 hours. So
Okay.
we can circle back to you in an hour.
Sure. All right. Thank you so much.
Perfect. Thank
Okay.
you so much for joining, sir. Thanks.
Thanks. Bye.
Thank you. Bye-bye. All right, so again, another wonderful session, and all of you guys who have posted your question to us, we have already noted your questions. Don't worry, we'll circle back to Siddhartha sir during our breakout session, and we'll be back with him. Meanwhile, you can also keep sending in your questions so that we can keep a note. Moving ahead further quickly, since we are very short on time, and let's proceed towards our next session, where we talk about the mitigating data movement in memory and storage system and about its opportunities and challenges. And to present this, we have with us the Associate Professor, Computer Science Department, Ashoka University, Mr. Manu Avasthi. Hi, Manu, are you here with us?
Yes. Hi, Minnie. Thank you. Can you hear me?
Yes, I can absolutely hear you, and we have your slide here already. So over to you now. Just a quick request, if you can keep a tab on time, we are running quite late and we are behind the schedule. So if you can keep a tab on time.
Absolutely.
Thank you
So
so much.
it is
Over
10:14
to you.
now. I'll try to wrap this up in 20-25 minutes or so. Excellent.
Yeah,
Thank you very much, Mini, and I really like to thank the IEEE Bangalore section for inviting me to this forum and inviting me for a talk. So I unfortunately have not been able to attend all the sessions in the morning, but I think some of these things I was attending Ms. Nandi's talk previously, and I think some of the things that I'm going to talk about are essentially also things that have probably previously been talked about. But what I'll try to sort of give you a sense of is how these things or the problems that we're currently thinking about in terms of individual memory level problems or individual storage level problems, how do they sort of come together and affect the system design as a whole? And how can we look at these things, which we have been again looking at in silos from a system design perspective, and what are the various challenges that kind of exist? And of course, where there exist challenges, there also exist a lot of opportunities. Right? So just to quickly start off, this is a very cartoonish presentation of a typical computer system. Right? I mean, you have your CPU, you have your main memory, and you have some sort of a tertiary storage. We all know about the von Neumann system of computer design, where and this sort of encompasses most of the computational systems that we have today, where the idea is that our instructions and data are kind of stored over here in memory, and they have to be sort of moved over to the CPU for information to be processed over here, right? And fundamentally, most of the explorations around system design that have traditionally happened in the past 50 years or so have kind of stuck themselves within this boundary, right? But the assumption is that all the instructions and data that you're going to ever need are sitting within your DRAM, and then they somehow have to be moved onto the CPU to carry out the processing, which kind of misses out a very important component, which is the storage subsystem over here, right? Because and this is becoming more and more important as the previous speakers have pointed out in the last few slides, right? And this is one of the reasons why the storage system is becoming more and more important, is because of this this inverted pyramid of latencies, which I believe everybody must have sort of seen at some point in time or the other. But I always like to point this out because it really shows the discrepancies in terms of access latencies for all of these different kinds of things. So how quickly you are able to process something is a function of where that data is located. So if you want to do, let's say, an addition, and the data is located somewhere on chip, you can get access to that data very quickly in the order of nanoseconds, and then process that very quickly. As and when you move away from the chip, either into memory or towards tertiary storage, or if you're really unlucky, you have to go over the network and get your data over some sort of a network, the time to access your data actually increases, right? So imagine this: if all you have to do was do an addition, in terms of the latency that you have to incur for that addition, you would do it very quickly if both your operands were sitting in your registers. Whereas if you have to fetch those exact two operands from somewhere over the network and put them in a register, you are going to see multiple orders of magnitudes of slowdown just to do that one addition, essentially. Right? And that's why it's very important to keep in mind this sort of an inverted pyramid of where your data is kind of coming from, and the large discrepancy that exists in terms of latency of accessing that. Right? So for the modern system design, what essentially the questions that we have to now ask are kind of or actually needed to be asked at a kind of a zoomed out level. Right? So we have to look at computer systems as holistic systems that have all of these individual components that I just talked about in the previous few slides. Then they are also running sort of middleware, which is operating systems and other runtimes, and then they are running applications on top of that, and that is true for most computer systems, whether they be server systems, whether they be smartphones, they be desktops. So all of these computer systems are running all of these different levels of applications, and what we need to sort of figure out and look at applications, figure out where the bottlenecks in those applications lie, and if those bottlenecks lie within the subsystems that we are personally interested in. I mean, this forum is more interested in subsystems of memory and storage. So how do these applications, emerging or contemporary, what are the bottlenecks or performance bottlenecks that they have, and how do they translate into specific bottlenecks for the memory and storage systems, and look at various mechanisms using some sort of either already existing notions in terms of system design, or come up with new notions and new computational models of how these systems can be designed and sort of alleviate these problems. Right? And again, I'm going to kind of focus on a few use cases. One of them is what I like to call the big science, and this is not a term that I coined, it's been around for a while. But then the idea is, people talk about data generation in all of these large tech giants. Right? I mean, if you're a Facebook, if you're a Google, you're of course generating tons and tons of data every day. But even if you're not one of these entities, even if you're one, is also growing exponentially because the cost of generating that data has become really, really cheap over time. So what this graph essentially shows you is how cheap sequencing a particular genome has become over time. So in the period of, let's say, a decade and a half, the cost of creating a large data set that represents the biology of one or multiple individuals has become very, very cheap. Right? So you can create all of these data sets that have some information about me or other people there. And in order to solve the biology's problems, or in order to understand new biology about human beings or living organisms, we need to sort of crunch this data. And we need to sort of be able to crunch this data at the same rate at which it's being generated, which you can clearly see that is not happening. Right? So Moore's law, or as a very rough approximation of how well computation can scale up with the generation data, has not been able to keep up with how quickly the data is being generated. And this is again a very, very specific use case, and you can sort of apply this argument to a large number of different domains. But I just wanted to bring this up because this is not something that's talked about a whole lot in industrial venues. And again, this is one more representation of the same thing that I sort of talked about in the previous slide, which essentially says that because the cost has become so low, people are generating lot and lot of data with every passing day, and sometimes even super exponentially to some extent. Right? What this graph over here shows are the different sort of areas in which data is being generated. And if you see that the x-axis or the y-axis is log scale, you can see how quickly the data is being generated in different areas of science. Right? So a lot of data is being generated. This data needs to be processed very, very quickly, so that if we try to do that, then we sort of run into another fundamental problem. Right? So the computational model that we have for the most part, for most of the computers today, essentially remains one node, which means that the computer system has to go somewhere, fetch your instructions and data, bring it over to this centralized unit, the CPU, where some number crunching happens, and your results for that particular processing are being generated. Right? The cost of that computation has been growing, going down very, very quickly. What has been increasing is the cost of getting access to that data. And when I say cost, essentially, it means both in terms of latency as well as in terms of energy. So there was this very nice talk that was given by Ben Daly at Supercomputing, where he kind of projected some calculations in terms of what the energy differential of a computation is going to be, assuming your data is either sitting on chip or you have to go to DRAM to get those two pieces of data. And as you can see by the numbers over here, one is picojoule, the other one is nanojoule, roughly in the same ballpark. So that is 3 orders of magnitude difference in just energy for getting access to your data. Right? And now imagine this scaling with the amount of data that you have to process, which eventually is not even sitting in your memory. It's sitting somewhere on a direct attached storage device, or in the worst case, somewhere across the network. And this energy cost keeps rising further and further up. Right? So one of the things that people have suggested over time is essentially to use different things or different kinds of technologies that are emerging, so that these kind of problems can be solved. Right? I mean, if the problem fundamentally is how do I access my data quickly, which is essentially with low latency and with low energy, then you have to kind of start looking at other things which are non-conventional to some extent. And one of the non-conventional things has been around since the early 60s. So these are the different kinds of non-volatile memory technologies, which is, let's say, phase change memory, which is STT-RAM, which is, ReRAM, and a bunch of other different kinds of things that are already out there. People started looking at how these things can be leveraged to solve the latency and the energy. Right? And then again, there are a whole bunch of good things about these so-called emerging technologies. There are a lot of them out there. They have high area density, so you can pack a lot of bits in a very small area as compared to DRAM. And the good thing is they don't require refresh or standby energy like so, of course, nothing comes with all positives. So there are, of course, some drawbacks for each of these technologies. They have, of course, higher access latencies. There are asymmetric reads and writes. So as opposed to DRAM, where your read and write is going to cost you the exact same amount in terms of energy. For many of these technologies, that is not true. And they have limited lifetime, so you can't write to a second. Right? So then the question then becomes is, how do you use the pluses of these technologies to solve the problems that we have at hand, both at the level of memory as well as at the level of storage? And I'll try to address each one of these things one by one. And just to give you a sense of what has already been proposed as let's say an upcoming use case of how these non-volatile memory technologies are being used is the Intel Optane sort of device that has been put out there already. Right, so Intel Optane is made up of what is known as 3D crosspoint. And one of the use cases that Intel has put out there, which makes Optane available in a DIMM form factor, is that you can take an Optane DIMM, which is a non-volatile memory technology, and you can just chuck it or place it on the same sort of DIMM slot as your DRAM. Of course, it talks to your memory controller using a different protocol as opposed to your DRAM, but if you have been given this ability of being able to place this non-volatile memory DIMM form factor device on the same bus as a DRAM, then you can do a whole bunch of different kinds of things, right? So for example, you can use this device to increase the amount of physical memory space, which essentially is the memory space that you can address with load store semantics by a large factor, because each one of these DIMMs has much higher capacity as compared to the regular DRAM, right? Or because you know that these DIMMs are going to have higher access latencies, you can use the existing DRAM that you have sitting on the memory bus as the DRAM or as a cache for everything that is kind of located within these Optane. Right? And these are the two sort of main modes that Intel, at least as of today, points out as the use cases for the Optane DIMMs. And again, a lot of, of course, hand-waving a whole bunch of things, because what requires to be done over here is that the memory controller needs to be augmented with the capacity to be able to talk to both DRAM as well as Optane DIMMs, possibly over proprietary protocol. Right? So again, because there is this different kind of a technology that is non-volatile and has limited lifetime, there is some amount of bookkeeping that you have to do so that you can increase the lifetime of these devices. And as a result of this, you have to have some additional logic on each one of these DIMMs, which kind of makes sure that your writes are distributed across and the lifetime of your device is preserved, as well as adding a certain number of performance features, trying to reduce the latency, increase the bandwidth, so on. Right? So again, a lot of innovation has to happen both at the level of the memory devices and at the level of the individual memory DIMMs or these DIMM form factor Optane devices, so that you are able to manage each one of these things properly. Right. So that was one way in which people are trying to solve the problem of being able to access a large quantity of the data, which is located on a device sitting on the memory bus, which has a large capacity, possibly a little higher latency, but that's still better than going to the storage system. Right. The other way in which people are trying to fundamentally solve this problem is trying to break the computational or the traditional computational model. Right? So as I said before, the traditional computational model looks something like this, where your instructions and data are sitting in memory, and then they have to go back and forth between the CPU so that the CPU can actually process it. Right? Well, one of the better ways of doing that is, why do we have to move stuff back and forth? Right? I mean, why can't you just take your computation and put it in the memory, so that you don't even have to move that data across, so many interfaces, so many buses, so on and so forth. And that's an active area of research, which essentially falls under this large domain of what is known as in or near memory computation. Right? So then the question becomes, well, okay, I want to do my computation, in or near memory, but where do I do? Right? So one of the different, or few different paradigms have again proposed under this large umbrella. One is where you say, I'm going to do processing near memory. So I'm not going to do processing within my memory devices, but I'm going to create some sort of a logic. And HMC from Micron was a great example of that, where you have this logic layer, and the logic layer can be augmented with some actual logic so that you can do some processing with the data that's sitting right on top of you, specifically in case of HMC. Right, then you can do processing at various places, whether you want to do it within some of the associated circuitry or themselves. Right? I mean, you change the structure of your array such that you're able to do very basic operations, such that and something like that. So for those operations, you don't have to move your data around at all. Right, so those are the kind of innovations that people are doing at the level of memory to solve the problems associated with high latency and high energy of getting the data across. Now I'm going to kind of move over to the different subsystem, which is a storage subsystem, which is this third wheel over here, which people typically kind of tend to overlook, at least in a lot of these architectural studies. What I really wanted to point out over here, if you look at a typical enterprise grade SSD today, not even enterprise, look at the client grade SSD, it's a complete compute subsystem by itself, right? I mean, if I look at the insides of an SSD, you have storage, you have a processor over here, you have DRAM. So again, if I just look at this box over here, it's essentially a computer by itself, right? And most of these things, especially the DRAM as well as the processor that's sitting within the SSD controller, is essentially used for bookkeeping operations today. And when it's not being used for bookkeeping operations, it's just sitting idle, right? So then we have a very sort of a good opportunity at hand, right? So again, this is one of the other things. This particular diagram over here sort of shows you some of the other things that might be potentially present in the controller SoC. And because these are complete compute subsystems by themselves, we can potentially think about sort of offloading some computation that would have otherwise happened on the CPU into one of these units like here. What is the biggest benefit over here? You don't have to ship stuff from your NAND array all the way to the CPU and back. What you can essentially do is figure out what is the computation that needs to happen on this controller SoC and do that computation over here. So the only data movement that takes place is within the NAND array and the SoC, which essentially over the course of your application run, which is probably going to process, let's say, terabytes of data, essentially is going to cut down your energy as well as your latency cost for an end-to-end very high increase in performance for an application, right? But that essentially gives rise to a whole bunch of very, very interesting questions. What is the compute that we need to have? So let's say tomorrow somebody decides, well, okay, let's do smart SSDs or in storage computation or whatever it is that we want to call it. What is the computation that you want to put in, right? I mean, do you want to add more cores? Or is there supposed to be some sort of an accelerator over there? If it's going to be an accelerator, what kind of an accelerator it is? Is it supposed to be adhering to a specific ISA, or should you just put an FPGA in there and let people decide what kind of an accelerator they want? Right. So these are the very sort of set of interesting questions that that need to be answered. One of the things that I'm going to point out over here that typically gets overlooked in a lot of these scenarios is people try to focus or so essentially end up focusing a lot on what is the architecture of this entire in storage compute is going to look like. But a lot of the problems don't stop there. Even if you come up with a very optimized architecture, what essentially you have to think about from the perspective of being able to use that particular product that you put out there is how do you design these APIs so that you can ship computation off to those computational structures that you have put on your controller SoC. How do you divide them up? So you have a large application. What fraction of it goes on the controller SoC? What fraction happens on the CPU is something that you have to decide, and that has to be decided in conjunction with the compiler, with the system runtime, possibly with the addition of APIs. Right? So I'll take maybe, if I may, I take maybe 5 more minutes and then close up. Is that okay?
Yeah, we're already 5 minutes behind.
Right. So I started 10:14. So give me 5 more minutes.
Yeah.
And I'll work.
Yeah. Okay.
Excellent.
All right. Sure.
Okay. So one of the things that I'll quickly mention over here is what is being promulgated as storage class memory. Right. So again, this kind of fits into or sort of breaks our typical notion of a computer in a little bit. Oops. Can you guys still see my slides, or is that not shared?
I think the sharing got stopped, Professor Manu.
Yeah, okay. Now I have the sharing button. So okay, fine, excellent. So storage class memory is essentially the mental model is you have something which essentially is close or which essentially is a storage device that is sitting on a memory path, right? The challenges there are again after, let's say, you are able to architect that something essentially lie in terms of how you optimize the system software, right? So over the course of the last 50, 60 years, the software stack has optimized to look what I have shown on this particular slide. And as Mr. Nandi also pointed out in the previous talk, this storage stack doesn't come for free, especially in terms of latency. So there is a significant amount of latency associated with just the code that you have to execute in this stack. And that is something that you might, or we might have to think about optimizing if we are to think about storage devices that are sitting on the middle part. So I mean, for backward compatibility, it's just easy if you think about, okay, I'll use the same software stack. But then whatever the performance the device is going to offer you, you're not going to exploit it to the best possible potential. So the entire software stack, especially regarding the file system, needs to be kind of thought about from let's say ground up, and there are a lot of these file system options that are there. People have started to think about this as something that needs to thought of, right? So again, I'll not talk about hardware software code design, but let me just quickly sort of put this slide up there for public consumption, because if we have this model where we have storage class memory, or we have something that resembles storage on the memory pass, then there's a lot of interesting questions that we need to answer, right? What needs or what should go in that PMEM device or storage on the memory? Should it be data? Should it be metadata? Should it be both? Is there some kind of a tiering that I need to establish between storage on the memory bus versus storage on the PCIe or SATA? Is storage on or the storage device on my memory bus better off for caching than just using it as actually a storage device, right? So these are all good open questions that people have found answers to for very specific use cases, but there is no generic answer that exists right now, right? Let me just quickly, in 2 minutes that I have, talk about the future of distributed, or I don't want to call it future because this happened today, but the idea is you have all of these new high performance devices coming up. If you attach them in a direct attached mode, you're not able to get the most out of those devices, because one computer system, however powerful that server is not going to be able to drive those devices. So what you have to think about is creating a bunch of flash, right? Or getting together a bunch of flash, connecting it over a high performance, low latency network, and then trying to figure out what it is or how well you can kind of use this disaggregated storage, right? And again, there's one paper that we wrote, which seems like another lifetime, 5 or 6 years ago, which shows that this can pretty easily be done, right? With if you do minimal optimizations to your software stack, your net or your distributor, your flash over the network essentially has the same performance in terms of latency and bandwidth, which is shown by these graphs over here. Comes very close to direct attached storage. So what we are comparing over here is direct attached versus something that is attached over high speed. right? So again, let me not talk about these questions anymore, but if you assume this kind of a disaggregated storage model, that gives rise to a huge set of interesting challenges that we need to sort of start looking at as to how not well or not just optimize the utilization of individual sort of servers in one rack, but the entire rack as an entity by itself, right? So again, this is where I'll stop. One takeaway message, if I'll give everyone in this talk, is this is an exciting area to be in, and there's a lot of exciting work that needs to be, or that still needs to be done. Nothing is a solved problem as of now. Some problems are solved, but for very specific use cases. And I'll just quickly thank all my sponsors for sponsoring the research in these things. All right, with that, I'll just quickly stop here. Thank you very much, Minnie.
Thank you so much, Professor Manu Avasthi. Thank you so much for being here and sharing your valuable insights. We'll quickly open the room for questions, and if we have time, Ankit, just take how many questions we can. Totally up to you.
Yeah, I have multiple questions, but I'll try to limit it to a fewer set. And I know for a fact, like Professor Manu has been doing some really interesting research in his lab, as in we have interacted. And thank you for your session today. So one of the questions is that what is an efficient data structure according to you? Like we talked about all the emerging hardware and things, but as someone who's developing the stack on top of it, because flat memory space also means like you need something to access it. What's an efficient data structure to maintain your metadata and data? So that's one of the questions that we have for you.
All right. Thanks, Ankit. So the answer to that question is essentially it depends, right? I mean, I don't think there is one clear-cut answer as to this data structure works well for all of these use cases that you have at hand versus this other data structure, right? So in some cases, a B plus tree or a B tree might work very well. In other cases, a hash map would just suffice on your needs. It is typically very much dependent on the application that you're running. So if you're running, let's say, a MySQL database versus, let's say, a Tomcat server, right? And in both of these cases, depending on what is the stream of accesses sort of coming to your, let's say, IO subsystem kind of looks like, will eventually determine what the most efficient data structure is going to be for your specific needs. So unfortunately, I think that is the best answer that I have right now. And at some point in time, what I'll try and provide is, okay, for this use case, this is the best data structure. For that use case, this is the best data structure. But at this point in time, this is where I'll start.
Sure, sure. So there are a few other questions. Professor Manu, I'll try to reach out to you offline and have the answers distributed across to the audience. So it was really lovely having you on the session. Back to you, Minnie.
Thank you.
Thank you so much, Ankit, and thank you so much once again, Professor Manu. It was a pleasure to have you here with us. All right, quickly moving on to our next session. Since we all know we are a little behind the planned schedule, so to add to the conversation and tell us more about the challenges in building AI solutions, we have with us someone who has worked in the area of cloud system, HPC, and graph theory for over 18 years now. He's the principal engineer with Ericsson Research, Bangalore. Please welcome Mr. Badrinath Ramamurthy. Hi, sir. Are you there with us?
Yes, I am, and I'm trying to share my content. So the moment it's enabled. Yes. Okay, good.
I think it's enabled now.
Yes, it is.
All right. So just a kind request, since we are a little short on time, so please keep a tab of time. You have 20 minutes to speak, and then the rest, a couple of minutes, we'll take for the Q&A.
Sure.
Thank you so much.
I'm trying to share. Just a minute. Maybe I shared the wrong thing. Give me a minute.
Yeah.
Maybe not. Maybe just stop sharing.
It was visible to us.
You could see it.
Yes.
Okay. I couldn't see it.
Okay.
So I was wondering what's up. But I need to be able to see it. So just give me a minute.
Yeah, no problem. Where are you joining us from, sir?
I'm right at my home in Bangalore.
Bangalore. All right.
Okay. share content. I think that should do it. Okay, so let's see if this works. Do you see my PowerPoint, or what do you see?
Yes, now we can.
Okay. Oh, no, I don't see it myself. So what is this
Some
word?
data scientists in AI system, the first slide, it's out there, it's visible.
Yeah, but it's quite challenging because I can't see it myself. So I don't know how to do this.
Shingappa sir, if you can come in and help, he's unable to have a look
I
at
can't
his.
see.
We
Yeah,
can.
exactly. So that's what I was.
So, Badri sir, so once you do a share content, right? So you just like don't share the whole whole screen. So you can just point it to the presentation and try bringing that up.
Okay, I'll do
So
that.
when you click on share, a window appears, and that in that window, try to find the presentation that you have opened.
Okay, just give me a minute. I understood. Now I understand. Okay, let me do that. And bring that up, and then I'll present, and then I'll go back here and try to share my window. Okay. Okay. So hopefully now you see it.
We again can. I hope now you can see it.
We are
I
seeing
can't,
it in a
but
slideshow mode. Hope you are also seeing that.
no, I don't. But you know what I'm going to do? I have an idea. I'm going to just flip between the two so that I can see what I'm presenting and see if that works. Yeah, I think
Okay,
it
for
should work.
now we are
Okay.
seeing the opening slide which
Yeah.
says with the title "Some Data
Yeah.
Challenges in AI Systems."
Yeah. So I don't see it, but I don't know. Let's just try it out. Maybe it'll work. Yeah. Okay. Let's see.
All right.
Okay.
Over to you.
Yeah. So thank you very much for this invite. I'll try to give you back some time. Let's see if I can do it in 20 minutes. I put a little timer for myself. Let's see if that works. Okay. So I talk about today. I'll be talking about something to do with AI. I come from the AI area. So I'll be talking a little bit about AI. But of course, I'll be talking about challenges that are data related in AI. And also, it will be a bit of a telecom context. So I will be, sharing things from a telecom context. So, that should be interesting for some of you at least. See some telecom problems in this area. Okay. Let's see if I can get this to move. Okay. Okay. Do you see the first slide now? Because I can't see it, so it's proving an extreme challenge for me. Okay, you see it. Okay, so let's see. All right, good. A bit of an outline as to what you're going to see. So I have my outline up here. Hopefully you see it. So I'll be talking a little bit about the context in which we are working. So you'll see me talking about a few telecom problems. I will also give you an idea. So it gives me a chance to set the context from where I'm bringing the problems, and I'll try to then relate it to AI. So what does AI bring into this picture now? Definitely AI has a lot of stuff that is related to some of the stuff that we've heard a bit earlier. I mean, a little bit about hardware and how the hardware is connected to memory and the NVRAMs and stuff like the file system and so forth. But that will not be the focus. For us, the focus for this talk will be more of end-to-end view. Okay, so let me tell you what that means. Okay, so moving on, here what you see is a picture of what's in a telecom network. So now I realize that it's good to be able to point but I'm not able to point. Just give me a minute. See, or maybe Chengapa, maybe it's the good thing for me to share this with you. I realize that's the better thing to do. So if you just give me your email address or something, I'll just post it to you because this is not. Okay. Now it's better. Suddenly it worked. Fine. So so this area that you see here, and I hope you can see my pointer as well. Okay. So this area that you see here is what we call the radio access network. So this radio access network, think of it as the Wi-Fi network. So I'm being a little slow here because I want to make sure that you understand the context of the problem. Okay. So this is the stuff where we have all these phones sitting around, and we have these things that, these are places where we have our telephone antennas, these towers, right? And all these devices connected. Typically, it's what you see out here, the way our phones are connected. But in reality, it could be a little different as well. For example, it could just be that this base station is a sort of a little bit private, in the sense that the area that it covers, this green blob, let's say, or this green and blue blob together, let's say, right? That they together cover just, let's say, a big enterprise, a factory, something like that, right? Even that is possible. But in any case, this is called the RAN, or the RAN, or the radio access network. And then you have something here, which I'm pointing to, this black box here. We call this the core, and this is where all the functionality sits. Typically, all the functionality that's required to handle mobility of users, um, authentication, you turn on your phone and it gets attached to the network, all that kind of stuff. The logic sits here. Also, there's a little data centers where some applications could run. And also, this is the way you connect to the rest of the world, the internet, for example, right? Okay, so we call this part the core networks. So there's a RAN network, there's a core network, and then there is this pipe of a bunch of, let's say, communication channels, and a bunch of equipment like routers and switches. So this purple thing we call the transport. Just to give you some context. So and so now what problems arise? So for example, a telecom operator is providing you services within a certain area, and he wants to do a bunch of different things. So some of the problems I've listed here are all have to do with um, uh, most of these have to do with the management or the operations of this system, right? So for example, a lot of power is being consumed. These are radio transmitters, but then you don't have so many users all the time, right? So think of some place like, a busy business district. You don't have people in the evenings. So you obviously want to save power by turning down some of the radio channels, right? Also, you may want to optimize, people are moving around. So you may want some of these blobs to look bigger, to cover larger areas, and some to cover smaller areas to give better service, right? And then, sometimes for some services, let's say that you're doing some real-time surgery or something like that, right? So you want to have a very high quality slice. So this brown line is called a slice. So you want a very good slice to wherever you're doing this, between the remote and the local operations place. And then you want to make sure that the slice is managed, its quality is maintained, and so forth. So a lot of problems here is what these telecom people do day in and day out. So now, lots of problems, you can look at them. But then obviously this has to do with a lot of data being around, because you want to so the data is not just the end user data. For example, it's not just the video that you transmit, right? But to do these optimizations, you need to do a lot of performance data. So you need to collect a lot of data that tells us how well the telecom system is doing. So what we call data sources could be your external stuff, like some weather information I put here, but it could be the operations data, video data that I talk about. But it could also be some IoT device. It could be a network node, right? A switch in the network. It could be what we call a network function. So I told you, for example, one of the functions is, let's say, a power optimizing function, right? So it could be a network function, or it could be some cloud infrastructure on which these functions run. So you may want to actually collect data. So think about it as you're sensing data, not just transferring data, but you're sensing a lot of data from the infrastructure point of view as well. So for these telecom guys, it's very important that they consider all these data sources, and they talk about how this data is actually made available to the applications, right? So what, this is what people call a data pipeline. Nothing absolutely new here. This is common stuff, but just letting you know that this data pipeline is an integral part of even a telecom system, a large system where lots of data is collected. Yeah. So what they have as part of, at least the way I have seen these data collection work, is that at the very edge they have these things called data collectors. So let me show you a little more context. So there are a bunch of these data collectors sitting close to the data source, and then what happens is that they collect data locally, right? But they also have to figure out how it's made available to applications, right? So they go through some kind of data ingestion process, and they get relayed to some applications which could be sitting. For example, in this case, they talk about data generated in a customer location, but the application sitting in some third-party location. So this emphasizes the fact that data may have to traverse organizational boundaries as well. But the interesting part for me is that all this data has typically lots of metadata associated with it. We just need better data, even for normal operations. And then I'll tell you what more we typically talk about when we come to AI, right? So already, even for the existing data, you have lots of metadata that's available. And then you have global sort of catalogs that talk about how different applications or new applications can find the right data. Okay, so lots of data challenges. I don't think I should repeat all of them. This is very common data challenges, well known. We just talk about a few of them maybe. For example, a lot of this access needs to be done in a secure way. Not everybody should be allowed to access everything. Another interesting part is that a lot of the data needs pre-processing, right? And pre-processing is an interesting thing. Sometimes it's easy to say what pre-processing is, and sometimes it's not so easy. It actually depends on the context. So for example, if this guy is cataloging data and he's putting some metadata saying what's up with the data, what's been done with the data, different things are done with different data, and therefore different metadata needs to be captured. And sometimes that is per application, right? So each application may require different things to be done to the data. And then these need to scale to a very large size. These are typical challenges in these telecom networks. Now, what's AI doing here? Well, here's a little blurb that you'll see from this is from Ericsson, but I assume from any kind of data operator, telecom operator, you'd see something like this, right? So they want to manage infrastructure, they want to do energy efficiency, operational efficiency, improve customer experience, and so on and so forth. But for me, what's interesting is the kind of stuff that people are saying will actually support this thing. So a lot of it is about building cloud native architectures. A lot about is about how the data collection and management is AI ready. So we heard I think Siddhartha and some of the others talk about this, but being AI ready is important. So here's another requirement that's getting into the data pipeline, right? And then they talk about this is going to be enabled by this thing called closed loop operation, and the whole thing is coming under this umbrella of what we call zero touch automation, right? So closed loop control, if you want to think of it. Right? All right, so that is what AI is trying to bring in, right? And then when AI tries to bring in this, it throws a lot of challenges. So here is I take a specific example just to highlight what challenges could be there. So for example, let's say we have these two base stations that are covering an area. Sometimes these areas shouldn't overlap. If they overlap too much, then it causes interference, right? But then if they don't overlap, or if they are too far apart, then we create black holes where for example, if you have your phone in your black hole, then in the black hole, then you may not get connectivity, which means that it's not good news for the operator, right? He loses a customer, right? So how do you control these tilts? And the deal is that a lot of this is affected by a lot of exogenous events, right? This typically is done once a day, but in smaller environments, like I was talking about a factory and so forth, with the dynamism, it could be done several times. But even with once a day, um, there is sufficient challenge. The reason why you don't do it on a minute basis is because there are so many external dynamics, external events happening, and you're often you don't know whether let's say that you did a tilt today and then it gave you some kind of a good KPI tomorrow. You don't know if it's because of the tilt you made, or maybe just there was very little traffic, right? And maybe things improved. So it's very difficult to separate out the effect of different factors. So for example, an RCA agent would be asked the question, did it improve because of the tilt we made or because of things that happen naturally? So if you have an AI that tries to do the tilt, not only does it have to learn to do the tilt, maybe through an RL or something, but it also has to be able to explain at some point of time why what it did worked or what worked of the things that it did. So very interesting questions AI brings to the things that it enables, but it also means that doing all this means you have to support an AI lifecycle. AI lifecycle includes all the data stuff like data preparation and so forth, but it also means things like training the model, which is sort of a different demon, right? So data is being prepared. Where is the training done? That's a good question. Do you train it on the system? Is it offline? If it's offline, then what's the time lag between the data that you gather and the training and the resultant model? And lots of interesting questions come. We know that telecom, for example, right, as many other data sources, they have seasonal variations, and you need to be able to have some kind of understanding of the data. So lots of metadata is required to be able to appropriately train the model and even use the model. And then of course AI brings this closed loop thing. So what does closed loop thing mean in this context? You see the execution, you see the performance, and then that feeds back into how you even pick the data for your next round of training. So some ideas that the life cycle. So I want you to carry away simply that the AI life cycle is an important thing to accommodate in this in the way we deal with data. It's important to accommodate this AI life cycle. Okay. Lots of things. I think I mentioned some of these things. For example, it's important to get the right data, but then the right data could have a lot of transients. Transients could exist over a long period of time. Just to give you an idea, for example, an environmental factor could have a very significant impact on the way data looks, and therefore it's important to be able to segregate that out from the data, and so collect the right data. And often, like it was mentioned, I think Siddhartha again mentioned it, a lot of this data is in some sense sensory data, right? I mean, you're just trying to understand what some KPI looked at or some counter looked at some point of time. And this data therefore has a lot of holes. It is not necessarily a good time series as you would like it to be. So data quality is very important. But on the other hand, you don't want to miss the data. So here's the problem. You're handling lots of data. You want to keep the data, but the data is not great. So you want to do something, you want to only transfer the useful data, right? You don't want to transfer all the data. You can selectively transfer data. You won't even transfer the useful data. So how do you detect that the data is useful as close to where it's generated? Otherwise, you're transferring a lot of data. Every time you transfer data, you're consuming a lot of the resources, including energy, including bandwidth, and so on and so forth. Okay, and there are a lot of bunch of other issues, but I just want to give you a feel that there are a lot of data quality issues with the specific problem that I talked about. The managing those tilts of those antennas has a lot of data quality issues. Okay, Now the little bit of what the architectural connect to this is, right? So in a telecom network context, what this means, so what I have here is sort of like, you know, you remember the antenna picture that I showed you. So think of the antennas as being here, those green and blue blobs as being here. And all these are core, what I put as core, you know, the black box that you saw, they're running a lot of functions. So at the low level, we have things that are actually consuming resources. They could be functions, they could be the data generating endpoints, right? And then in this picture, what is shown in between is from a data point of view, right? From a data stack point of view, you have a bunch of functionality, which we call operations and management in our context. This functionality is all about this functionality is all about the ability to distribute data to the right destinations. And one of the destinations is this thing above that's called the data ops, right? So the data ops is the place where, for example, you have some models and maybe it's a develop environment. You've hosted, for example, some of the AI, right? So the data that comes from here is also consumed here. This is part of the training. Some of these functionalities are executed right here. Some of them are executed here. Some of them may actually be executed at the very end, right? So we have these this little loop that's going here between this data ops environment and what we call the operations and management. That is the part that actually controls all these functionality. You also have a little loop at the very end. So you have these little loops here, which talks about how the end actually consumes the data. So for example, it could be that there's a small AI sitting at the very edge here. And the intention of the AI is to, sometimes you can't just transmit the data all the way up the stack. Latency would be too high. So for example, the RAN has what they call real-time and near real-time intelligence, which means that you have little AI loops or little closed loops that quickly try to do some work, some feedback here and do some control. So you have little AI sitting here as well. So then you have this AI sitting here, which is more in a local data center, but you also have what we call an end-to-end software pipeline, which means that there could be a third-party product, like maybe it's IoT management software, right? And that also needs to work on the same data. And then it has some interesting challenges. For example, can the infrastructure here support pushing some of these functionalities? So think of it as pushing a little bit of AI right towards the edge. And then now this becomes interesting because then this opens up the question about, what kind of support do we need at the edge for AI, right? So definitely I can create a model and I can push it down here, but can I also train the model here, or can I train the model here? The model ultimately is going to be created here, let's say, but can I owned here, but can I create a secure environment down the stack so that we avoid the latencies and the communication costs? And an operator would actually like that, because that pulls down the communication cost. So in some circumstances, it's a very good thing. Just to let you know, this cannot, all this is fine, right? So what I talked about looks very generic. It's a small data pipeline, everything is fine, but this can't be done in a sort of, let's say one particular company or an operator chooses to do it. He just can't do it by himself, because in the telecom industry, at least, everything is governed by a bunch of standards. So I'm just, showing you a bunch of these dotted red boxes with some names. For example, this says ONAP, this is ORAN, this is SA2, this is SA5, this is ZSM. These are all different sort of standards bodies at different levels, let's say, that sort of guide what interfaces should look like. Right? So that means that if we want to actually make this work, remember, this is a third party thing, if you want to make this work, then you better standardize the interfaces here. And then standardizing means that, it sort of, it can go into a lot of detail, right? Not just what the interfaces should look like from what functionality they support, but also possibly what data models they support. And then once you start doing that, then you start digging low level. So what should the metadata look like, and so on and so forth. But then the metadata is often related to the application, and so things become very interesting. But this is just to emphasize that we need to do all this activity of creating a data pipeline, but in the context of standards, right? So that's another challenge that a telecom operator or a telecom company faces. One last thing before I close, this is just one more application. So for example, we've heard about IoT in a couple of places. So IoT is one very important area for networking and telecom operations in general, where you have your end devices here and you have some platform or some stuff running in the cloud, maybe the applications, and you want to push things as close to the edge as possible. So you hear a lot of things about offloading something from the cloud to the edge, and then something from the edge to something even closer to the device. Some people call this the mobile edge, or they call it the mobile end device. So you can think about, and then once you want to allow this, then again the question comes, how do you set up the infrastructure? How do you do the management? Again, another data problem. So you try to do something to solve a data problem and you create an interesting new data problem. But then this is the way things are going, and we all know that mobile edges are becoming more and more commonplace as we get better data centers towards the edge, and we get even more powerful devices. Another just last word here. One word on this context here. I wanted to emphasize that for things like IoT applications, to know, like for example, if I get 23 degrees, right? What does it mean? Oh, it's 23 degrees in a room. Oh, no, not really 23 in a room. It's 23 in one corner of a room, and I have 5 devices. If I take the average of them, then I know what the real temperature is. To make that statement, I need a lot of context, right? And where is the context built is an interesting question. We'd love the context to be built at the end device, but right now it's built at slightly higher level. Perhaps these days it's built in the cloud, but the question is how much can you push it towards the edge? So metadata is very important. All right, so I'd like to wrap up. So data pipeline architectures are central to the functioning of large systems. Telecom systems are nothing new. And what we have tried to do here is see how AI, at least in the context of telecom systems, we have tried to see what kind of constraints it places and what kind of technologies it's trying to push. We have looked at it more from an end-to-end point of view, not here's the file system improvement, or here's how we can run a neural network better. Not that viewpoint, but an end-to-end viewpoint. That's what we've seen here. And lastly, we've also seen, I think at the very end, I showed you that these large system architectures often need to be standardized with harmonized with standardization, which in itself is actually a challenge. But that is the challenge that these large companies face, at least telecom companies. That's the one I have visibility to. So thank you very much for your time, and that's your most important position. So sharing it with us here. So thank you very much.
Thank you so much. Thank you so much for throwing some light on these challenges. I'm sure a lot of us were actually looking forward to what you had to say about this. So quickly moving on to the Q&A, I would request Ankit to come in and take up audience questions.
Sure. Thank you, Minnie. And thank you, Mr. Badri. We were looking forward to your talk because you're someone who actually deploys the entire system. And so we talk about the data pipeline as someone who just develops components going into it, but you're someone who has been putting the pieces together and how actually finally gets used. So I have a couple of questions, but then due to lack of time, I limit myself to just one question. So you mentioned about the deployment of solution with nodes on the edge, nodes in the data center, and then the whole pipeline running in a way. You may not want to actually move all of the data. And people have been talking about distributed AI and distributed computation kind of things. So what are your expectations of the core center, basically the central data center? Is it just some solution or data accumulation place now, or does it play any more significant role in the entire thing? Because all of the AI, everything's running on the edge and just feeding in data.
Yeah, so things running in the edge is a good thing for everybody. and infrastructure is moving in that direction. So including even end devices are becoming more capable. So I agree with you. So things are going there. But then to get larger context, we need some kind of federation among them. So we also talk about federated learning and so forth, where you're learning from multiple independent spaces, so to say. But I think the central data center continues to have its value simply because of current technology infrastructure is not capable of delivering what we want at the edge. The edge power is more of a concern. Centrally, power is less of a concern. So there are a lot of AI stuff that will, I think at least, and I can see that it's continuing to happen in the center. However, I do agree that more and more things are moving towards the edge. So we're going to have, I think, is a no-brainer. We're going to have some kind of a good, healthy combination of the two.
Sure. Thank you so much. I have more questions. Maybe I will pass it on to you offline and have an interaction and pass on the answers back to the audience. Thank you so much for your talk. Back to you, Minnie.
Thank you.
Minnie, your audio is on mute.
Thank you. Thank you so much. It was lovely having you here with us, sir. And please try and stay on. There are, I think, a couple of other more questions which our team will forward to you on your personal email or personally ask you. Thank you for addressing the existing questions. And thank you, Ankit, for coming in and presenting the questions. All right, so quickly moving on to our next session now. So our next session is about the much talked about OpenFAM, a programming model for disaggregated memory. And to throw some light on this, we have with us our esteemed guest, Mr. Masood Abdullah, Fabric Attached Memory Expert, HPE India, Advanced Development Center with over 30 plus years of experience in the industry. Wow. Welcome, sir. It's a pleasure to have you here with us on board. Are you here?
Yeah, I'm here. Am I audible?
Absolutely audible.
Yes. Okay, okay, share is enabled now. Give me a second.
Please. Yes, please try. I hope you're doing well.
Yep, I click the share button.
Yes, we can see it.
Okay.
All right.
Let me. Hopefully you are seeing my desktop.
Absolutely.
Thank you. Okay.
All right. Over to you.
Yeah, I am Masood.
I'm so sorry. Before you start, just keep a tab of time. You have 25 minutes.
No problem.
Thank you.
I am Masood Abdullah. I am part of High Performance Computing Group HPE. So today we will talk about OpenFAM. That's a library for disaggregated memory. So let's move forward. So we'll discuss about motivation for having OpenFAM. Then we will discuss in detail about overview of OpenFAM, the APIs, the performance, and something about the future work and summary. So here, are you guys seeing my entire screen or okay, fine. I think this is fine now. So as you all know, we are having a data explosion. So 1 second. We are having a data explosion. We can see data getting created out of transaction database or from social media or from IoT devices. So this slide shows that memory bandwidth is not going up as much as compute bandwidth. So the y-axis is a ratio between compute bandwidth versus memory bandwidth. If both were growing equally, you would have seen a horizontal line. But since it is memory bandwidth has lagged, so here you can see it in this form. So now we have NVMs, so non-volatile memories of the latencies from 200 nanoseconds to 1 microsecond. So this is in between the memory tier and the disk tier. Traditionally, we had two kinds of computes, shared nothing and shared everything. In shared nothing, we had multiple compute nodes or many compute nodes which had its own data, which had its own DRAM and NVM. This is extremely good for parallel computing. But if these compute nodes had to interact with each other or communicate with each other, this doesn't perform really well. So we had shared everything. This is like a large SMP system, and everything is inside one physical server. But this may not be able to scale indefinitely. So we have something called shared something. Here we take a middle path. We take the advantage of shared nothing, and we have a fabric attached memory pool which has a lot of NVMs, or it can be even other memory types like DRAMs also. And this fabric attached memory pool is connected to the network, connected to these nodes using a memory fabric like InfiniBand, OmniPath, or Slingshot. Let's go deeper. So the importance of fabric attached memory is that this system is that we can scale the compute cluster or FAM pool independently of each other. This both has its own fault domain. So if something crashes here, it doesn't affect anything else. So here we also have reduced depth for IO stack. This fabric attached memory pool is byte addressable, so the memory fabric can access it easily, and it reduces the IO depth. So also we have a large non-partitionable data for something to be used for graph analytics or something like that. Entire data can be stored in this fabric attached memory pool, and these compute nodes can be able to access this data parallelly. So there are certain challenges here. So the cache coherence is within these compute nodes. It actually needs to be taken care. Then this memory fabric latency is larger than the local memory access latency. So we need to refactor the software a little for that. Also, not lot many APIs, easy to use APIs are available for developers. So we are trying to come up with some API library here to access this fabric attached memory. So we have OpenFAM. So currently the available version is 2.0. So it's completely open source project, which is from BSD license. So please do visit GitHub OpenFAM page and have a look at the code over there. Have a look at the documentation at this link. Please do come back to us with feedbacks. So this is currently working on Ubuntu 18.04 and CentOS. We have it's currently supports OmniPath and InfiniBand cluster. We have tested on it. Slingshot support is underway. It's a work in progress. So here we have this large pool of central fabric attached memory, and inside this we have two tier allocation model. We have regions and data items. So regions are like containers, and data items are where actual application data is stored in. This FAM resident data outlives the application. So this can be in persistent memory, or even in this FAM can be made of DRAMs also. So these data items are named data items, and it has permissions associated with it for the access control. So we can have a lot of compute nodes. These compute nodes have its own memory, which can work on for the near memory access. So all these compute nodes see the entire FAM as one unified fabric attached memory. So this is the OpenFAM reference implementation. Currently, we have lots of memory nodes here, and these memory nodes is where the NVMs or PMMs are connected. This memory PMMs or NVMs are this client compute nodes access it via memory fabric, and we use libfabric, which is an open source software internally within OpenFAM to facilitate this RDMA. So here for our management operation, we use gRPC. We have gRPC clients and servers here, and then PMX for launch as a launcher. So this is how our current OpenFAM reference implementation works. We have this metadata services also running in this cluster, so that this handles the named data items and permission management is done by this metadata service. So this OpenFAM provides unified view of FAM, which is located, which is clustered across these memory nodes. And this regions, which I explained in the previous slide, span across these memory nodes. So there are lots of OpenFAM APIs. So there are some region management APIs, so which are like create region, to create a region, destroy, resize region. Similar to that, we have data item management APIs, allocate, deallocate, or change the permissions. Permissions are applicable for regions or data items, and if we don't specify explicit permissions with data item, it inherits the permissions from the region. Then we have the data path APIs. Couple of examples are FAM get and FAM put. Here, in case of FAM get, we get the data. All this data path APIs work on data items. So when you do FAM get, this data item is copied to the DRAM of the local node. So similarly, we have FAM put also. Then we support atomic operations to facilitate access between facilitate the concurrent access of this data item from multiple of clients. These are like fetch operations, add, subtract, max, compare and swap. These are some of them. So this we support 8-byte atomics, which libfabric provides. So we have an overlay on top of that. Then there are some other APIs like memory ordering APIs, fence, quiet barrier, then copy operations, lookups, permission management. These are the other APIs which have not shown explicitly. Please feel free to go through our API documentation in case you need. So I've given the link in the previous slide. Okay, we have run some performance tests of OpenFAM in InfiniBand cluster and also in Omnipath cluster. So we have used 48 nodes of an InfiniBand cluster, which has 12.5 gigabytes per second InfiniBand fabric. So we have used 48 nodes on that. Let's see some performance data. So FAM get, we were able to see latency of around 4 microseconds for all these data path operations. We are getting latency of about 4 microseconds. This latency was measured with 256 bytes of data. So the latency was you can see here across different operation, get blocking, then put blocking, and we have used random and even distribution of data. So this did not change the latency. So it was almost around 4 microseconds. The fabric latency was around 2.8 microsecond in that cluster. Then we did so for the throughput, we used data size of 4 MIB, 4 MIB here. So with that, the maximum throughput from this 16 mem. So here in x-axis, we have taken number of memory servers. In the y-axis is throughput. So we had 16 memory servers. So if we have 16 memory servers, the maximum throughput would be 16 multiplied by 12.5. I think it is around 200 Gbps. This is the maximum bandwidth or throughput. So we are able to achieve around 180 to 195 here for throughput. That is for even distribution of data. But when the data is randomly distributed, obviously there will be bottlenecks in other parts of the system. Some parts of the system might be free, some part of the system might have bottlenecks. So we are seeing lesser throughput with when the data is distributed randomly. So for the atomics, the performance are around, we can see similar to whatever we have seen. It's all in microseconds. We see 5 to 6 microseconds, except for this big spikes here. This big spike this is number of memory servers. So here you can see the blue is one memory server. So when we have lot of PEs accessing one memory server, we see contention there, and that is the reason for these spikes. So we have this second graph we have run with single memory server with increasing number of processing elements. One PE is called P is a processing element. So when we increase the number of compute PEs, we see that the latency increases because of the contention. Here, this is only with one memory server. The second graph is only with one memory server. So we need to have multiple memory servers serving the fabric attached memory. Overall, we see that if there is less contention, or if there are more memory servers so that load is equally split, we will have atomic latency around 5 to 6 microseconds. So here OpenFAM is programming model for disaggregated FAM. So here we are focusing on fabric attached memory. So instead of remote processing element memory, so this FAM data items have names, permissions, and other details. So we have two level of allocation, that is regions and data items. Regions span across multiple memory servers. In our next implementation, we are planning to interleave the data items also, so that the load gets equally distributed. This will help the random access numbers, which I showed in the last slide. So that should get evenly distributed if we have data item also interleaved. So the code is present in GitHub OpenFAM. Please feel free to download the code, play around with it, and probably raise issues or give us comments. We would like to interact with you guys, and contributions are welcome. So in future, we'll be continuing the optimization. So we will add support for FAM. We are thinking through adding support for FAM resilience. Then we are thinking about an archive layer which has SSDs, so that data can be pushed to SSDs periodically, or via user actions or something of that sort. Then currently the atomic operations which are supported are 64-bit atomics, but we are thinking of large data atomic transfers, which basically to 4 KBs or MBs of data. Also, we are thinking of integrating with other programming APIs like OpenSHMEM. So OpenSHMEM is, I think you guys might be aware of OpenSHMEM. In case of OpenSHMEM, we have each PE access the memory from other PEs. So here we are thinking of having FAM as another layer for OpenSHMEM, so that it gets access to the central pool of disaggregated memory also. So that is one investigation we are doing. Then we are thinking of having other interfaces on top of OpenFAM, like HDF5 or Python interface or something of that sort, which will help the programmer productivity. That's all content I had. Hopefully, I think I finished a lot faster than expected. Questions, please?
Absolutely. Thank you so much. All right. So since now we've wrapped up on time, so we can take up more questions, and which makes me happy. So let's quickly move towards the question. So the first question that we have here is, so what are the application workloads of OpenFAM? If you could throw some light on this.
Okay, some of the application which would benefit from OpenFAM are like the graph processing applications. So let's take an example of, let's take a graph processing application where the entire data set can be present inside the FAM. And here it's like, think about it. So in such an application, this needs to move from one part of the graph to another part of the graph, which may not be able to fit in this entire compute PE memory. So this entire thing can be present in the FAM, and this can be analyzed within directly using FAM. So that is, those are some set of applications that we are thinking about.
Okay, all right. Thank you. The next question that we have here is, whatever applications for OpenFAM can be shared, no architecture can be used for the same applications. So what are the implications, latency, cost, and other details?
Can you repeat the question? It broke in between.
All right, I just repeated for you. So whatever applications for OpenFAM can be shared, nothing architecture be used for the same applications. So what are the implications like latency, cost, throughput? Like what are the implications of this?
Okay, so if you look at it, the latencies of Fabric is higher than the latencies of local memory latency. But the thing here is, in case of shared nothing architecture, there needs to be more communication between these compute nodes. Here, the that happens mainly through Ethernet or something of that sort. But here, the communication is via Fabric. The entire memory lies on the FAM, and as I said, this graph kind of applications can be processed with using the central FAM memory. So there are certain things about the cost of NVMs, cost of PMM. Those things, we are hoping that those things will evolve, and we will have a better version of SCM, or we will have some more versions of SCM going forward in future.
Sounds great. There's another fun and quick question. So what is the preferred and most affecting data sharing method, Mutex, Sklock for Fab?
So those other two are within the systems, and here the Fabric attached memory is across a distributed system. So if you are thinking about across a distributed system, you can definitely use FAMs. We have done some projects here to see how this data can be shared between all these things. We have some concurrent data structure implementation also our FAM. So probably those things can be done with when we have in a distributed system.
All right, sounds interesting. And without taking much time, I also want to take another fun question. So, how big the memory pool can grow in size in shared something architecture?
I think it can grow indefinitely. I think it should be theoretical limit would be 2 to the power 64, that or 2 to the power 128. 2 to the power 64 should be the theoretical limit. So that I guess is pretty much sufficient for the current day workloads or some workloads coming up in the near future.
Sounds amazing.
So currently we have tested with 48 node FAM. So 48 node we have tested in a 98 node cluster. We have tested with FAM up to 32 nodes, and each of these nodes had 1 terabyte of DRAM memory. So that is what we have currently tested the system up to. Or I think it was not 1 terabyte. I think it was around 4 or 8 terabytes. So this is what we have tested currently.
Amazing. Sounds great. Thank you so much for answering these questions so patiently, and thank you so much for throwing some light on such an interesting topic. I thoroughly enjoyed it, and I'm guessing so did so many others because we received so many questions and queries for this one. So thank you.
Thank you. Please feel free to visit our OpenFAM GitHub page and have a look around. Thank you.
Definitely. Thank you so much for joining in. All right, guys, so I hope you enjoyed this session. Quickly, once again, if all of you could just maybe show your presence by raising your hand on the chat box, or maybe just using the clap emoji, so that once again, I know that we all are connected and all of us are here. All the participants, I think there are around 150 to 200 people in the room. Yes, amazing. That's the energy that I'm expecting. Super. Now I'm guessing by now most of you have had your breakfast as well. So moving ahead, now it's time for the much awaited session. I know for a fact that all of you have been waiting for this session because now it's time for the panel discussion. And the agenda for today's discussion is HPC, HPDA, computational storage, NDP hurdles, and enablers. And now, to moderate this session, we have with us someone you have already met, someone who has been working hard for past so many weeks to put this event together, and one of the organizing members, program co-chair, none other than Mr. Ankit Mathur. So once again, over to you, Ankit.
Thank you, Minnie, and what a power-packed day today. So we have had some really interesting sessions since the morning, covering the trends, what has been happening. Then we had Professor Manu talk about the really fast memories, and then the last session we had from Masood about how we can move data efficiently and data sharing. So, well, continuing that journey and getting more information. So we have some really knowledgeable set of researchers joining me on the panel discussion. And for this panel discussion, the topic for the day is near data processing and computational storage in the era of HPC and high performance data analytics. So we want to see what has been enabling and what has been the roadblock. How should we overcome some of those roadblocks? And with me on this panel, let me first introduce you Professor Shiva. He is assistant professor from IIT Bombay. And I also have joining me Niranjan Pendarkar from Nutanix. And also we have Sakshi Chaitanya from HPE. So you guys can see all of them. Let me just switch to the grid mode so that I can see all of them. All right, great. So Professor Shiva is from the mechanical engineering department, and he's someone who uses high performance computing day in and day out. So we have been looking at the various components and things as they are being built, but someone who uses it, someone who actually makes use of what can be done with a high performance computing device is where Professor Shiva comes from. And he has worked on different supercomputers across his journey, right from his college days, and now he's in college training more people to do the same. So let me start off our discussion and ask Professor Shiva, so just to have everyone on the same page, how has he seen the high performance computing world change over a period of time, in terms of the data that we have been dealing with, in terms of the compute power, in terms of what we have as a system to work with?
Yeah, thanks, Ankit. First of all, thanks for inviting me to this panel discussion and for having an engaging, day with all these talks. Okay, so just going back, right, looking back now nearly 20 years, that kind of makes me feel old at how things have evolved. Things have evolved significantly in terms of, different technologies, right? And because of the change in technologies, we, as kind of almost end users of this technology, had to kind of constantly, adapt ourselves to the changing hardware scenarios and the changing technologies which are coming. So when I started in this field about roughly about 20 years ago, we were still in the era of single core computing, right? So the processors which are out there were still kind of single core. The memory bandwidth that was available. There was the previous speaker showed that nice plot about the ratio of compute to memory bandwidth. We were kind of right out in that left corner where computing was kind of really still slow. Memory was kind of easily accessible, much faster, right?
So anyone who is trying to guess Professor's age, well, computer world has been changing really fast. So it doesn't take a lot of years for this to change.
Yeah, and it will change a lot in the amount of time that I have left in my career. And just to give you a ballpark of my age, the career ahead of me is longer than the time that I've already spent in it. Okay, so you can then do some analysis based on that. But yeah, just going back to the main point is that what we have seen is we have seen an exponential growth in the compute power, right, from the time that I started as a student. And because of that, we are trying to do more and more complicated problems. The size of the problems that we deal with now has kind of phenomenally increased. Okay, so the point of, like, if you really look at core engineering, scientific computations, we are now talking about doing digital twins of the full stack of the process, right? We could talk about something like a land-based gas turbine, which is producing power. Like, you look at things right from the fuel injection level to the actual transmission of power to a shaft, or even something like a full-blown simulation of a nuclear power plant, right? So you can look down at the nuclear reactions, which is literally like at the microscopic or even lower scales. But then you also look at the whole power plant in the sense that, which is now big thing. So we now are dealing with lots and lots of data. A typical calculation will have what we refer to as about at least 1 billion degrees of freedom, and each degree of freedom will now take of the order of a kilobyte of data, right? So now we're talking about like terabytes of data just being churned through. So you can imagine the scale of problems that we're doing. But also what has happened is that the compute power has increased phenomenally, right? So because the compute power has increased phenomenally, we're able to do more and more calculations on a per core or a per socket basis. But then when you need to communicate across, now the volume of data is changing, right? So you start having these memory bottlenecks, or the communication bottlenecks, and so we have had to kind of adapt our processes and adapt our mathematics actually at some level to figure out this changing nature of these technologies. So it's been a phenomenal time, and I think it's going to change dramatically in the next coming decade because of all the technology that has changed. Many interesting things happened between the years 2000 to 2010. The introduction of GPU technology, accelerators, and then you started having all these, APIs for programming these accelerators. Imagine we started off at a time when GPUs came out, nobody knew how to program them.
Sure.
We were trying to program create them.
Yeah.
So yeah,
Professor,
so there are a lot of.
I'll circle back to you for more information on how you are going about using all of these things. So Sakshi, you have worked pretty much all through the stack. Like you have worked with RAID, you have done like encrypted file systems, you have done data management. Like what else actually remains in the storage stack that you have yet to touch? So Sakshi, what has been your journey dealing with high performance computing and the challenges and things and trends that you have seen along the way?
Sure. Thanks, Ankit. Thanks for the intro, and yeah, so thanks for having me as a panelist here for the discussion. Hope it's audible, right?
Yes, loud and clear. Thank you.
All right. Okay. So like you introduced me, and I've been doing most throughout this stack. I mean, I've started my journey through having it in the core of fiber channel drivers and stuff like that, all the way to going now into management spaces of the storage systems in that sense, right? So the journey I'm seeing, especially with the HPC world, is that I mean, like Professor Shiva was talking about, the bottlenecks have been shifting and stuff, and that has caused evolution within the storage architectures, right? I mean, from all the way from being SCSI based and stuff to fiber channel based, and now iSCSI based and stuff. Now all the vendors are talking about having NVMe or Fabric kind of attachment. That evolution is one story to it. That the connect to the systems is one evolution to it. The other evolutions have been in terms of the media types itself, right? So from a rotating media to solid state media, which is SSDs, and now with within I mean, after SSDs, we have seen this SCMs as being used for the centralized storage systems too, in that sense. Not just connecting to directly to a compute node or anything. It is becoming like a centralized storage media type too, in that sense. However, there have been bottlenecks in each of things. I mean, as we solve one bottleneck, I think we'll come upon another bottleneck in each of the layers that would we progress upon. Like for example, the evolution of SAS and fiber channel to SAS to NVMe. the things have we are using the bandwidth utilization is becoming it's increasing and it's way better from the previous protocols and stuff. But from the latency point of view, unless you go to a different media type, which is SCM or something which is a faster media than things, you would not see that latencies. I mean, latencies still contribute a lot to the problem in that sense, right? So that's the evolution that there's a lot more to catch up in that sense. SCMs are not there as a storage systems to be delivered as a off the shelf. You can go buy from any of the vendors. That's not it there. So that's the evolution that I'm hoping on to catch up with in that sense. That's the journey that I'm seeing.
Sure, great, Sakshi. So let me introduce Niranjan. So actually, he has packed 21 years of experience working in the storage industry behind him. And when I met him, I thought actually the topic should be how do you stay young with all the stress and everything going around. But then the organizer said, like, no, you need to stick to high performance computing. So Niranjan, we'll have a separate session on, but then looks can be deceiving. And welcome, Niranjan. He is working on some of the emerging technologies, and he's working on. He's also the chair for the technical committee for SNIA India. So, Niranjan, can you actually tell us what has been the evolution on the emerging technologies like persistent memories you have been dealing with, and you're actually dealing with replication and various other things associated with the new emerging technologies. So, what has been changing and the material that builds up all these systems?
Yeah, thank you, Ankit. I hope you can hear me okay?
Yes, clear.
Okay, all right. Thank you for introducing me. Thank you for having me as a panelist. Thank you for your kind words as well. And you're right, looks can be deceptive. So we'll talk about that separately. Yeah, so when I started, right, at that time, storage used to be the slowest component, really, right? It used to, there used to be hard disk drives, fiber channel was coming up as well, and fiber channel used to connect to this storage media. And usually the bottleneck would be on the storage. So you can, there is no issue. You can just, the software program itself, the inefficiencies of that would not show up at all. But as we went, what has happened is that the bandwidth hasn't increased at the same rate as the data has increased. The amount of data that is being required to be processed, or for that matter, the storage devices, the sizes of storage devices, that has grown quite a bit. And therefore, what I have seen is that storage has started coming closer and closer to the compute, because the bandwidth is now suddenly slower compared to the data that needs to be processed.
Right, as they say, it would be criminal to go over the network to access a PMEM.
Exactly, exactly. And as Sakshi was also telling us, HDD SSDs came, and then now we have this 3D crosspoint and so many other technologies that have come up, and then now persistent memory, where your persistent storage is sitting right next to the DRAM on the memory slots. And we are at a point, even with NVMe drives, the bottleneck is now slowly shifting to compute. Really, it's just with a few NVMe drives, for that matter, and of course with persistent memory also, it is easy to saturate compute, and the software efficiencies are showing up in much bigger way. And storage is, we are slowly at a point where storage is no longer the bottleneck. So and that's where the emergence of so many technologies that have come up, like near data processing technologies, like for example, HCI environment has come up from that perspective, or for that matter, in memory computing, near memory computing, and there's so many aspects, right? The storage is moving closer to compute. So that is one of the aspects that I have been noticing. And storage is no longer now the bottleneck, or at least we are able to read data much faster than we used to be able to, and we can saturate compute now. So
yeah, great. So we have a lovely audience out here, like over 200 people who are listening in to us. So just a disclaimer that for the panel members, we all are associated with different organizations, but any views that we are expressing are completely our own. So our organizations may not subscribe to the same, but then please feel free with that to ask any questions under the sun, as long as it is around high performance computing. The age related and how to stay young will be later. So, all right, so you can post in the questions to us on the chat group, and we will be happy to take those questions. Circling back to Professor Shiva, so you were talking about the various applications that you run on high performance computing devices, and basically there is a lot of data that gets read in, churned and processed. So can you tell me, how does a day look like in the life of a high performance computing application? Like what happens at different stages? How does the processing happen? What all things go through? And therefore, like, our audience and I myself would love to understand, like, where are those bottlenecks in place? What are we trying to focus on? Are we actually focusing on the right places or not?
Yeah. Okay, that's a very good question, Ankit. So actually, I would like to answer it in like kind of two sub answers. So there are two ways of looking at these things, right? So one is kind of these what we call as routine production type of applications, right? So a production type of application could be something like, let's say, a weather prediction model, right? So we have an input data set of, let's say, the entire Indian subcontinent, and we just want to churn data and kind of predict the weather for the next maybe 3 days or 4 days or a week, depending on the complexity of the weather model. Now, in this, it's kind of a routine run. The inputs are typically again taken in from the current meteorological conditions or whatever it is, and it's kind of fed into the model. The model size can be kind of pretty large, right? So typically, if you look at it, the entire Indian subcontinent is roughly 3,000 kilometers by 3,000 kilometers, give or take, I mean, approx. And then the height of the atmosphere that you have to kind of look at is about like 15 kilometers, right? And we typically want, I mean, today, the state of the art is that you want to look at kilometer level data, right? If you get kilometer level data, now you're talking about, 15 into 3 into 3, which is like about 150 billion degrees of freedom, right? So that's just the geographical points. Now, the typical thing is that you feed in an input size of about that much, then you let it integrate in time, you crunch it in time. Now, typically, if I want a 3-day forecast, I don't want a 3-day forecast calculation to take 6 days. Then it's useless for me. So typically a 3-day forecast will run in about like maybe 3 hours to 6 hours, depending on the size of the processor that you have. And the data size associated with this is a few terabytes. Now, which is now going to be spread across several compute nodes and several processors. The data is outputted very frequently as well, right? In the sense that because when I want to forecast for, say, a 72-hour window, I want to know how the weather patterns change every 15 minutes, every 30 minutes. So imagine that, so in a 72-hour window, I will have roughly about maybe 500 outputs, each of few terabytes out, right? And all this is happening in kind of a 3 to 6 hour window, right? Because that's how the forecast is taking place. So you can imagine that the scale of data that is being churned out, and this is happening day in and day out at your weather prediction facilities, right? So this is kind of a production run. Then you look at slightly more complicated engineering type of calculations, which are not done on a daily production level basis, right? So let's look at the nuclear reactor calculation. Now, this is something which you will be doing something at the design phase when you're actually building the nuclear reactor, prior to building the nuclear reactor or building the digital twin, right? There, the complexity is like, okay, I need to generate this input data set, which could be of the order of, few hundred terabytes again, get all the scales right, and then probably do a calculation, maybe not every day, day in and day out, but you will do, a few tens or few hundreds of these calculations before the actual power plant is kind of built and things like that, right? So it's all depending on the kind of application that you end up with. But at the end of the day, we end up writing large amounts of data. So now in the weather modeling case, time is of a critical essence. So in 6 hours, I need several terabytes of data out for sure. Otherwise, my weather calculation is useless. Now, in the other case, yeah, I mean, time is not as critical. I don't need a nuclear reactor simulation in 6 hours. That's not required. But again, if it's going to take 5 years, it's useless because, like, the design cycle of such a nuclear reactor should be, I mean, the simulation part should be much smaller, right? So we kind of approach these problems, in a slightly different way. So I hope that kind of answers the question that you were asking.
Right, right. So Sakshi, like circling back to you, in your experience, like if customers or users have approached you with like, here is my set of bottlenecks and places in the entire stack, since you have dealt with all the different layers. So what has been your experience? Like, which is the critical piece that you have seen as fix this for me?
Right, interesting, right? So, like, I mean, I probably taking cue from what Professor Shiva talked about, which I think is, having a centralized system for doing all the analytics to and pulling the data into it, right? And I think that's that's one large challenge. And the evolution that I've seen is that there have been technology. I mean, it's a shift from a core computing to edge and core kind of computing, right? Like, for example, the weather stations, the weather modeling that Professor Shiva was talking about is like, should we be doing it at a centralized place? All the modeling should we be done at one, all the data points, should it be crunched at one place, or can there be aggregation at a smaller weather stations, and then a kind of can we derive out analytics from there and then push out for a higher modeling? Can we push out whatever is the data point that
Sort
we
of
would
a
want
distributed model.
distributed in that sense, right? So that basically the problem I've seen is that people want to move their data, and moving their data has been a problem, especially from smaller centers to larger centers, and and stuff like that. That is one area of the problem. However, in a distributed systems kind of thing, the storage, typically if somebody were to be using a technology like erasure encoding or stuff like that, the moving of the data or recovering the data from there has been really a challenge on the network itself in that sense. So those are the kinds, the network being a bottleneck, that's the kind of bottleneck that people really bring it to the table, saying, how do I solve my problem by not having to do the large data that I need to transfer, but can I do the edge analytics and then move only the incremental stuff into the higher thing? That's one of the kind of pivoting point that I'm seeing in most of the discussions for bottleneck resolution.
Sure. So next question that I have is actually for all three of you. So the question is like, you can have a Toyota to run on pretty much any kind of road. So you can have a very generic solution that pretty much settles and runs everywhere. Reliable, you buy it once, runs over like 200,000 kilometers, no problems. Any kind of road, no roads, no problems. And then once you want to have a drag race, then you don't take your Toyota out, you take your Ferrari. Right? It runs only on a flat road with a ground clearance of maybe like 50 mm or maybe slightly more. So, well, high performance computing, I would say, is more like the Ferrari. And so what is your take? What are the specializations in various devices that are going into the whole solution? And can you actually develop the solution in a way that it can work like a Toyota? Give me whatever, I can run it on the cloud, I can run it on every machine, or how do you actually deal with it? Probably Niranjan, your take.
Sure. Thank you. That's nice analogy, by the way. High performance.
Niranjan, before you start, sorry to interrupt. I would just like to add, most of the time people like me take a Ferrari and drive it through a Silk Road type junction.
Yeah. Good one for a Bangalore audience, Professor Shiva.
Yeah, that is so true. So your question was about what advancements that are happening, right? So that will help in the Ferrari scenario, and also that can help general scenario. Is that right, Ankit?
That's right. So yeah, two pieces to the question. One is like, do you want to have a generic kind of solution developed so that I can run it agnostic, I can run it on the cloud, I can do a cloud bursting, if you will, and so the solution runs anywhere, or like I want to really optimize because I only have a certain kind of hardware. So I have an NVIDIA GPU with me, or so now I actually sit and look at each of the instruction sets and code right exactly. No, not one more instruction going in. So like how should we be dealing with the way forward? Because the data set is growing, and we can't everyone afford a Ferrari, right?
That is true. Ideally, we want the best of both the worlds, right? So I would like to run my high performance computing application also along with my other applications if I have in a generic infrastructure that would kind of that will make sure that my resources can be reused, and I can if I have to run Ferrari, for example, high performance computing for some time, then I can provision resources for that and then run there. And once that is done, I can repurpose my resources for other applications and things like that. That would be an ideal scenario. And things are happening to some extent, right? Like that to enable those kind of things. For example, even in a general purpose computing these days, we get GPUs and all those devices available that can be used even with virtualization. Those devices these days could be used so that we can offload some of these high performance computing to these various devices. Then there are these days smart NICs that have come up where you can offload some of the operations over there as well, so that you don't have to load the general purpose CPU, so that general purpose CPUs can be used for applications like high performance computing, because we want to for the processor where HPC application is running or any critical application is running. If we are running storage, network, everything there, then there are those many interruptions in the on the CPU as well, which is bad. So there are so many facilities for offloading these aspects are coming, like SmartNIC is one, or for that matter, the computational storage devices like smart SSDs and things. There's so many computational storage devices where you can offload a lot of let's say storage related, network related operations over there, so that the general purpose CPU can be used for the applications like high performance computing without interruptions. So but we still need the simplicity of deployment and scale of performance and scale of components as we go. Those kind of things we still need. So I would say these advancements are making sure that we can have best of both the worlds, so that we get the simplicity, and at the same time we can reuse the existing components, off the shelf components for running these complex applications.
Just to add to Niranjan in that sense, right? The technology is really enabling anybody and everybody to start doing high performance computing in that sense, right? So basically, you can still have a kind of off the shelf, not so great tuned hardware, or not general purpose hardware stuff, and you can still run your workloads by fanning out in that sense, right? Scaling out, fanning out, and stuff. So it is basically enabling anybody to start doing high performance computing, which could not have been done earlier, which would needed a kind of dedicated architecture solutioning and to go with it. Now I think with the general purpose and putting your high performance workloads on it is enabling in that sense, especially the containerized deployments and stuff. It is enabling those kind of workloads to be added on to a general purpose hardware to start with. But I mean, like Niranjan is pointing out, yes, the hype, all the technology is aware of leveraging the underlying hardware and making best use of them in that sense.
So Professor Shiva, like moving on to you, not everyone has the luxury of the Bandra Worli Expressway or the Ferrari. So how do you deal with it on a day-to-day basis?
So yes, that's what the thing. So when you actually, so I think it comes up with when you are starting to acquire a system, right? I mean, the thought process has to start at that point of time. Like, you have to look at what you are really catering to, right? So you will buy a Ferrari if you know that you're going to do only drag racing, right? And so let's say, going back to the example, right? So if you are, let's say, the IMD, the Indian Meteorological Department, and you know that, okay, I am going to, I'm going to use this machine day in and day out only to predict weather, then you will go down to the fact that, okay, I'm going to get a very specific hardware, very specific machine, program it, fine tune it to the point that, okay, this is going to be my drag racer. But then if you look at general researchers, like even me, or like in academic institute, like an IIT, right? So we have varied set of people with varied set of demands, right? And if you really look at our HPC workloads, they vary dramatically, right? So for example, somebody like me, I tend to use a single calculation would tend to use a large number of computing cores, large amount of memory. Whereas the large set of, there are other sets of users who would use smaller sets of cores and smaller set amount of memory, but do a large number of these ensemble type of calculations, right? So then it's like kind of the pizza delivery problem. Like if you want to deliver pizza, you don't want to take it on a truck. You want to take it in like 50 scooters and go around the city and kind of deliver it, right? So so when you are having a varied set of users where the workloads can change dramatically, I think at that point of time, having the flexibility of what Niranjan has talked and what Sakshi has spoken about, I think that's really useful. And also the burst capacities, right? So I mean, typically, like in research institutions like ours, we do not have a uniform capacity, right? We see these bursty capacities, like towards the end of the semester, students suddenly realize, oh, their projects are due, and then they're like pushing their things through into our HPC system, right? So that's when we want these this capability to scale up. Or I mean, for example, a major conference comes up and people want to put out their data, right? So we need that kind of elastic capacity a little bit as well. So it all becomes sort of a horses for courses kind of question, right? It all depends on what your end user application really is and how you're going to go about using them.
Sure. So in the HPC application per se, let me now take it closer to some of the evolutions that Niranjan talked about, like persistent memories, and we mentioned like going over the network with so much of data, it becomes a big problem because you may have a lot of compute power, but then you spend most of the time carrying the data to the compute.
Yeah.
And that's something like some of the trends are actually changing, that you have some of the media which are so fast. So for that, what has been stopping an application developer like you or a solution provider like Sakshi? As in, what are those things that are pulling us back from the adoption of like a near data processing, having CPUs actually sit where the storage is and actually write distributed running algorithm rather than a Cray-like machine, if you will, like where you have a lot of compute which actually sits together and just talks to each other. And is it because that the HPC applications have the initial read, they write only for checkpoints, or they write only for data, or there are other things that are blocking basically a wide scale adoption of this?
Okay, so I'll answer this in a slightly different way. So first of all, HPC applications work slightly differently from analytics type of applications. So in analytics type of applications, there's a high throughput of data going back and forth continuously. It's not super bursty. Whereas in HPC applications, the data pattern is very bursty, right? So at the start of a calculation, you'll have this huge amount of data being read, and then there'll be a lot of churn in the data, and then there'll be at as you said, at points of checkpointing and so on and so forth. There'll be like these large volumes of write. So now when this is really happening, what I mean, this has always been the problem for us, right? And this has been the problem for us for the past 30 years or so. So a lot of people have actually kind of worked on lower level algorithms to kind of do this latency hiding kind of business, right? So in our own customized codes, we tend to know that, okay, this hardware is going to perform in this way. So we tend to write algorithms where we do this latency hiding for this IO. Now, my personal wish is that, I don't have to put that effort, right? I would like to see this handled by the hardware per se and not really deal it with at my end, because there's a significant effort that I do. And the other thing is that every time there's a generational change in the hardware, there's a new technology which comes in. For example, the moment when GPUs came in, the memory transfers to the GPU, the PCI, bus became our bottleneck, right? I mean, so then we knew that, okay, we really cannot keep transferring data to the GPU memory the way we did it to kind of, CPU memory, right? So it's just too expensive. If we did it, very frequently, it's just going to kill our application. So we have to take everything to the GPU, kind of modify our algorithms. So similarly, right, now we know that there are certain latencies when we go across nodes, when we go across, even sockets, right? If you have multiple sockets on the board, we know there are certain latencies. We tend to hide them in our algorithms. But honestly, as things improve, these latencies don't matter as much, right? As things become closer and closer. But it's a question of the size. It's the volume of the data that is still good. Still, even today, the volume of data that we deal with in HPC does not fit in all these near, elements. We still have to go across. Still have to go. I mean, we no longer use swap space. We are not that archaic, right? Swap space is dead for us. We hold everything in physical memory, but still holding everything in cache or holding everything in buffers closer is still not an option for us, just simply because of the volume of the data.
Sure. So before we go to the audience set of questions, Niranjan and Sakshi, like one or two liner thoughts, and what are the blockers that you have been experiencing in adoption?
Interesting point, Ankit. Yeah, I was listening to Professor Shiva, and what I felt was that, yeah, so definitely the volume of data is a problem. So readings and of course the caches that exist near the processor are smaller and smaller, and the data is like huge. And if we have to really process it, we have to bring it into the near the processor and process it. That's going to be a big bottleneck, and that's where I was talking about some of the computational storage devices. If we can push some of the computation down there rather than bringing the data up there, that could be one enabler. But I think one of the issues there is standardization, because are we going to write our code to different types of hardware devices? It would be much better if there was a standardization so that algorithms can be written in a very standard fashion, right? So that was my one or two lines. Those thoughts went into my mind as Professor Shiva was speaking.
Sure. So Sakshi, any lines of thoughts you have?
Sure. So one, I think one enabler is that people getting to use the new technology in that sense, like is adoption of container worlds and stuff like that, with containerized deployments and stuff. Is that going to solve their problems? I think that's one area that we need to see, and how that pans out in that sense, like that can provide the scale out that they need to deploy it, and provide the abstraction to be able to run it on any platform that they would want to deploy it on, right? So that's one way of looking at it. The other thing, within the storage world, I see like what Niranjan was talking about. It's the scale, the scale of capacity that needs to be handled, the scale of objects that needs to be handled in a high performance computing world. I think that's where we will start seeing some bottlenecks coming into forefront. Like the amount of scale that we'll have to deal with. I guess that's something that needs still more research and solutioning.
So I have like a lot of questions pouring in. So let me move on to those and pose it to you as a group, and any of you are welcome to answer those. So how do you see the role of smart NICs in building high performance PMM based file systems? Typically, what all can be offloaded to a smart NIC for high performance? Niranjan, I think it might be closer to what you deal with.
He's muted. Niranjan, you're muted.
Sorry, thank you. I'll try to answer to the best of my knowledge, right? So smart NICs, definitely they are pretty good in offloading things. So the question is what we should offload, right? Smart NICs definitely allow network to be offloaded. They allow storage aspects to be offloaded as well, so that you can free up the processor to run what it needs to run, which is the applications, right? Now we have seen that smart NICs typically they run low power processors, which means so their speeds may not be as high, or their computational power may not be as high as the general purpose processor, but because there is a low power requirement there. But they also pack a lot of these hardware assistance, like maybe we can do compression faster there, and all those things, right? The checksums faster, or SHA computation faster. So wherever and the smart NICs can also do these DMAs and RDMA kind of capabilities. The movement of data can be orchestrated through smart NICs. So I would say wherever there is a need for doing this computation of checksums, compression, and all those things, they can easily be uploaded there. And also movement of data over RDMA or something like that, that can be orchestrated through these smart NICs. So some of those things could be offloaded. so that we can free up the processor for doing for running the real computations, the applications.
Any additions to that, Professor Shiva or Sakshi?
No, I think Niranjan has kind of really nailed the thing. We have to really identify what needs to be offloaded, right? I mean, what sort of minor computation can I offload? Because the throughput of data from computations will keep coming, right? And then you just need to figure out what part of it can go to a smaller compute on these other things. Yeah, that's
right. And SmartNIC needs to do things at wire speed. It cannot become another CPU that it actually runs a software whole stack on top of it. So, because we'll return to the original problem, I guess, in a different place, like
Right.
Silkboard, right?
Exactly. I mean, so NICs are meant for data movement, and that's what they're capable of doing. I mean, it's not for computational purposes in that sense, right? But however, yeah, I mean, there can be offloads for anything related to checksumming, to data recovery, to stuff like that. Anything related to data movement that is there, that is definitely the candidates for moving it there.
Sure, great. Let me move to the next question, and maybe we can treat it more like a rapid fire. Any one of us just take a stab at it, so that the audience is all satisfied they have an answer to their respective questions. So with so many HPC applications being versatile and unique in their own way, what are the common set of requirements you have for the infrastructure, especially storage for an HPC application?
Common set of requirements, I would definitely say is, I mean, high throughput. That's always right. The faster you want, you get it. That's always there. But the other thing is that with the volume of data increasing so much, I think redundancy. That's a very key critical point which we tend to kind of miss because with the volume of data that is coming in, even if the probability of errors are low, just that with the volume of data, you'll have significant errors which would creep in, and then that would cause, failure of, whatever simulation that you're doing. Right. So fault tolerance and, redundancy checks, I think these are the really important things.
So, Professor Shiva, would you also want to add, like, if you can't afford a Ferrari, then maybe affording a Ford Mustang might be good. Like, it can do short bursts, but then it can't be a sustained long run. So if a bursty traffic,
even a Suzuki Swift is fine if it's able to go at some speed for some small amount of time, right? So that is there. And it always takes me back to Tannenbaum's famous quote in his textbook. Do not underestimate the bandwidth of a station wagon full of tapes barreling down the highway.
Right? Of course.
So nice one.
So if you remember that, and you would be surprised, right? You might think I'm a dinosaur, but we still use tapes sometimes for archival purposes. But it's really useful because it takes a longer time. But
nobody can beat cost. I mean, and this cost factor, nobody can beat tapes.
Exactly, nobody can beat it. And when you're generating terabytes of data, I mean, today tapes, a single tape can hold about 15 TB. I mean, it's getting there, right?
Sure. So another rapid fire question, your ideas on the usage of AI for data offloading to SmartNICs. So can we use machine learning, AI, or other techniques to guess what is the right place for a certain run? Because we may not have a capability of handling everything, but then can AI help us to only have the relevant things being offloaded? Any one of you? Niranjan?
Yeah, so especially from SmartNIC perspective, we have to see what computational device that we need for doing that particular operation, right? Do I need a GPU type of a device or TPU, or what kind of device we need, right? And whether that device is there in the SmartNIC. So, for example, if there is no GPU in SmartNIC and if your computation needs a GPU to be kind of for acceleration to happen, then you need to offload it to a place where it can really be accelerated. So I think we should see what hardware is available in the SmartNIC or whatever device that we want to offload to, and whether the computations suit that from acceleration perspective, right? And that decision has to be taken after that.
Okay, so next question is sort of orthogonal to all of the high performance. It talks about how do you take care of security in all of this paradigm? are any of the high performance computing runs critical from a security point of view? And are we letting our guard down by saying like everyone can DMA the data across, you're opening up your memory space? Can someone cause corruptions, steal data, or do something else? So is security also something that fits into the picture, or it's all performance in this? Because when we talk about near data processing, we are actually saying that, well, I just know what needs to be done, go ahead and do it for me. So, but then
Ankit, if I may, slightly try to, split the question into two things, right? One, the integrity, I think no questions asked, right? The integrity of the data is paramount, right? I mean, we do not want to, we do not want a bit flip to happen anywhere in that sense, right? So that, I think there are enough protocols to take care of any kind of data inconsistencies, in corruptions and stuff. That, I think, no questions asked in any of the protocols that we deal with. That's already part of it. From a security angle, I mean, to me, at least HPC world, it is seen as secure, and it is there within a data center to be doing that kind of application in that sense, right? So I've not really come across where people are using, let's say, for example, something which is highly secure. For example, would somebody be using iSCSI to and enable a chap on top of iSCSI to protect that workloads to be seen that it doesn't happen? I don't see that kind of paranoia sitting in terms of HPC kind of computing world. It is still in a trusted environment, and I mean the technology exists of encrypting the data and storing it and stuff, but that I haven't seen in the HPC world people adopting that, at least.
all right. So there is one question that actually is sort of I don't know where in the horizon, or is it already arrived. So one of the audience is asking about quantum computing and its usage with high performance computing. So any of you want to take that, or
I can try to answer that a little bit. So yeah, quantum computing is the future. It will kind of be a major player. But at least, today what is really happening is that the number of algorithms that can exploit quantum computing is kind of still kind of very limited. So it's looking at, a very, very narrow set of problems as of now. So think about it like, how computing was probably, in the 50s and 60s, right? So you're talking about the days of ENIAC and things of that, where the machine was built for a particular purpose and a particular type of calculation. So we are still in that phase. We're expanding the generalized computations a bit. So we're still seeing that the generalized computation, more generalized computation, is kind of like 2 decades out, right? So, 2 to 3 decades out. Where everybody starts kind of logging onto a quantum computer and starts doing calculations based on that. So we are still in the early days. We still have a lot of life in HPC. I think before HPC ends, Moore's law will break, and I think it's not already broken. I mean, I know IBM just produced something with some 2 nanometer technology. We're getting smaller and smaller by the day, but I think that will end before kind of quantum computing becomes ubiquitous and kind of supersedes what we are doing. At least that's my take on it.
Sure. So we are sort of getting on top of the hour. So one question before we exit to all of you, and then we can sort of a summary. So it is very evidently clear that we need to take the compute close to where the data lies, and only then we can continue scaling out with how the data is growing. But one liner or like a thought from each of you before we close on what, as a summary, what has been preventing or what has been the roadblock for each one of you that you see that in the adoption, like why today, or let's say even tomorrow, immediately, not all of our high performance computing devices are somewhere where we have computational storage or in-memory compute installed. So like Niranjan mentioned about standards and things like that, maybe as a closing thought or summary, so what should the audience take away? And most of the audience are people who are going to be solving these problems. So let's put those questions and problems upfront so that they go back and by the next conference we have, they say, oh, by the way, I got to know of the question, we solved it for you.
Okay, so from a researcher's perspective, what I really think is that the technology comes quickly and changes quite fast. Okay, the adoption of the technology takes time. And the reason why it takes time is that because there's a huge inertia from the research perspective that has been built, right? So the research technologies, and I'm talking about the algorithms, the math behind it has been developed over some 30, 40 years, right? And to kind of change it and adapt it to the newer technology takes time. And by the time we kind of, are getting to the grips of it, the technology flips and changes again, right? And also it takes a lot of effort in terms of kind of learning the new, let's say, the APIs or the new frameworks and paradigms which are being put up. It takes a while to kind of get trained on it. And by the time if you get trained on it, if it's kind of getting closer to, I'm not saying it doesn't become completely obsolete, but it's kind of getting towards the aged portion of its life, right? So then the new thing is coming. So that kind of is what really brings in the roadblock. So we want APIs and paradigms which are kind of easier to learn and easier to fit into our research journal where we don't have to change too many things around.
Sure. Sakshi, any parting thoughts from your end?
Yeah. So while storage has reduced its, or reduced itself being a bottleneck for high performance computing in some sense, but I think the challenges are still there in that sense, right? One, in terms of the latency it can offer for the bursty kind of nature of the reads and the writes that happen in the HPC world. I mean, most of the time will it be idle, and only during the burst can it service those kind of can there be more cache build? Can there be more of things to be handled just to handle the burst of it? That is something that needs still some solutioning part of it. The other area that I see is that distributed computing world, or that is actually adding in a lot of things on being a distributed file system and distributed storage in that sense, right? So they're sharing, rebuilding problems, especially on the erasure encoding. What are the problems that we have with rebuilding in case of failures and stuff? I see there is still a scope for improvement in those areas for sure. So those two that come to my mind, at least for now.
Sure. Niranjan, like are some of the existing technologies still having some juice remaining, and they are still competing and making and in possibly delaying the adoption, or there are some other blockers that you see? Your thoughts?
Yeah. So definitely for HPC, we have to make sure that the processor computes as much as HPC computations rather than doing so many other things, right? Because these days processors are doing so many things, right? Network, storage, and virtualization, and we should give as much bandwidth to the HPC applications as much as possible. And that's where, to me, the offload becomes important at this point. How we can architect our storage, networking, and all these solutions so that we can interrupt the CPU much lesser and let the HPC applications run on it as much as possible. That would be important, and that's where some of these technologies that we already talked about, computational storage devices or smart things, and so many other things that allow us to offload things, and that's where the standardization comes as an issue. We need to get over that hurdle, I would say. And yes, there are, but we are evolving, right? And I agree that it takes time to evolve and adopt all these technologies. PMEM also came so many years back, but it took some time to adopt. But the standardization helped there for sure. So I think that's what I would say at this point.
Sure. Thank you so much, and thanks for joining me in for a panel discussion. Really, lovely to have you guys in the panel discussion. We could probably go on for the next whole day, but then we have limited time. But then for the enlightening discussion that we had, thank you so much. And over to you, Mini.
Thank you.
Thank you so much for having us. Appreciate it.
Yeah, thank you.
Mini, no audio from your end.
All right. So this was a beautiful session. Thanks to all the panelists for joining in today, for taking your precious time for all of us. And thank you, Ankit, for moderating it so beautifully. I hope you guys also enjoyed, all the panelists, while answering and taking up all the audience questions. Did you?
Yes, absolutely. Thank you.
Super, amazing. All right, this was fun. Now, let's move ahead and let me now take you to another session, which is almost as fun as the panel discussion. Next up, we have the lightning talk, where we show you back-to-back presentations presented by three researchers and technology enthusiasts. And I won't tell more about them right now because I really want you to witness it for yourself. So I think now I'll quickly open the room for all the presentation and talks led by Arshad Sohani, Shubhankar Suman Singh, and Prashanti SK. So can we please have the presentation here? Shinakaji, are you there? Can you please plug in the first video? Shinakaji, am I audible? Okay, so we have the video for it.
Thank you so much for attending my talk. I am Archit Somani. Hello everyone. Thank you so much for attending my talk. I am Archit Somani, currently working as a research scientist at Huawei. Prior to that, I have completed my postdoc from Techni in Israel. Before that, I have completed my PhD from IIT Hyderabad. My area of interest are parallel and concurrent programming, software transition memory, distributed system, and blockchain. First of all, I really want to thank to IEEE for giving me an opportunity to present my work at Data and Storage Summit 2021. The title of my today's presentation is A Brief Introduction to Build an Efficient Blockchain. Here are the contents of my today's presentation. First, I'll briefly talk about what is the blockchain, and then I'll show what are the bottlenecks in existing blockchain. To overcome those bottlenecks, we have proposed some solutions, but while building those solutions, we have faced a lot of challenges, which we will discuss in my today's presentation. And later, I'll conclude my slides followed by the future direction. Now let's talk about what is the blockchain. Blockchain is a distributed decentralized database or ledger of records. It consists of set of blocks. For sake of simplicity, I am depicting only two blocks. Each block consists of set of transactions, hash of its own block, and hash of the previous block, which represents or which ensures the immutability properties of the blockchain. There are two main entities in the blockchain. One is the miner, who adds the block to the blockchain, and second is the validator, who validates each block added to the blockchain. And the popular blockchains are Bitcoin, Ethereum, and Hyperledger, where Bitcoin and Ethereum are the public blockchain, whereas Hyperledger is the private blockchain. In my talk, we will mainly focus on the Ethereum blockchain. Now let's look into the Ethereum high-level design. Ethereum nodes form a peer-to-peer system. Clients who are external to the system wishing to execute the smart contracts contact a peer of the system. This will be clear with one example, where I consider four peers, 1, 2, 3, and 4. Initially, I assumed that all the peers have a synchronous view of the blockchain, where they maintain 3 blocks, B1, B2, and B3. And there are 3 clients where they want to execute their request or transaction, so they contacted the peer P4. Here, peer P4 will start behaving as a miner. It executes those transactions sequentially or one after another, calculate the final state, and compute the hash of the previous block to ensure the immutability properties of the blockchain. After forming the block by the peer P4, it broadcasts that block in the network. So other nodes which are there in the network will start behaving as a validator. So once all the rest of the nodes will receive the block P4, they will execute those transactions sequentially or one after another, compute the current state. After computing the current state, they will compare the calculated state with the final state given by the miner. If both the states are same, then they will be agree on the block P4. Otherwise, they will reject the block. And once they will reach the consensus from the network, then that respective block will be added into the blockchain. So here, for sake of simplicity, I assume that they reach the consensus and block B4 is added into their blockchain. So this is the high-level designs of the blockchain. Now let's talk about what is the smart contract. Modern blockchain interposes an additional software layer between clients and the blockchain known as the smart contract. A smart contract is a piece of code deployed in the blockchain node. Client requests are directed to the smart contract, and the popular smart contracts are coin, wallet, and simple auction. Here I'm showing a transfer function from the coin contract. Transfer function consists of 3 arguments. One is the sender ID, second is the receiver ID, and third is the amount which sender wants to transfer from his account to the receiver account. But before going to transfer, there is a need of doing the validations where it will check like sender is having a sufficient amount or not. If sender is having a sufficient amount, then that amount will be withdrawn from the sender account and deposited into the receiver account. Otherwise, this transfer functions will throw in exceptions. Now let's look into the bottleneck in existing blockchain. Serial executions of transactions by miners and validators fails to harness the power of multi-core processors, thus degrading throughput. This will be clear with one example. Here I am considering 2 transactions, T1 and T2, and in figure A, I am representing the serial executions of both the transactions. Here transactions T1 wants to transfer $10 from A to B account, and T2 wants to transfer $20 from account C to account D. One can observe that both the transactions are working on different accounts, so they don't have any conflict. And as we know, multi-core processors are ubiquitous, so there is a need of exploiting those cores properly. So we can execute those transactions concurrently, and while doing so, we can achieve the better efficiency and higher throughput. So this is the motivations of executing the concurrent transactions over the serial transactions in the blockchain. Now let's look into the challenges of executing the concurrent transactions in the blockchain. And the first challenge are identifying the conflict at runtime is not straightforward. This will be clear with one example where I have considered 2 transactions T1 and T2, and both of the transactions are working on same data items K, and assume that one of the transactions is updating that item. So identifying that conflict at runtime is not straightforward, and the simple solution for that is lock. But improper use of locks may lead to a deadlock. Discovering an equivalent serial schedule of the concurrent execution of a smart contract transactions is difficult. So we propose a simple solutions. We use software transactions memory system to solve these challenges. Now it's time to talk about what is the STM. STMs are a convenient programming interface for a programmer to access the shared memory using multiple threads without worrying about the concurrency issues. So user need not have to worry about any deadlock, live lock, priority inversions, everything internally handled by the STM. So basically STM is a multi-threaded library which export following methods such as STM begin, read, write, try commit, and try abort. And user who don't know anything about the parallel programming and multi-threading, he or she can use those methods to make their sequential program to run concurrently. And all the challenges and concurrency issues will be internally handled by the STM library. And the second challenge is validator may incorrectly reject a valid block proposed by the miner. We call such error as a false block rejection. This will be again clear with one example where figure A represents the concurrent executions of 2 transactions. Here transactions T1 is transferring $10 from A to B account, and transactions T2 is transferring $20 from account B to A. One can observe that both the transactions are working on same accounts and updating the balance, so they have a conflict. Once the miner will receive both the transactions and execute it concurrently, it could reach the equivalent serial schedules as T1 followed by T2 and get the final state as A is $20 and B is $0. But there could be possibilities once these 2 transactions receive to the validators, it could execute both the transactions in just the opposite manner from the miner and reach to some different final state. And due to that, validator may incorrectly reject a valid block proposed by the valid miner. And this case should not have to be happen in the blockchain. So we have proposed solutions in which miner appends the block graph in the proposed block to avoid the FBR error. So when the validator will receive that block graph, it will respect the conflicting transactions and execute in the same manner which is done by the miner. Now it's time to conclude my slides, followed by the future direction. We developed an efficient framework for the concurrent executions of SCTs by multi-threaded miner and multi-threaded validator. We implemented our technique, and the proposed multi-threaded miner and multi-threaded validator achieve approx 3.91 times and 48.45 times performance gain over the state-of-the-art SCTs executions by the serial miner and serial validator respectively. There are a couple of future directions. As we have used block graph as a technique, but we know block graph consumes space. So constructing storage optimal block graph is an interesting challenge. Implementing our proposed approach in other popular blockchains such as Bitcoin, Hyperledger, EOS, IO, and IPFS is an exciting exercise. As we know, EVM does not support multi-threading. So another research direction is to design a multi-threaded EVM. And one more interesting direction is to apply the concurrency in the nested execution of SCTs. For more detail about our work, please look into the archive link. I'll be happy to take the questions on my contact details. I'll be present during the sessions to take the questions. Thank you so much.
Thank you so much. That was lovely. All right. Now it's time to move on to our next thing. So now it's time for me to take you all towards our next session, which I'm very excited for. I know for a fact that a lot of people here in this room are looking forward to it. And to present that, we have with us someone who has more than 30 years of experience in the high-tech industry, the battery chain solution architect, and also the SNIA EMEO director, Mr. Jean-François Marie. To our surprise, he's also a basketball player and has been a head coach for over 25 years. Wow. All right, I am amazed already. Please welcome Mr. Jean-François Marie. He is joining us all the way from Paris today. Hi, Jean, are you here in the room?
Hello, can you hear me?
Absolutely. How are you?
Okay, so I'm trying to share my content, but it seems I cannot share any content. Can you hear me, Mimi? Oh, okay. Thank you so much. Here you go. Can you see my screen?
Absolutely.
Okay, very nice. Okay, thank you so much for the nice introduction. So what in the next 30 minutes, I'm going to try to explain the challenge about data. Obviously, you have some blockchain algorithms, etc. So my company is deeply involved in algorithm as well. And what we are trying to solve is data and algorithm applied to data to make sure that you extract something from the data, right? You may have heard that already. Data is something. It's like the new oil. You take oil from the ground, but it has very little value. But you need to filter the oil, you need to extract the oil, you need to change the oil to something which has value. And all companies are facing that challenge. First, extracting data to get something which has value for their companies. But the other challenge is the amount of data they have to face and analyze. And this is changing completely the landscape of all the tools, all the architectures. And I'm going to explain one way to do it. Perhaps to help your companies, your partners, etc. So you have the extract here is really about leveraging new technologies to go fast, right? Feeding the GPUs, feeding the fast algorithm. And one way to do it is to use the emerging technology NVMe. NVMe is a massive parallel protocol, allowing to do massive parallel reach to data. So you can combine that with NVMe over Fabric and DPUs, data processing units, and I will cover that. Yeah, so thank you for the intro. I don't need to do that. My company is a French company. So it's a young company, 12 years old, built from the ground up. And you're going to see that we have developed our own processor, our own core, and it has been designed to manage data, to crunch data, as we used to say, right? To manipulate data, to put algorithm on data to get something out of the data. So small company, we have like 30 patents. We have raised 100 million in R&D, and we have raised already our third generation processor. We have two use cases in our company, and I think that's important to understand that. When you do something about data, you have two ways to do it. Either you offload an activity or like neural network, AI. AI is not inline, right? You do some treatment, you inject in a neural network or in a machine learning thing, it does a job and get the result. So it's kind of an offload out of band. The other activity is inline, right? SmartNIC, all those new adapters. You just take the flow of data and do something while going. And this is the activity I'm going to cover today. It's really how, with the vast amount of data and those challenges, you could re-architect your infrastructure so that you can manage and take care of that big amount of data coming in data centers, edge, etc. Another challenge, right? Interesting. I may cover here very quickly. 75% of the data will not reach data centers. They will not, because there's not enough bandwidth, even with 5G, because there are too many devices. Obviously, you're aware of IoT and all the billion of devices. So when you think about storage, we are used to manipulate 100,000 devices. When it comes to network ports, you're used to manipulate millions ports. But when it comes to devices, we are talking about billions or billions of billions, right? And that's another challenge. Those are generating vast amount of data. So they will not reach all the data centers, and edge will become the new entry door, where you're going to need compute to filter, to analyze, or to pre-analyze before reaching to the data center. If you look at the AI pipeline, this is how it goes, right? You pre-filter and you train with just a subset of your data. So all those initiatives, if you look at 5G architectures, they are super smart in having edge intelligence, and you need such processing power at the edge already. And the associated challenge with that is power consumption. So nonetheless, you need massive amount of power, massive amount in terms of data treatment, but very low power utilization. Those are many challenges we are to face, and this is what we have managed to solve with our approach. So NVMe OF, I'm pretty sure you're familiar with that. It's brand new, right? Brand new in terms of adoption. Specification for the NVMe TCP have been released in 2018, and we start the ramp up. Why is that so long? Because storage guys are very conservative. You may be aware of SCSI. SCSI have been there for decades, right? Manipulating tapes. Before in mainframe, it was not SCSI, it was other protocol. SCSI with open system ramp up. For the 30 years I've been in this industry, it was just about SCSI. Now it's a replacement to that, because SCSI is serial and NVMe is parallel. So if you want to feed GPUs, if you want to feed those parallel algorithms, you need a parallel protocol in order to get your data to your algorithm, right? So it's about massively parallel treatment, and NVMe OS is an answer to that. Now, and attached to that, obviously, you need to feed, you need speed. Are those new generation of SSD? I think you need to think about it. When I got started 30 years ago, HDDs were rotating 5400 rotation per minute, right? Maximum IOPS 20 IOPS. Then we had HDDs 15K, 300 IOPS per drive. First generation SAS SSD, like 6 to 8 years ago, it was about 10,000. Right? So we moved from 300 to 10,000. First generation NVMe SSD, leveraging PCI Gen 3, about 2 years ago. Between, if you look at the SSDs, you can get 50,000 to, let's say, 500,000 per drive. So it's a big gap, 300, 10,000, 500,000. Now what we see, PCI Gen 4 SSD, it's about 1.5 million. So between 500,000, 1.5 million per drive. Think about it. 2 rack unit, 24 drive SSD, that generation is 40 million IOPS. It's a promise. It's very nice. So everything you need to feed your algorithm and everything you need to feed GPUs or high power CPUs doing AI, ML, and all those data analytic things. Problem is in the middle, storage intelligence. And storage intelligence has been designed for SAS, has been designed for SCSI, has been readapted for Flash, but is not yet ready for highly parallel protocols like NVMe and NVMe OS. And this is the next challenge. How do you transfer that data power from the SSD to the applications? So DPUs have been designed for that. It's not a CPU. It's something different. It's a new class of processor, highly programmable. It's not a generic processor like an x86. It's not, right? You may not run all your applications from your x86 on a GPU. It's not a GPU, right? GPU is for graphics. It's for matrix applications. That's why it's very well used for neural networks. It's something different, right? It's what we call a third socket in the data center. You have CPUs, you have GPUs, and now you have DPUs, and you start to see more and more processors of that type. Why? Because it's an all-in-one. You can do networking, you can do storage and security. It has been designed to treat those specific networks and to treat data high speed, low power. So it's fully programmable. C management plane to say, hey, what type of data do I need? What structure do I need? And data plane just to treat that as fast as possible. High performance. It has to take care of all the latest type of interfaces. Mass production interfaces, 100 gig, PCI Gen 4. In the coming years, obviously, we'll see 200, 400 gig PCI Gen 5 or other type of interfaces, right? High speed, you need to treat things very fast, to crunch, to parse, to manipulate blocks very fast. Obviously, it has to be super secure because you need to trust. You cannot manipulate your data without trust and integrity. You need secure boot, you need secure firmware upgrade, those type of features. Obviously, if you have that in a car, autonomous driving, or in a plane, right, or any flying vehicle, you understand how complex it is, how complex the security is, right? You need to fit in there. The regulations are very heavy, so you need a processing unit which may fit in those environments. Obviously, you need a hardware acceleration because the promise of software-defined is nice, but it's not enough. Software-defined is interesting. It has provided for the past 5 years some nice things, but leveraging x86 is not enough. x86 has not been designed to do that, right? So you lose a lot of power. If you think about, let's take something very close to our mind in virtualization. Everyone is using virtualization, VMs. You know what are the hypervisors. When you think about it, one hypervisor could take from 30% to 50% just to do storage. This, you have two choices. Either you take, if you want to run an application, a high power CPU, because you know that you're going to lose 30 to 50% to the storage management. Or if you have such an engine along the side, you can decrease the power of your CPU, or on the same CPU, you can have twice more application running. So it's very cost efficient from a global application perspective. So here is the landscape, and I'm not going to go through. So DPU is not just Calray, right? DPU is a wide range of guys trying to accelerate things along the side of software defined. Yeah, you need software, you need to be programmable, you need flexibility. You don't want an FPGA. You don't want something fixed. You don't want a CPU, because CPU I/O from a CPU are fixed design. They are not flexible. We are talking here about things which are completely programmable, completely configurable on the fly. And here is a DPU. The DPU is a bunch of cores. Here we have 80, but we can hook an infinite number. Fast interconnect, 100 gig, very power efficient. This chipset does not consume more than one SSD. 20 watts in operation for 80 core, 80, right? High-speed interfaces, 200 gig to the chip, Gen 4, as I said. Fully programmable C, using SPDK for storage and other platform for networking and others. Accelerators, crypto accelerators, error coding accelerators, and other things, so that you can really treat data very fast. This is a DPU. And this is an example what we took us 10 years to implement that type of thing. The promise is really high parallelism, massive scale. You could hook 4 of them together, 10s of them together. Not a problem, right? The core architecture allows you to do that. Security, obviously. So what can you do with that? How can you use that type of unique processing power? If you think about blockchain, for instance, as has been explained in the previous presentation, or cryptocurrencies, right? You may have heard about the power needed to hold cryptocurrencies. You may be aware of the power needed to run blockchains and all those very heavy, demanding processing and algorithm. The thing is, you need to feed them with data, right? So the data may come from network or maybe on a drive, and at the end of the day, it's on a drive. So the attempt to go fast, obviously, is to really leverage the NVMe power and those million IOPS or 500,000 IOPS delivered by NVMe SSDs. And the first attempt has been, okay, let's hook those drives into server. Problem with that, on the left-hand side, directed charge SSD, you create silos. On my first node, I have a bunch of drives. Let's say I have 10 terabytes, okay? 10 drives, 1 terabyte each. This means that on that node, if the software is not doing anything about it, making sure that this data is available across all nodes, I want to be super efficient. Those 10 terabytes are just available for that node. If that node takes it all, that's fine. Good utilization. But if that node only consumes 5 terabytes, you're losing 5 terabytes, and you cannot get that 5 terabytes out to another node. If that node needs more than 2 terabytes, it cannot get. Otherwise, replacing SSDs. The other thing is, what you don't see, because it goes so fast, right? Million IOPS, gigabyte per second, tens of gigabytes per second. There's no RAID. There's no RAID protection for those drives, because we are speaking here about microseconds latency. It's not hundreds, it's tens or microsecond latency. And there's no yet card to protect those drives, so they are unprotected. So obviously, what you can, either you need software defined on the top of it to protect your data, recopying, like, Ceph or Object, or all the hypervisors doing erasure coding, distributed erasure coding, or all sort of data copy. It takes a lot of CPU power, as I explained. So it's really inefficient. So you need something to protect your data and to free x86 power so that your algorithm are taking benefit of 100% of the CPU power of the machine, right? If you pay $3,000 just on x86, and 30% of that, thus $1,000, is going to storage management, it's a loss for you, right? You lose 1/3 of your power and your money just to protect data and not to do algorithm. So an alternative needed to raise. And the alternative is obviously to get data outside of the box, no data in the server. But in order to do that, you need a protocol that goes as fast as if data were local. So NVMe OS is that promise. And if you have a flash array, not just a flash array, so you need an NVMe-based flash array, so end-to-end NVMe, NVMe SSDs, NVMe OS on the front. The thing you need is a processing power that allows to deliver the full power of the SSD to the outside, to the compute node. If you have a look at all those flash arrays on the market today, they are struggling because of that. Some guys are doing well, so some guys are doing bad because their storage OS sucks. Many storage OS are limited to 2 million IOPS. Why? Because of x86. If you take a very high power x86 engine with internal drives, you put some intelligence, RAID, logical volume, snapshots, etc., you will never get more than 2 million IOPS on that machine. Never. So that's not enough. You need something more powerful, right? Because you need density, you need power, and low consumption. And this is what DPUs are promising. DPUs are the best position in terms of IOPS per watt. Remember, 20 watts for one DPU and IOPS per dollar. We are able today in 2 rack units, that you see here, 2 rack units, 24 SSD, to have more than 12 million IOPS and 70 gigabytes per second. It's like you have 6 x86 in there, right? So very powerful, delivering Gen 3 type of quality SSDs along the road, and will deliver full Gen 4 type of thing. But you need those things, right? And then what you have is a global silos, a global repository for your data. And you can get, oh, I want this node needs 5 terabytes. Oh, I'm going to give you 5 terabytes. It's secured, safe for you. You don't need to reconstruct your data. And it takes 0 power of your x86 to any data protection or any data provisioning. Obviously, what you expect from those arrays, like new generation arrays, basic services, thin provisioning, logical volume, snapshot to protect and do backup, data reduction, compression, and duplication. And that's nice about GPU because they have been designed for that. You have accelerators, crypto accelerators, hash accelerators, compression accelerators. It's a combination of software, very flexible, and hardware, very fast. Availability, obviously, and security. So really something you can rely on. Another use case would be look a bit differently. And you can combine those things. What you can do, remember those drives inside the box. Now the drives are outside the box. And what you would is, okay, so now let's address nonetheless virtualized environment, but bare metal. Let's address a combination of things, distributed services. So what you need is a DPU on a host as well as in the backend. So you combine both ends of the fabric so that you ensure, for instance, data security, data integrity end to end from your application down to the drive. That's very important, right? booting from NVMe. One other interesting thing is, okay, you're talking to me about NVMe OS, my OS, like Windows, because I'm using Windows, does not support NVMe OS. So I cannot use. Sure, you can use. What you can do is take one of those cards, GPU LED, as an NVMe device. And what is interesting and what we are doing here is that card is seen as an NVMe device. You don't need a specific driver, you just need an NVMe driver. The Windows has supports NVMe. So, and we have tried that many times. You hook the card in, you boot your Windows, and you see an NVMe drive. So the beauty of PCI, multifunction PCI, plus NVMe, makes this very interesting. So what you can get is see an NVMe device. So your NVMe OS device is routed through the card, and the card is proposing on the PCI NVMe features. So let's say I take my 5 terabyte logical volume NVMe OS. The card will get that as a drive, is a network drive, and will propose it as an NVMe device of 5 terabytes. So that's interesting because it opens door to more use cases, to more OS, to more flexibility. At the end of the day, perhaps you don't need NVMe OS. NVMe it may be good enough. Obviously, if you need lower latency and you wish to go to ROCE, GPU direct type of approach, etc., yeah, you would need NVMe OS. But there are good alternatives and good mixture of new type of architectures coming. So the role of the DPU is really a translation between NVMe and VMOS, and that's very interesting. For the first time, really, it's end-to-end NVMe. The device speaks NVMe. NVMe OS is just NVMe. So NVMe by default is NVMe on PCI. NVMe on TCP is NVMe in TCP/IP. ROCE is NVMe in UDP. You have NVMe on fiber channel. So you have end-to-end things speaking natively NVMe, and the drive speaks NVMe, right? So that's interesting. There's no big loss in terms of the translation. There's no translation, just transport. Same type of services you need, obviously, at the end of the day. Let's finish by the hyperconverged type of approach. And I'll explain that, right? Hyperconverged takes a lot of power just to ensure data resiliency, data copy across the nodes. And what we are building is a global data repository with storage adapter. So the GPU inside the host takes control of the drives. The x86 does not manage the drives anymore. And what we are using here is exactly the same technique as GPU Direct. We connect on the PCI two devices. We connect an SSD and our GPU, bypassing the x86. So every single storage activity will use 0 CPU of the x86. So the GPU takes control of the internal drives, do the protection, propose those logical volumes inside the host. And because it's also an initiator, it's also an NVMe OS thing. It proposes the internal drives, sorry, to the in-band 100 gigs. So every single node connected to that network will see those volumes from the internal box. So imagine now you have like 9 servers with internal hosts, all interconnected with DPUs. You create a global data lake across the board. So if you move a VM from one node to another, you don't care. You don't need to move the data. If you're familiar with VMware, if you do a vMotion, what's happening is the VM memory CPU is moving to another node, but the data remains on the first one. So you're going to use the interconnect to access the data. So what you need is the storage vMotion to move that data to the exact same node your computer is running on. With that, you don't need anymore. You gain a lot of power, a lot of cycle, a lot of energy. You do not busy your interconnect network because of the data. It's a global repository, and any compute can see any data from that repository as if it was local data. So what you need that peer-to-peer technology, which allows to take control, like the GPU direct. No specific needs in terms of driver, you just need NVMe driver. And it's a global data repository, as I said, across the board. And also you can connect an external array, so very interesting. So, and you scale really storage and compute independently. Same services, what you expect, data protection, resiliency, high speed, etc., etc. You may find your case. So as a conclusion here, we are facing a massive disruption, and for disruption, it takes time. Replacing SCSI with NVMe will take time because there are many installations leveraging SCSI today. High capacity SSDs are starting to raise, QLCs and PLCs starting to raise. The old flash data center is yet there, just the beginning. And it's also a major shift with software defined. And the future will be a combination of software defined and DPU accelerated. You need companions. One cannot fit all. One cannot treat that vast amount of data. So think about it. If you have already installed object store, does not scale. It does not scale. ARG coding takes so much power that you cannot count on that. Big customers, they have more than 100 CPU just for ARG coding. If you multiply 100 by 3,000, it's $3,000 just to do ARG coding software. What a waste in terms of energy, power, and dollars. And the right balance would be a combination of acceleration and software defined, because you need flexibility, you need programmability, and that type of DPU, as I said, is highly programmable to sustain many loads, many type of acceleration, many type of algorithm. I've reached the end of my presentation. Thank you so much for your time, your attention, and I hope you'll get a good day.
Thank you so much, John.
My pleasure.
This was nothing but. Is my audio fine?
I think your audio is a bit garbled. So
is it better now?
Bonjour, yes, now your audio is better.
All right, perfect. So yeah, over to you, Ankit. Let's take some audience questions. John, the session was amazing, and I'm sure that audience has tons of questions to ask to you, but due to shortage of time, I'm sure we'll pick 2 or 3. So over to you, Ankit.
Yeah, it is always lovely to listen to you, John, and your views about things. So while I was listening to your talk about the DPUs and the whole thing, and thinking back, since you might have a bit of experience over the different evolutions, so somehow philosophically speaking and thinking, I feel that from the days of mainframes, then coming down to personal computers, and then so you had a distributed system, and then you said, no, we can pack everything in one box, and then we split it out again into something disaggregated, and then we are trying to build it. So do you see that because of this, we might again offload a lot of things to the DPU, overload it, bloat it again, and then we might say, we need to split down the DPU right in the middle and have a different architecture again?
Yes, and the challenge, because there are so many challenges, right? For the many years, drives were the bottleneck. Then the network started to be the bottleneck. Then the OS was the bottleneck. It was not. And so with the evolution of the things, infrastructure, bottlenecks are moving. So we need to constantly adapt. I firmly believe that software has a lot of value. If you have software, it's programmable, it's not hard. I am in a processor company. When you design a processor, it takes 3 years. You think about it for 1 year or so. You design it 1 year, and you do the silicium 1 year. When it's done, it's done. You cannot change it. So if it's fixed, and if you have made a mistake, too late. Software you can adapt, you can fix, etc. So it's good to have that combination to give you more flexibility. So it's not just software defined, as many guys have said, hey, yes, software defined, we have that, so super flexible, etc. But we see clearly limits. Why? Because today the challenge is the data. Before, it was not so a challenge, because if you take an hypervisor, hyperconverge, it was not such a challenge because the network was the challenge. So you did not see the drive latency or the drive speed or lack of speed, right? Now you need to have that speed. So you need a fast drive, oh, you need a big network, oh, and you need software to treat it, and it's back and forth all again. So for the future, I think it's interesting to see what are the key components that I would need, and I would you may see that more and more. We name that composable architectures. So
Right.
you need first a fast network, low latency. So there are many initiatives. You may think about Ethernet, and you may think about evolution of PCI. Remember VXL, or remember the name of it. But the idea is I have components, hardware components. I need memory, I need a CPU, I need a GPU, I need a GPU, well categorized things because they do in their own area things. One will never fit all. You need flexibility. And what you're going to need, oh, okay, now I have this AI algorithm. This AI algorithm is really GPU intensive. I'm going to hook a bunch of memory, a bunch of GPUs, do my job. This new workload, it's not a GPU thing. It's just analytics. I need good x86 intelligence because it's a very smart and complex application. But I would need some offload. And perhaps you're going to hook an x86 DPU and combine them together. So what we are seeing more and more, but this is going to change dramatically a lot of things, is a combination of software, hardware components you can hook on the fly, and containers. Containers are coming. And when you think about containers, it's also a revolution because it's very flexible, highly parallelized. So yeah, I hope that massive parallelism will come back again, and that flexibility. I hope I answer your question, at least give you some ideas.
Yes. So there's one more question I would like to take because there are a couple of them, but then we are sort of short of time. So another question from the audience is that the DPU helps in improving the dollar per IO or the watts that energy consumed per IO. But how about the latency?
Very good question. So if I take a reference array, flash array, or flash array, NVMe based, average latency is over 100 microseconds, right? What we are doing here is below 20 microseconds. For TCP, we have about 40 microsecond latency. For Rocky, we have about 20 microsecond latency. And when the card is in the host, we are talking about 5 microsecond latency, because the big latency is about the network, TCP and Rocky. But when you are inside the card, it's just PCI, it goes super fast. So again, it's on a 10x in terms of latency, right? So we divide by 10 the latency. So the good thing, if you compare to iSCSI, nothing to see. Far more speed, far better latency. So you can say that now you have a protocol and a DPU that is taking care of all aspects of keeping the data, speed and latency. Yeah, we take care of that very seriously.
Sure, great. It was always great listening to you, and thank you this time as well. Mercy, over to you, Miri.
Thank you very much. Take care. Have a nice day.
You do. Bye-bye.
Thank you. Merci beaucoup. Thank you.
I always love how you take care of us. Thank you so much.
Yeah. All right. Okay. Thank you so much. And I think this was a wonderful session, full of information and full of valuable insights. I'm sure people have enjoyed it. People have enjoyed this. And as we could figure from the questions, a lot of people had a lot of queries. And thank you so much for addressing all the questions so patiently. All right. Okay. Without much further ado now, I'd like to move ahead So now let's move towards our next session, where we are going to address the Apache speaker, Cassandra integration for large-scale LiDAR point cloud analysis. And to throw some light on this, we have with us Professor Jaya Nair, the first and perhaps the only woman speaker in the symposium today, and it makes me so proud and immensely happy to invite her to the podium. She is the Associate Professor of IIT Bangalore, Visual Analytics Researcher and Expert. So warm welcome to you, ma'am. I hope you're here.
Thank you so much. Are you able to hear me?
Absolutely. How are you?
Yeah. I will. Thank you so much for the introduction. I will just share my screen right now.
Absolutely. Yes, your screen is visible now. Over to you, ma'am.
Yeah, thank you so much for having me here. And I see there's a big crowd here, and you have been on this for half a day now.
Almost
Today
200 people to be precise.
I know. I saw the crowd. It's very impressive. You guys are doing great. Yeah, so thank you again, and yeah, I have today. I'm Jaya Srivalsa Nair, and the work that I'm going to present today is actually by my MS student Satyendra Singh, and I'm really the voice for his work here, apart from advising him. So this particular talk is on Apache Spark Cassandra integration for large scale LiDAR point cloud analysis. Now, I'd like to confess upfront that I'm not a systems person. I work on visualization and data analysis. But when I got this invitation from Dr. Prashant Mishra to give a talk here, I thought a lot about, I don't want to be the odd man, odd person out. But then at the same time, I thought this is some, valuable work that we have here, that we have been able to use Apache Spark and Cassandra to build a visualization system to work with LiDAR point clouds, that I thought I should use this opportunity to give a shout out to the community, saying that, these tools are valuable. At the same time, I wanted to use this opportunity also to bring up this point that, of late, very recently, India, the government of India has opened up this policy to share data, geospatial data, with a larger crowd. And I'm part of IEEE GRS's community, so I thought I should use this forum to also say that, in this time when, these large-scale geospatial data sets are going to be available for the community, a community like this, as the data and storage community, the systems community here, can support this kind of work in the country, and this will be very valuable, in furthering the technology itself. Right? So that is sort of the background of my talk. So I'll first talk about how we have been able to use this technology for our work in processing LiDAR point clouds. So without much ado, I will start the slide show. Let me know. So if you're facing any issues hearing me or seeing the screen. Now this is what yeah. Thank you, Chenkappa, for your constant.
Absolutely fine. The screen and the audio both are fine.
It's hard to do this without that kind of support. So what we're going to talk about here is, so I work with spatial data sets. And one such data set that we work with is LiDAR point clouds. And this, what you're seeing here is, which looks like a pretty picture here, is actually a few 10 million points which are being rendered. Right? And these points, when I say points, these are three-dimensional points that with XYZ coordinates. This has been captured using airborne LiDAR systems. And airborne LiDAR is a technology by which it uses optics, as in the light is emitted from the sensor, and when it in very simple terms, when it strikes on an object, in the scene, it gets reflected back, and the time it takes to reflect back and the reflectance is used to capture the material that it has been incident on, and this gives us an idea about what kind of objects are there in a scene. Now, LiDAR, when it goes to the airborne LiDAR system, it captures very large geographical regions, and it is very useful to understand widespread, objects in a scene. So it could be urban regions, it could be regions for studying floods. It could be multiple things, right? And LiDAR plays a good role in terms of capturing three-dimensional information, unlike the image-based systems. So everything has a place, right? Now this 3D position helps us to reconstruct the data. As in, if you see a point cloud, you can actually reconstruct it from scratch. Now, what we are looking at here is it's a citywide LiDAR point cloud, which is of city of Surrey. This was captured and annotated by the University of Dayton, a lab in University of Dayton run by Professor Vijay Asari. And this is like the largest annotated airborne LiDAR data set that is available now. It was released last year, right? And if you look at it, this is these are the details of the point cloud itself. And this is a benchmark data, as in this is published to the public to be able to work with this kind of data set and make sense of it. Now, usually the thing that you want to do with LiDAR point clouds is to be able to reconstruct, like you want to build city models, etc. Right? Now, what we are seeing here is the first thing that, so this is an annotated data. So you already have labels for each point saying that which object it belongs to. It's a building or a road or vegetation, etc. But the idea now is we use these benchmark data sets to classify large scale points. And that's the part that I said about when you release, when you have the opportunity to share data sets, there's a lot of work that gets done in terms of building these training models, and which can be shared across with the community itself, and everybody benefits from that, right? So our goal now is to work with these kind of data sets. So there's a picture here to kind of indicate how this technology itself works. So there's a low-flying aircraft, and it carries a LiDAR sensor. Nowadays we have unmanned aerial vehicles doing similar things. But when you have these are the conventional data acquisition mode, right? Now modes. So what we see here is once this data is captured, you get just a bunch of points. And these points, because of the values that you have, this is GPS geo-reference, so you get the latitude, longitude, and the height of each point. Now with that, you can probably color based on height, and you can see a whole bunch of things. So this is a forest cover, and you can see that. But that is not enough, right? For you to be able to reconstruct the data and build city models and geological landscapes, this is not sufficient. You need to be able to classify each point semantically, saying that which object it belongs to, right? So this is what we really want to do. So this is how the data would it would initially look like. So if you have just the point and the reflectance value, this is all probably you can get. But what we want to get towards is this, right? As in, I'm able to pick each point and say what object it belongs to, and that's essentially what classification is. That is where we are going to use the machine learning models. Now, the problem that we are seeing here is, again, as I mentioned, so the more the data sets you have, the more models you trained, and if you can share them across, then this task becomes easy, right? But the thing is, as the technology is changing, the community itself is figuring out how to use, like for a very long time. In the recent, when I say long time, it's like the 5 years from now. I mean, 5 years ago from now, people were using random forest classifiers, and now people have started looking at CNNs to doing this kind of classification, right? Now, but this is like, it's a problem that everybody is sort of tackling with, because it's not sure as to how you would work with these kind of point clouds. And as I mentioned, when you have point clouds which span across really large geographical regions, what you really get is a very large, massive point cloud. And the DALES dataset that I have shown here and that I'm going to talk about here is not really the largest point cloud available either, right? When you look at the point clouds that are being collected from Dublin and Netherlands, and then you see that the point clouds are much, much bigger. It's just that we have the annotated data set, we just have this one, the largest one as of now, right? And so what are the challenges that we are looking at, that we are seeking solution from the systems community, right? We have really large scale point clouds, so large scale in the sense of millions and billions of points, and the actual storage requirement for the raw data is not, it's not a challenge anymore when you consider the memory systems that you have today. But the problem that we are currently facing is when you do start doing the computations, the intermediate results that need to get used for the training models, and the additional thing that we are interested in is also to doing visualization, is when interactive visualization is when the systems that we know of today start breaking, right? So you can't use them very effectively and efficiently anymore, right? So that's essentially what I mean by the first point, that the problem that you're facing essentially is with respect to scalability when it comes to really large massive point clouds, and the computational intermediate results that you need to store. The next part is now this data set is a real world environmental data set, and one cannot predict what kind of objects there are in a scene. Like we can have buildings with different kinds of materials, we can have roads and pavements and so on and so forth, right? So there's a lot of uncertainty in the data that comes in, because it's not a curated environment. One hasn't picked and chosen it and created the scene, right? So given that, when you look at the outdoor data sets, there's a lot of uncertainty in the data. And what we essentially do then is, if we have to work with these machine learning models, we have to capture the best features possible. So when we say we have to capture the best features, what essentially it means is we cannot work with just one set of features. If you understand the way ensemble methods work, we essentially do the same thing. We collect data from a certain local neighborhood of each point, and then we expand the neighborhood. We collect it for several neighborhoods. So what it means is, for a single point, if I need to use only 21 features in a random forest classifier, the number of features I actually have to generate is of the order of 21 times 100, because I have to capture it for, say, 100 scales, so that I can see which is the best set of features that can even go into the classifier. So what we're seeing here is, we have these features that we compute, and then we have to also do a selection of those features. So all of these require computations. So the feature extraction itself uses eigenvalue decomposition, which is a nonlinear process. Now, and then on top of it, we also have to compute the entropy, and then do a comparison, right? Ranking of the entropy to see which are the features that we have to keep, right? So there are several of these compute intensive processing that happens here, right? So which is why we need a system which allows us to do large scale computations, right? And the final thing is visual analytics, right? So visual analytics is where essentially a data science workflow, where once it's not just that you visualize the data set, right? Like what I just showed you is just an image, but you should be able to interact with it, play around with the tool, and also visual analytics is a new thing where it's actually not new. It's been around for 15-20 years now. The idea there is that the user can play around with the data, explore the data, and then change the data set itself that you want to work with, and then continue using the visualization tool as long as you want to explore all aspects of the data. So what that opens up is you're not just looking at the raw data and its characteristics alone. So I can even like run the random forest classifier and progressively visualize what the results of the classifier is as I pick any tile in the data set and then visualize them and so on and so forth. So the feature that are required in a single visualization system when you work with these kind of data sets and wanting to do a large number of analysis is essentially that you need a memory system, which is a persistent memory system that will allow you to do that. So what I have just said is from the first point is, okay, the scalability is given. It's a no-brainer. But the other part is we need a compute-intensive system and a persistent memory system to sort of get married together and integrated together so that we can use that for the purpose that we are looking at. So this is sort of the background of what we want to do. Now, this particular visualization system is for large-scale 3D, three-dimensional point clouds, and it's called Pottery. It's open source. It's open source. And the way Pottery works is, so for you to be able to render these many points, it's a hard problem, and these are browser-based tools. As in, you have to be able to load these points on the browser and be able to work with them. So what they do is they do something very intelligent. They subsample, right? And because that way you can reduce the number of points, give the same effect. You don't have to render all the points. But the problem then comes is like you lose a lot of information, right? When you want to do if it's just an visualization, you can do that because you just need the gist of the information about the data. But when you want to analyze, say, if I want to pick a point and say, this is not the feature set that is good enough for machine learning model, I need to change this this feature set for a region of points. I want to do these kind of activities, then sampling them will not work, right? So what we are looking at is, so this uses very robust sampling technique like Poisson disk sampling and so on. So it works very well, but the problem is it does not fit well with the thing where we want to interactively choose say what kind of features to use for and what kind of machine learning model to use for our classification, right? So that is where this falls short of, right? So what when I said that we have to compute multi-scale features, what I mean is for each point, the way it works is I work around its neighborhood, and I find its neighboring points, and the shape of that neighborhood of points is what is going to tell me, is going to give me the information about the class that point belongs to. So computing that shape is essentially what you would do when you do principal component analysis or eigenvalue decomposition. You have to essentially compute those eigenvalues there, right? So that is the scale of the computation that we have to do here, right? And once we do that, as I mentioned, this is one of the seminal works where they said that once you find these different scales, you still can't use all these scales for the final classification. So you want to be able to pick the optimal scale, and the way to pick the optimal scale is to be able to compute the Shannon entropy at each point using these eigenvalue features, and then find the local minimum of that Shannon entropy, local or global minimum, right? Depending on your application, you need to be able to change that as well, right? So what we're looking at is we need this tool which with a lot of human intervention, you want to be able to decide a certain set of characteristics that will enable further analysis, right? So one can do an automated analysis, improve on the thing, but the kind of tool that we are looking for is where we want to do a lot of trial and error and be able to improve on the classification that the models that we want to create, right? So this is essentially the sum total of the problem statement that I just mentioned in gory detail. So we need to be able to have all these things going on. Like we need to be able to normalize point clouds, partition them. If you're using a distributed system, it has to have a proper partitioning where it's not just randomly partitioned, but it also is locality preserving, right? So that we find the local neighborhoods to finding the features. It has to be able to do the neighborhood search, feature extraction, run the ML model, the classification, and the visualization engine. And the central to all of this is the storage system that will allow us to manage these large-scale data sets and then move them around as required in with low latency, with low network latency, and so on and so forth, right? So because we are talking about cloud computing systems here, right? So the solution that we sort of narrowed down or pinned down was using Apache Spark and Cassandra, and integrating them, because Apache Spark is good for the compute intensive aspect of the problem statement, and Cassandra will provide the persistent memory for doing both the compute system and also to be able to support external visualization subsystems, which will allow us to do browser-based, which will allow us to create browser-based tools and run them, right? So that's the idea here. So why these? So Apache Spark itself is optimized for general execution graphs with support for high-level languages like Java, Scala, Python now, so that you can run a lot of the recent Python machine learning packages and all that. And it also has Spark SQL and so on and so forth, right? And for the data set that we work with, actually, and Spark also supports in-memory computation. So we could have loaded the data in Spark itself. We didn't require the persistent memory aspect of it, right? But then when we started looking at the visualization tool design and development, we realized that this is going to fall short, because the way we want to do is we need to be able to allow the user to tile the data and look at sub-regions and then inspect points in those regions and be able to retrieve the machine learning model results and be able to create statistical analysis of the region that has been loaded and do it on the fly. And the key point with the visualization tools is nobody is going to wait around, so you need interactive tools, right? So as soon as you give it an input, as in the user commands, it should be able to retrieve and show you the graphical rendering as well, right? So, so then it came into play that, okay, whatever persistent memory systems that Spark has support with, that it has connector support with, we should use one of those, and Cassandra was one of the top choices there. So we use the persistent storage in Cassandra for two things. One is storage for processed data in offline applications such as visualization, and distributed data management when there are multiple partitions in a single node. So this is how we have set up the system. So essentially the Spark component itself looks like this. So we have a Spark application and a driver program in the Spark session, and the cluster manager manages the partitioning of the data, and it's sent to different worker nodes. And this is essentially, these are the executor nodes. Now, what essentially Cassandra does is, so we partition, as we mentioned, we don't want the default data partitioning that is available. We want to be able to partition the data in a way that the locality is preserved to a large extent, because we don't want to be doing a lot of search operations using communication across the nodes to find neighbors, right? So for finding the local neighborhood to compute the features, we need to be able to do that. So what we essentially said is, what is the kind of spatial partitioning we'll do in the data, and how those would be loaded onto the Cassandra nodes, and this will manage the rest of the application that we want to work with. So we essentially have the entire system like this. All of it is running on the AWS. We have the master nodes which run the Spark, and the cluster manager. and Cassandra nodes are within each of the Spark worker nodes themselves, and this is how our system is set up. The system specifications itself is we have used Apache Spark 2.4 and Spark ML Live, which is what we want for machine learning algorithms, and we have integrated it with Cassandra 3.0. We have 1 master node and 5 executor nodes in Apache Spark, and this is essentially the details of the system that we are using. Now, this is essentially the workflow that we are doing. We have this to be so we have a 3-stage process where
just a kind request. The time is up, so if, we can wrap it up
in next 2 minutes.
Yeah, that's okay. All right. Thank you so much.
Yeah. So yeah. So these are the different stages we have. So as I mentioned, it's not just the system requirements and that system integration that we had to do, but we also have to ensure that we do the data partitioning and in a way that it seamlessly works with the system. So we have, once we load the data on the Spark and integrate it with Cassandra, we have to do 2 things. One is to do hook it up with the machine learning models, and also be able to use our visualization subsystem to access both the raw data as well as the process data that comes from the machine learning models. So this is how our visualization system itself looks. So you can see that we can load the data set and visualize the points, but at the same time, we also allow the users to select data. So the magenta box that you see here is for us to move things around and then be able to capture some of the points. And this gives us, this allows us to do on-the-fly plots for statistical analysis of the features that are present there, as well as the features of the raw data itself. So we can do all of that. And also we allow the users to look at, to inspect the random forest results, the ground truth, and any other classifier model that we are looking at. So all of these need to be persistent in the memory. So this is essentially what we allow users to do with the tool that we have. So this is just a partitioning system, but essentially what we want to be able to do is tile the data, retrieve some regions, and then be able to visualize them, use the multi-scale features across all scales, allow them to look at the classification. And as the classification goes along, we see that progressively the class labels get populated and the visualization itself gets updated. So this has to happen in a real-time basis. And these are the results for the classifiers that we have been able to use, and the amount of the number of features that we have worked with is actually a subset of the features that is considered the best optimal for the classification. We used only 11 out of the 21 that is required to get the best classification, and still we have gotten really pretty decent results, right? So in conclusion, what I want to say is that this work would not have happened if not for the integrated system that we have been able to design. And as such, we don't work on the system side, but we are the beneficiaries of that kind of system that is put out by this community. And as a last note, this work has been supported by the grant that I had with SERB. So yeah, that's all I have for today. I'll be happy to take questions. Thank you.
Thank you so much. Thank you so much for joining in. Thank you so much for sharing such wonderful insights. I think we all thoroughly enjoyed your session. And we have lots of questions for you now. And I would like Ankit to come in for the Q&A. And let's take a couple of questions from the audience.
Sure.
All right. So thank you so much, Professor Jaya. And it was really insightful to hear from a user's point of view. So we have been designing systems, but then oftentimes we miss the view of how people are using it. So we were actually having a couple of questions here. So one of the questions from the audience is, how do you ensure when you do the data partitioning that much of the data is resident on the same node? That is, if you have a spillover, you might actually touch upon or stump upon each other's data. So how do you do the partitioning, making sure that that doesn't happen?
Right. So the partitioning was the trickiest part actually. So what we had done initially was, which I didn't cover here, is we had buffer regions, as in we had these ghost regions which were loaded so that the neighborhood of the points were present in the same node, and then we took this thing where those points are not used for analysis, but they are there just for providing the neighborhood so that we reduce the communication latency. But then later we decided to capture the error if we were not doing the buffer regions, because there is this added thing where it requires extra storage if we are storing these extra points but not using them for the analysis part. So then we looked at what is the error that we would get if we were not to use these buffer regions. And then we realized that the error is, we took a trade-off, right? So there's a trade-off in the error. So that said, so that our communication latency is completely zero, mostly zero when it comes to neighborhood search then, right? But that is not an optimal solution. As in, we need to be able to work with different kinds of spatial partitioning that can be that will allow us to use its neighborhood in complete, in its completeness. And the other part that we also did is what actually allowed us to do this trade-off is this multi-scale method, where we are using multiple scales to capture information. So what I'm trying to say is, when we partition the data by keeping the data set, by preserving the locality of the data set, what we essentially see is that if I want a cube of the neighborhood, I'm just using half the cube now. So and it is, and if I do it for enough number of scales, we end up capturing enough information there. But but we have had to play around with the spatial partitioning, and
Sure.
that's still an open question, as in we can try out more things there. Yeah.
Sure. So I had a couple of more questions, like on the lines of how do you have an automatic selection of data points and things, but actually we are sort of running short on time. So we will post the questions across to you and have the answers go back to the audience. Thank you so much, Professor.
Yeah, thank you so much for having me here. Thank you very much. Bye.
Thank you so much. It's a pleasure to have you here. I think this was indeed another great session, and I hope the audience and all the participants today are enjoying in. Once again, it's time for all of you to tell me whether you are here, whether you are present, how many of you have eaten. Just give me a raise of hands, either by show of hands or by the clap emoji. Can we quickly get you back? Come on, guys. Once again. Yes. Now I can feel some turbulence here in the energy. Amazing. Wow. That's the vibe of the room. Great. Super. So good. I hope you guys are enjoying the sessions, and I hope you all have actually learned throughout, there has been so much information pouring in throughout the day. And let me tell you, please stick around, because we have a special speaker for all you guys, somebody who's joining us from across different time zones, from across the world, and he'll be specially here for all of us, so stick around. But before that, let me quickly introduce you all to our next session. And before I do that, actually, this also reminds me that we still have our trivia session to go, guys. So please stick around, buck up, boost in yourself, have your coffee, have your lunch, because the trivia, the first person to answer the trivia questions will get the voucher. As I've already mentioned, worth ₹1,000 INR. So please, guys, please just stay around, and I'm looking forward towards the trivia round as well. Well, moving ahead now, it's time to circle back to the lightning talk and once again bring back our researchers and technology enthusiasts who will be talking about leveraging different ISAs and operating systems for designing applications, and of course the ELF Store, a resilient data storage service. So amazing topics coming up. Stay tuned, and over to you, Chingappa sir. Let's have the slides now.
Hello everyone, this is Shubhankar Suman Singh. I am a PhD research scholar in the Computer Science and Engineering Department at IIT Delhi. I am supervised by Dr. Smriti Ranjan Sarangi. I will be presenting my work on the topic ISA mod, which is a tool for designing application-specific instruction set processor by comparing different instruction set architectures. Here is an outline of the talk. I will give an introduction of our problem statement. Then I will discuss the motivation and related work. Next, I would explain the various components of our tool ISA mod. Finally, I will discuss the results followed by conclusion. Designing the ISA is a very critical activity in the entire ASIC design process. There is a long history of using automated tools that suggest custom instructions based on an analysis of the data flow graphs of target program. Such approaches often create an ISA that is over-specialized for a small set of applications, and they often suggest a plethora of custom instructions that cannot be practically implemented. In this paper, we focus on modern applications where we only need to add a few instructions to an existing ISA such as RISC-V. The aim is to either supplant or complement the extensive manual analysis that goes into such decision making. We discuss the motivation now. Generation of custom instruction sets for processors that are tailored for a particular class of applications is a classical problem in EDA and embedded systems. This is a rather old problem which saw its heyday roughly a decade ago. During this period, hundreds of ideas were proposed for automatically identifying instructions from the DFG of the program's execution. The first phase was subgraph enumeration, where all candidate subgraphs of the DFG were enumerated. The idea is to replace a candidate subgraph with a single instruction. The next step was subgraph selection, where a subset of enumerated subgraphs were selected and replaced with custom instructions. The reason that we revisit this problem now is primarily because the interest in ISA extension has been rekindled based on some recent developments. The biggest driver of this new trend is the advent of freely usable instruction sets such as the RISC-V ISA that have explicit support for introducing a few custom instructions. Coupled with the fact that it is getting easier and cheaper for fabless companies to create their own cores and SoCs based on RISC-V, this has spawned a flurry of activity in identifying a few custom instructions for specific classes of applications. We show a motivating example where we compare the performance of different ISAs for the same architecture using the Spec 2017 benchmarks. x86 is the best performer for 5 out of 6 benchmarks. Now we discuss the ISA mod tool. We want to find the effects of the ISA on performance for a given application, but the performance of a particular ISA is tightly coupled with its underlying microarchitecture if we use a real system. Other works have normalized the performance values based on the core frequency, but there are many architectural parameters apart from the ISA in which the performance depends. Hence, to ensure a fair comparison, we use a simulation framework where we use the same RISC microarchitecture for conducting experiments for all the 3 ISAs. Now, we discuss the ISA mod tool. It consists of the following components. We start with an application that is compiled for the different ISAs. The first step is to generate instruction traces for the same application for different ISAs. We use QEMU-trace, an extension of QEMU, to generate x86 and ARM instruction traces, and use Spike to generate RISC-V instruction traces. We then simulate these traces using the Tejas simulator to generate the architectural statistics. The next step is statistics analyzer. We mark equivalent phases across the different traces by marking the start and end of a particular function call. We generate this information from the program counters. The tool analyzes the most frequently executed functions and checks for performance differences across the different ISAs. Finally, it prints the sequences of instructions executed in these functions which are sent to the image generator. The ISA mod tool displays the comparison results in 2 views. In view 1, we show the performance and architectural parameters using Circos plots,
and show the instruction sequences using a raster diagrams in view 2. Finally, we apply manual analysis for custom instruction selection for the ASIP design. We first show the performance and architectural parameters in view 1 using a Sarkos plot. For each concentric circular ring, the range of the radial axis is from 0 to 1. A point on a concentric ring of each plot shows the corresponding value for a set of 250 consecutive instructions. The complete circle corresponds to a total of 200,000 instructions to be viewed in clockwise order starting from the top. We show the relationship between performance and different architectural parameters such as L1, L2, and branch prediction hit rates. We create images for the most frequently executed functions using instruction traces for all the 3 ISAs. We start by mapping each micro operation to a particular color and then create a 2D raster diagram representing the sequence of instructions horizontally from left to right and vertically from top to bottom. We then define the following patterns for these images to help find the reasons for differences in performance. Horizontal stride. The horizontal stride represents the loop size. A smaller value is better. Vertical stride. The vertical stride represents the loop count, number of iterations. It is relevant when we consider nested loops. Slope. The slope of a particular color pattern can also be used to compute the loop size. And finally, color composition. We have mapped darker colors to high latency operations such as loads, stores, and floating point operations, whereas we have mapped the low latency operations to lighter colors. Hence, it is very easy to visually identify which image is associated with a better performance. Now we discuss our results. We compare our results with the state-of-the-art in custom instruction generation, Fageci. We applied their algorithm of custom instruction enumeration and selection on the Spec 2017 suite compiled for the RISC-V ISA. We set the number of inputs to 2 and the number of outputs to 1 for the custom instructions for their algorithm. From the table, we can see that Fageci enumerates 215 to 301 instructions and finally selects 31 to 53 new instructions. In comparison, ISA mod provides only 1 to 10 instructions. The output is thus much easier to analyze and understand. In this graph, we show the improvements in the RISC-V core upon introduction of application-specific instructions obtained from Fageci and ISA mod. We observe a maximum performance difference of 4% in case of the Leela benchmark. The average gains for Fageci and ISA mod are 17.75% and 16.5% respectively. The results are comparable. Our tool's benefit is that we provide fewer new instructions 5 to 40 times and a visualization engine to analyze the new instructions and explain the performance differences. In conclusion, we presented our tool ISA mod where we introduced novel visualization techniques for designing ASIPs. Our set of increasingly complex diagrams filter out all unnecessary details and show us all the information that is required to identify the key reasons behind the performance differences. The Sarkos plots captures microarchitecture details and the raster diagrams capture code patterns. We increase the performance of RISC-V by 10 to 28% just by adding 2 to 10 new instructions. The performance gain is comparable with the state-of-the-art in custom instruction generation. We at the same time reduce the number of suggestions made by the custom ISA generators by 5 to 40 times. I thank you for listening to my presentation. I will be happy to answer your questions.
All right. Thank you so much. And next up we have Prashanti SK. Can we please have a slide on?
Hi everyone.
Over to you, Prashanti.
PhD student with Professor Yogesh Suman at the Dream Lab IISc. Today, I'll be giving a brief talk on LStore, which is a distributed data storage service across the edge and the fog. LStore is an ongoing work in our lab, and there has been a previous publication at ICWS, which you could look up if you're interested. So through this talk, I'll be trying to address some of the key challenges and future research directions in edge storage. So with the growth of IoT, we see a wide variety of applications, right from smart cities to autonomous vehicles. And all of these involve using a lot of sensors and compute devices in the field. As a result, edge has evolved as a computing paradigm. Previously, it used to serve as a transition point for just moving data to the cloud, but now it's being used for compute itself. Additionally, we also have fog devices, which are more powerful in terms of compute and capacity, and these also play a role in the compute paradigm. But the gap exists in edge storage itself. So while things like application deployment, scheduling, and orchestration are well studied, not much work has been done on using edge devices for storage. So there's no distributed file system kind of view, something similar to what HDFS gives us. And a limited work exists related to edge storage, but they assume that edge devices are similar to workstations and use big data platforms. So this is where LStore makes its key contributions. And LStore is basically an edge local federated store. And it provides block-based storage exclusively on the edge. And we have various operations such as search, put, and get on blocks. And we use federated and probabilistic indexes, which we will get to in a bit. A key thing to remember here is that edge devices are inherently unreliable, but LStore provides reliable data management by offloading reliability onto the software layer. And we also use approximate statistics in doing this. And fog is used more for coordination and providing the service API for storage. Moving on to the architecture and data model. So you can think of the edge as a Raspberry Pi and the fog as a workstation. So edge is used to store the block data itself, whereas fog coordinates operations and exposes the storage service API. So we have this notion of blocks and streams where you can imagine them to logically be analogous to files and directories. And these streams and blocks also have properties. And one of the unique things about LStore is that it has capabilities to search over these properties or metadata. So the operations that LStore supports are create stream, put block, get block, update, and find on a stream or block. So coming to the architecture and how devices are organized. So we use what is called a super peer overlay, which is inspired by peer-to-peer systems, but has differences from them. So the circular things are fogs in this picture, and the squares are edges. So edges are partitioned among fogs, and every fog is responsible for a certain set of edges, and it's termed as a parent fog. And this together is called a fog partition. And between fogs, you have the notion of neighbors and buddies. So every fog has a few neighbors. For instance, 9 has 10, 11, and 12 as neighbors, and it also has 1 and 5 as buddies. So this is our two-level super peer overlay in a network, and we'll see shortly how organizing devices into this sort of a network helps us achieve better results in search. So for health monitoring, every parent fog is responsible for its edge devices and tracks it through heartbeats. Similarly, fogs also interact with their neighbors and buddies, and this is both for monitoring and sharing statistics. Coming to federated indexes, we have two major concepts here. One is called a local index. Every fog maintains this, and it has information about what is stored on all the edges belonging to this fog. And the other is the bloom filters, which every fog sends to its neighbors, which is called a neighbor bloom filter. Similarly, every fog also sends a buddy bloom filter to all of its buddies. And this is called a buddy bloom filter. The difference is that the buddy bloom filter not only has information about that fog, but also its neighbors, essentially a buddy and the buddy's neighbors. And why this is useful is it helps us perform search in 2 hops. For instance, if you start at fog 1, you first check in the local index if you can find whatever you're looking for. If not, then you check the neighbor bloom filters, which is 2, 3, and 4, to see if any of these have what you're looking for. If not, then you look at the buddy bloom filters, which is basically 9 and 5, and that will tell you if either 9, 10, 11, 12 has it, or 5, 6, 7, 8 has it. So overall, we require only 2 hops, and this is an improvement over existing peer-to-peer systems where search takes logarithmic number of hops. One important thing to note here is that local indexes give exact results, whereas Bloom filters are probabilistic, so you could get false positives from them. So they are sort of an approximate search mechanism. But despite that, search takes an overall 2 hops. Coming to reliability, as I said, edge devices are inherently unreliable, but LSTOR uses what's called differential replication. Basically, the replication factor is decided by a combination of 2 things. One is the rated reliability of the edges, and second is the required reliability for a particular block. Depending on this, we select Q edge devices for replication such that you get the desired reliability. And one thing to note here is that the number of replicas is kept within a band, as in there's an upper bound and a lower bound, so that it doesn't become arbitrarily large or small. Coming to approximate statistics, again, this helps every fog form an independent global view of the system. So how this is done as follows. The figure that you see on the top right, basically every fog does that locally. So it on the x-axis is storage and on the y-axis is reliability. And you have min, median, and max on both the axes. And every fog partitions or puts its edge into the appropriate quadrant. So there are 4 quadrants, and then it counts the number of edges in each quadrant. Now, all of this information can be compactly packed into this 10 tuple that you see below. Basically 3 values for reliability, 3 values for storage, and 4 values indicating the counts in each quadrant. And every fog broadcasts this 10 tuple through our 2 layers super peer network. And using this 10 tuple that every fog gets from other fogs, it can independently form a global view of the entire system, which is what you see in this figure. Again, this is approximate because we're not sending exact data about an edge's reliability or storage, but that's what enables LSTOR to be so scalable and performant. Basically, because you're sending approximate statistics, and this helps with performance. And so continuing with what approximate statistics helps in, so when you select devices for replication, basically a client does a put on a particular fog, and the fog examines this global matrix that we saw before to incrementally select Q devices such that the reliability is met. Moving on to recovery, because edges can fail anytime, the parent fog detects a failure and triggers re-replication. So recovery is very similar to put, except that you first do a get to obtain one surviving block, and then you find a device with reliability similar to the edge that died, and you put the block onto that. And we also allow for concurrent updates through leasing mechanisms and locking streams. So coming to the setup and results, we perform detailed experiments on put, get, find, and recovery. But due to time constraints, I'll only be going through the put results here. You can go through the rest of them in the paper if you're interested. So we use an in-house virtual environment called Violet to validate LSTOR. And we have 2 setups, the D20 and the D272. So the number after the D indicates the number of devices in the setup. For instance, 272 indicates that there are 272 devices, which is basically 16 fogs with 16 edges each. So moving on to the experiments itself. So on the y-axis, you have the number of edges or the number of writers, and the blue violins indicate end-to-end time, and the red violins indicate replica count. And the left partition is on the D20 setup, and the right partition is on the D272. Now, looking at the results, so on the D20, for one edge, we see that median time is around 3.8 seconds. And with 4 edges, it goes slightly up to 4.5. And then there's a sudden jump at 16. So this is because bandwidth becomes a bottleneck here. If you remember, this D20 has a total of 16 edges, and here all of these edges are actively putting blocks. So this causes bandwidth to become a bottleneck, and that's why the number goes up. Whereas if you look at D272, from 16 edges to 64 edges, the time just goes up from 2.5 to 2.9, which shows that LSTOR scales fairly well and that the system overheads are pretty low. And if you look at the replica count, you can see differential replication coming into play. Basically, for D20, you see that the median number of replicas is 3, whereas for D272, it's higher, it's at 4. So this is because D20 has a higher reliability compared to D272. Therefore, this will need lower number of replicas, and this would need higher number of replicas. And yeah, so the key takeaways from this, LSTOR is the first of its kind distributed edge storage system. And we use edge as a first-class storage entity and fog for coordination. Other novel things about this work are federated indexes and approximate statistics. Both of these help LSTOR scale well without losing out on performance. And our empirical results corroborate this and show that we have very low system overheads. So moving on to future work, consistency is a major aspect that we're looking into. So native LStore supports monotonic writes, and we are trying to support various other consistency models in a tunable or adaptive fashion. Other things that we're looking at is to have provisions for fog recovery, to use fog as a storage layer, and so on. So that's all I had. If you have questions for me, please ask them during the Q&A, and you can also write to us at this email ID. Thank you.
Thank you so much, Prasanthi. This was wonderful. It's just that we are a little behind schedule, so we'll circle back to your Q&A after a couple of minutes because we have one more speaker in the house. So please stick around. We have received multiple queries and questions for you. Just stay here and we'll get back to you. And also the other two speakers who presented in the lightning talk, please stick around. We'll just circle back to you in some time. For now, it gives me immense pleasure to introduce you all to our next session. And as promised, this is the much awaited session. So all you guys who have stuck throughout the day, I hope you guys have enjoyed all the sessions that were planned for you, all the people that came in from different walks of life, from different parts of the world. And now we have one more speaker, a surprise entry for all you guys. Although I'm sure you already know about this and you guys have been waiting for this. So let me quickly introduce you to our next speaker, our chief guest for the symposium, someone who is also an IEEE fellow, professor of computer science at ETH Zurich, none other than Professor Onur Mutlu. His broad research interests are in computer architecture, system hardware security, and bioinformatics. Professor Onur has also received several prestigious awards, including IEEE High Performance Computer Architecture Test of the Time and IEEE Computer Society Edward J. McCluskey Technical Achievement Award. And of course, it's our absolute true honor to listen to his thoughts on the intelligent architecture for intelligent systems. He's joining us today all the way from Zurich, and it gives me immense pleasure to welcome you here, sir. Are you here with us?
Oh, Minnie, can you hear me?
Absolutely. How are you?
Good, good. How are you?
Amazing. We are really looking forward towards your session, and I hope you have received the enabling rights to share your screen.
Okay, let me check that quickly. Okay, I think I have. Let me also do this. I don't know if this works. Okay.
Yeah, it's working. It's absolutely working. We can see your presentation. So
Okay,
it's
great.
an honor, sir. Really looking forward towards this session. Over to
Okay,
you
yeah.
now.
Yeah, thank you very much for your introduction, and thank you very much for accommodating the timing that changed. Well, there was a confusion in terms of the timing due to the
But
due to a
perhaps
mistake on my part.
due to the different time zones as well.
Exactly, yeah. But hopefully this will go well. So yeah, it's a great.
We are looking forward eagerly.
Okay, great. Should I get started?
Over to you. Absolutely.
Okay, excellent then. Okay, thanks for inviting me to give a talk in this conference. I unfortunately I missed a lot of the conference because it was night during my time frame, but hopefully you will enjoy this talk. So I'm going to talk about intelligent architectures for intelligent machines, which is along the lines of the topic of this conference quite a bit. We're going to mainly talk about memory and storage, essentially data. And I think I have 45 minutes, so if I go over, please let me know, because I have material to talk about for days and days. But we're going to talk about computing.
Just try. So the time limit for today is 30 minutes, 25 minutes for the speaker session, and we are trying to keep 5 minutes for the audience questions because I'm sure audience will have tons of questions after this session.
Okay, sounds good. Yeah. So okay, so I will start then. So we're going to talk about intelligent architectures for intelligent machines, and the problem is that today's computing systems are very much limited by data, bottlenecked by data. And data is key for many applications. AI, ML, genomics, important workloads are all data intensive. They require rapid and efficient processing of large amounts of data, and data is increasing on top of this. We can generate much more data than we can process. And data is key for many workloads. These are some workloads that we're used to. They're going to become even more data intensive. It becomes a performance energy bottleneck. These are some mobile end workloads, less server workloads, but they're equally and maybe more so data intensive. In fact, we're exercising some of these workloads right now as we do remote calls. And data is performance energy bottleneck in these workloads. And some future workloads are going to be more data intensive. This is genome analysis. Today, we can sequence genomes much faster than we can analyze them. We have many potential analyses that we can do on genomes. And this is becoming much more powerful because genome sequencing devices are becoming much more powerful. You can see that they're becoming less costly. And this is clearly very important, especially as we are seeing with the COVID-19 outbreak. But there are many applications in terms of health and scientific discovery of life, etc. Basically, today, we're bottlenecked by the data that we can produce. We're unable to analyze it efficiently and at high performance. And I'm not going to talk about this in detail, but this is clearly an important application. And we do some work in this area, understanding how we can make genomics much more efficient and much higher performance. And today we have devices that look like this, that can fit into your hand. You can buy with relatively low cost compared to other devices in the past. And you can sequence a lot of things, but then processing of the data and analysis becomes a huge bottleneck because this device is not able to process data locally. So you have to send the data that you produce all the way to data centers somewhere. And it takes a long time to process the data because I don't think we have good principles to actually operate on the data where it resides today. And this is just one example of a potential future platform we can build if we can actually rethink how we design the computing systems so that we make data less of a bottleneck than today. So if you're interested in genome analysis, we have written a lot of articles on it, and this is a more recent survey article that we wrote at IEEE Micro. I would invite you to take a look at it. And we also write papers where we actually do specialized designs, hardware, software, co-designs that can accelerate genome sequence analysis, in this case, approximate string matching, which is at the core of genome sequence analysis. So in the future, I think this problem is going to be even more important for many reasons, health reasons, medical reasons, as well as scientific reasons. And we're going to have more edge devices like this, and we will need to have much more efficient methods of computing on this data. And if you're interested more in this, we have lectures about also. Sorry, I hear an echo. Is there a question or? Okay, I hope it's not on my end. But we give lectures, so you can take a look at the lectures if you're interested in these. And these slides will be available if there's a I'm happy to send it to the conference organizers, but I also put them on my website. Okay, so hopefully this gives you an example of many applications requiring a lot of data. And data, in the end, overwhelms modern machines. It overwhelms the storage and memory capability, communication capability, and computation capability. It greatly impacts robustness, energy, performance, and cost. And when you look at a computing systems from a first principles perspective, we have fundamentally three key components: computation, communication, and storage. And we have heavily optimized the computing unit. Everything else is there just serving the computing unit, moving and storing data. And as a result, we have systems that are overwhelmingly imbalanced. We have systems that look like this. This is my cartoonish picture, of course, but if you look at any die photo today, most of the system is really dedicated to elements that move and store data: caches, interconnects, other caches, other interconnects, memory controllers, other caches, other interconnects, shared memory, interconnects, storage. So more than 90%, 95% of the entire system of a single node is designed to move and store data and not compute. So we call these computing devices, but they're really not computing most of the time. They're most of the resources dedicated to moving and storing data. So we'll come back to this. We'll try to fix this problem. This is there because we have a processor-centric design paradigm in our systems today. Okay, so as a result, we have data coming up as a performance energy bottleneck and overwhelming our machines. And this is one example we will get back to, but we did the study with Google a few years ago where we found out that more than 60% of the total system energy is spent on data movement on important applications that I showed you in this particular slide, including machine learning, web browsing, video playback, and capture. Okay, so I will start with this axiom, basically. I will say we want to design intelligent architectures for the future because these architectures, these platforms are going to make decisions for us going into the future. And they have to be intelligent. And I believe that intelligent architecture has to handle data well. I'm not going to question this from now on. And of course, the question becomes now, how do you handle data well, right? And I'm going to give you three different directions that are complementary to each other. And I believe they should be done together. But we're going to focus on one particular direction for the purpose of this talk, since we don't have a long amount of time. But basically, we need to ensure that data does not overwhelm the components that we design via intelligent algorithms, via intelligent architectures, and via intelligent whole system designs, algorithms, architectures, devices all together. I'm going to especially focus on this part. We also want to take advantage of vast amounts of data and metadata flowing through the system to improve our decisions over time. So a good system learns from past behavior. And I believe as humans, we are learning. We have a lot more to learn, of course. We can do better. But if you look at the systems we design, computing systems, they don't really learn, at least at the very core of them, hardware, for example. For example, we design the memory controllers and storage controllers. They don't really adapt their decisions to the workloads over time based on what they've learned. They don't change their scheduling policy, power management policy, etc. So we need to have more intelligent systems that take advantage of data, more data-driven architectures. I'm not going to talk about this as much. I'm going to briefly mention it in the next slide as well, but I'll direct you to some lectures that you can watch if you're interested. And the third perspective is we want to understand and exploit properties of different data so that we can customize our algorithms and architectures to different types of data and different properties of data. Some data is very important for security, for example. Some data is not very important for security. Some data is very important for error tolerance. Some data is not that important. If we can somehow distinguish these different types of data, we can make much better decisions and optimize our systems much better. So architectures today, based on these three directions, are not doing well, basically. They're not doing well, dealing well with the data because they're processor-centric as opposed to data-centric. They're mainly moving and storing data, and very little amount of time and real estate is spent on computation. We're going to focus on this a lot in this talk. They're also not good at taking advantage of vast amounts of data and metadata available to them over time. My cell phone, for example, is still using the same algorithm it is using to schedule memory operations, for example, and it hasn't learned anything over the course of 6 years as it has seen workloads. It hasn't customized itself to me or the workloads. And I think this is a big problem with an intelligent architecture. So that's why I don't consider existing architectures intelligent, because they make human-driven decisions as opposed to data-driven decisions. They don't learn from their mistakes. And the third is our architectures today are not do not know or exploit different properties of application data, because they're designed to treat all data the same, because the characteristics do not get communicated well from the higher levels, from the semantic levels to the hardware in the system. As a result, architectures make component-aware decisions as opposed to data-aware decisions. They cannot adapt the decisions to the properties of the data. Again, I'm not going to talk about data-driven and data-aware aspects of architecture design much in this talk, but they're as important, if not more important than data-centric. I believe they're all together very important, but we're going to focus on data-centric purely because of time reasons. Okay, so let's jump into data-centric or memory-centric architectures. I also call this as processing data where it makes sense. Essentially, if you think about data-centric architectures, there should be multiple properties. We're going to focus especially on the first one, processing data where it resides, where it makes sense, as opposed to moving data far away from the processing units into the processing units that are far away. But we also want low latency and low energy data access, low cost data storage and processing, and intelligent data management. I'll touch upon intelligent data management a little bit to motivate processing data where it resides. Okay, let's jump into it. I call it processing data where it makes sense. The basic idea is data is stored in data storage units, whatever they are, tape, SSDs, hard disks, memory, caches. We're moving data to accelerators and processors that are far away from them today. Can we actually do better? Can we actually process data where it resides, where it's generated, where it's stored? And this is not a new idea. This is an old idea, actually. Early incarnations of it go back to in-memory processing, like logic in-memory computer that I show you over here. It's as early as 1960s. But today may be the time where we really actually take this idea finally serious and make it commercial and change the paradigm of computing in all of our systems going into the future. Why is today the time? I think we have a huge problem with technology today because memory technologies that we have designed are having a lot of problems, and maybe we can make use of them in a better ways. I'm going to talk about that to motivate a little bit. And we're looking at controllers close to DRAM, and industry is finally open to new memory architectures today. I'm going to mention that later on also. So we have a huge push from technology, but we have a huge pull from applications and systems as well. So let me talk about the technology push today. Basically, today we're looking at interesting systems that look like this, 3D stacked memories, for example, where you have logic underneath memory, where you can do logic very close to memory at high bandwidth and low latency. And there are other examples that I will show you later on, where people are trying to incorporate processing elements inside the DRAM chips. And they have actually done it. They're commercial products that you can buy. But Why is this motivated? What is this motivated by? Basically, we are motivated by memory scaling issues. We're having trouble with technology scaling, and this is a paper that we wrote a while ago. If you're interested, you can take a look at it. But basically, memory is becoming having a lot of issues, and one issue is reliability. This is data that we collected with Facebook over the course of 1.5 years. We analyzed all of the memory areas in Facebook's data centers, and we found out that memory reliability is reducing, and memory reliability is causing system reliability problems. Essentially, the chips that are denser have more errors. As a result, servers are failing more than before because they're employing these chips that are less reliable. Why are they less reliable? Because cells are closer to each other. They're more vulnerable to many different types of noise. Cells are smaller in storage, in memory. And as a result, we're having trouble with reliability. Okay, if you're interested, you can read more about it. We're not the only ones writing about it. There are also other works you can find. We also built infrastructures that look like this to understand such issues at a really fine-grained level. These are FPGA-based infrastructures where you can put memory chips and test the memory chips for different types of errors and different types of issues. I'm going to talk about what we have found. We have found a lot of things, but I'm going to pick and choose some examples. But if you're interested in actually doing studies with real memory chips, we actually open source this infrastructure, and you can actually relatively easily do studies on real memory chips using an FPGA-based infrastructure like this, and we'd be happy to help in this direction. So while we were doing a lot of studies together with Intel using this infrastructure, we found out that one can predictably induce memory errors in most DRAM memory chips. This is now known as the DRAM row hammer problem. Essentially, you can predictably induce bit flips in most DRAM memory chips that are out in the field. And this is the first example of how a simple hardware failure mechanism can create a widespread system security vulnerability. And people are writing articles that sound like this. At the core of it, forget software. Now hackers are exploiting physics. I like this title over here because it has a nice higher level reflection of what row hammer is. So row hammer is basically what I'm going to show you here. All memory is composed of rows, and you can activate the row to read data by applying high voltage to a word line in memory. This is DRAM. And this is called opening the row. Now, if you do this repeatedly, activate high voltage and then precharge, low voltage in DRAM, activate precharge, activate precharge, activate precharge, activate precharge, high voltage, low voltage, high voltage, low voltage. It turns out adjacent cells that have nothing to do with the part of memory that you're activated, except being physically adjacent, get corrupt, meaning they flip from 1 to 0 or 0 to 1, depending on different circumstances we analyze in the paper. But this should not happen, basically. We're just reading this part of memory. We're not even reading potentially. We're just activating and precharging. And we're affecting data that is stored in some totally unrelated addresses. And these addresses could belong to some other processes. These addresses can belong to the system, the operating system. As a result, this poses not a reliability problem, but a security problem. So we call this the hammer row and victim rows. And we showed that this problem exists in more than 80% of the memory chips that you can buy out in the field today. Whereas it should not happen, because this is a serious reliability and security problem, as I will show you a little bit more as well. So this was not happening in chips that were manufactured before 2010 because cells were not close enough to each other. This happens because cells are too close to each other, and the activation that you do on one cell is affecting the data that's stored in other cells because of multiple reasons. Certainly electromagnetic coupling is one reason. And cells became too close to each other in recent technologies. As a result, all chips that we tested that were manufactured between 2012 and 2013 are vulnerable to these errors, independent of the manufacturer. And this is a reliability and security problem because it breaks memory isolation, which is really a key property, key pillar of a reliable and secure computing system. And we said when we wrote the paper, an access to one memory address should not have unintended side effects on data stored in other addresses. And I still strongly believe in this. And we said in the paper that someone can hijack your computer exploiting this. And later, folks from Google Project Zero showed this. And there are a lot of interesting security works that came about later that show that you could do it in remote systems by exploiting row hammer in a remote server, for example. You could do this in Android phones, but intelligently. An Android phone, an application you download can actually hammer your memory and take over your system, get access to all kinds of private data, etc. And more recently, people have shown that row hammer bit flips cause problems in deep neural networks. Essentially, they showed that you could reduce the accuracy of these deep neural networks from 90%, for example, all the way to something like 10%. Essentially, these deep neural networks become useless. If you're employing them in situations where your life is dependent on these deep neural networks, or some other people's lives are dependent on, for example, in self-driving cars, or in some medical predictions that you do using neural networks, you may actually get completely bad outcomes. So that's why this is a serious reliability, security, and safety problem. And if you're interested, you can read more about it clearly. And we have written multiple papers. I'm going to flash some of these over here. But to solve this problem, we need intelligent controls. Essentially, we want controllers. You want intelligent memory that doesn't have these problems and that prevents these problems, scaling problems, before they actually get exposed to the user. So this problem has not gone away. I wish that it was gone away. Unfortunately, the problem is not fixed yet. In 2020, we have analyzed Ropehammer again, and we found out that newer DRAM chips are actually more vulnerable to Ropehammer because of technology scaling, and existing mitigation mechanisms are unfortunately not effective. So we need to actually look at new ways of dealing with this. And we also showed that existing DRAM chips that are claimed to be Ropehammer free are actually not Ropehammer free, because some intelligent attacker can reverse engineer the DRAM chips just enough so that they can actually cause these bit flips that were the problem to begin with. So we're back to square one, and we need to fix this problem going into the future. And I think people who may be listening to this talk may be interested in some potential solutions. And we would, of course, welcome many solutions. And this is one solution we developed. This is one of the most recent solutions that was published in HPCA. I'm not going to talk about it, but it involves an intelligent memory controller to identify hammering patterns and to ensure that those hammering patterns do not cause bit flips. And if you're more interested in Ropehammer, I would recommend taking a look at some of the lectures that we deliver as well. Okay, so this is one example of a technology scaling problem that causes serious safety, reliability, and security issue. I liken this to a bit flip that happens in critical infrastructure like bridges, right? Bridges are clearly critical infrastructures. Humanity has been designing bridges for thousands of years, and we know that they're critical. We try to make them robust, etc. But sometimes there are bit flips in critical infrastructure. So computing is much more critical today. Computing is going to be used in essentially everywhere in our lives, like making life-critical decisions, medical decisions, self-driving decisions, self-optimizing decisions. And if it goes wrong, its implications are going to be much worse than bridges like this. And bridges, unfortunately, these bridge accidents also happen. This is in Korea in 1994. This is in Minneapolis in 2007. This is more Genoa more recently in 2018. Now, I think in computing, we're more lucky than bridges because bridges are very heavy infrastructure. In computing, we have more patchability, essentially. So, okay, I talk about this in my undergraduate lectures also, saying that this rod is very strong, but if you get a bit flip in it, these people may not be very happy. So I think we need to take security more seriously going into the future, security, safety, and reliability. We need to think about preventing unforeseen consequences because we're going to trust our lives on these computing platforms, like this example of a self-driving car with Mr. Bean, for example. Okay, so a big challenge of an opportunity for future going forward is designing fundamentally secure, reliable, and safe computing architectures. And I think this requires predicting and preventing such safety and security issues like Ropehammer, but Ropehammer is just one example of it. There are other issues that I'm not going to go into, like retention errors, but other errors in storage and memory are also going to be serious. But to be able to fix these, I believe we need intelligent memories, intelligent memory controllers, in-field patchability, programmability, so that the memory controller can intelligently detect that this sort of attack or this sort of reliability issue may be happening, and it fixes the problem without exposing anything to the user. Okay, so this was the push from technology part. We want intelligence in the memory system. But there's a huge pull from systems and applications today that didn't exist even 10 years ago or even 5 years ago as well. I'm going to talk about that. It was always important, but it's becoming much more important. Essentially, data access is an increasingly major bottleneck today. Energy consumption is a key limiter, and data movement energy dominates compute. We're going to take a look at each of these quickly, and then we're going to take a look at some solution directions. In my opinion, the key question is this. Going into the future, do we want sustainability and energy efficiency in the world, or do we want a world that looks like this that's going to be terrible for our children? I think we want energy efficient sustainability, but we also want high performance to solve the problems. The question is, how do we get there? And I think before we answer the question, we need to identify the problem. I think the problem is data access today is a huge performance energy bottleneck at the very core of the design of our computing systems, because our current design principles cause great energy waste. They also, at the same time, cause great performance loss. I put this in parentheses because even though they cause great performance loss because we move data all around, we try to avoid that performance loss by designing the system and making the system more sophisticated, more complicated in hardware and software. Unfortunately, that causes even more energy waste. So we're in this vicious cycle today. Data access, we know, is a major bottleneck. It causes energy problems. It causes performance problems. To avoid the performance problems, we're causing even more energy waste and even more complexity. And I think we need to break this vicious cycle. To break the vicious cycle, we need to process data far closer to the data and identify the problem as processor and memory dichotomy, basically. We want to get rid of the processor and memory dichotomy. Essentially, a computing system consists of computation, communication, and storage. We want to merge them together, if you will, because today's computing systems are very processor-centric. As a result, we have all these problems, as I mentioned, and I'm going to mention also. Basically, because of the processor-centric design paradigm, memory becomes a huge bottleneck. This is Dick Seitz. He was the chief architect of Alpha computers in the 1990s, which were the fastest of their time. And basically, they designed the flagship Alpha processor in 1990s. And he basically wrote a one-page article in Microprocessor Report titled, "It's the Memory Stupid." And basically, he analyzed the performance of this Alpha processor. He said, basically, we designed this processor over the course of, let's say, a decade. And we optimize it so that it can finish 4 instructions every cycle, but it's finishing 1 instruction every 5 cycles, let's say. So it's operating at 5% of its peak bandwidth. Why? It's waiting for data to come back from memory. And he basically said that he expects over the coming decade, memory subsystem design will be the only important design issue for microprocessors. And I think we need to keep that perspective going into the future. This is data from my own PhD thesis. We found essentially something very similar together with Intel. We found out that most of the time, the processor is waiting for data to come back from main memory. And if you're interested, you can look at our analysis in this paper. And this is data from Google. Google found out essentially the same thing more recently. Most of the time, the processor is waiting for data to come back from memory in their system because we have a processor-centric system. Okay, so essentially, because we have a processor-centric system, the system is grossly imbalanced, and it's energy inefficient, low performance, and complex, and the processor becomes complex and bloated. This makes things even more energy inefficient, low performance, and complex. And as a result, we're back to the picture that I showed you earlier. We call this a computing system, but it's most of the time, most of the resources are dedicated to moving and storing data. Now let's look at the energy perspective quickly. So this is data from Bill Daly. I borrowed this slide. This is relatively old, but it's essentially things have not changed as much, even though the absolute values have changed. This is a complex arithmetic operation, 20 picojoules energy. This is a memory access, 16 nanojoules energy. So it's 800x difference. So a memory access consumes 2 to 3 orders of magnitude the energy of a complex addition. Make that a simple addition. Even a simple addition is like that today, actually, because this was data from 2012 or so, if you will. So basically today, in order to operate on data, we need to do an operation that's 2 to 3 orders of magnitude more costly than the operation itself. Now the question becomes, does it really make sense to move the data over these energy-hungry interconnects to do a simple energy simple operation? And because we don't do that today, more than 60% of the total system energy is spent on data movement. As a result, our systems suffer. So I will posit that we do not want to move data. We want to design data-centric architectures, and we want to change the paradigm shift to enable computation with minimal data movement, compute where it makes sense, where data resides, and make computing architectures more data-centric. So what does that mean? Essentially, we want to enable processing wherever data resides, wherever data is produced, as opposed to having to process the data in the processor and the accelerators. So memory is a special example of this. I'm going to talk a little bit more about memory in this case, but our principles apply to storage. Our principles apply to wherever data is generated. Sensors, for example, in an IoT system, you may want to do processing inside the sensor, processing inside the camera, processing inside the screen, for example, as well. Okay, but let's focus on memory, because memory is a place where a lot of data is stored in conventional computing systems, and we can store our applications. Basically, we would like to be able to ask memory, can you execute this function on this database for me? And the memory responds with results. So there are many, many questions over here. I'm not going to answer all of them clearly in this talk, but how do you design the memory and the controllers? How do you design the processor chip and in-memory units? How do you design the software and hardware interfaces? The system software compilers and languages, and the algorithms and theoretical foundations of computing. So this is really an across-the-stack problem, all the way from algorithms to devices. It even threatens or maybe questions the theoretical foundations of computing, because if you have taken a theory of computer science course, and many people here on this course may have, you're counting operations, right? The complexity theory is based on counting how many operations you do using an algorithm. But maybe that's not important. Maybe how many memory accesses is much more important from an energy perspective and performance perspective. So in a data-centric architecture, you really need to question the very fundamentals of the compute-centric theory, processor-centric theory that we have developed over the course of 5, 6, 7 decades. Okay, let me quickly give you examples of what kind of benefits we can get with different approaches to processing in memory, and then we're going to conclude. So I'm going to give you 2 examples. One is processing using memory, and the other is processing near memory. So these are both examples of processing inside memory, let's say, processing in memory. But processing using memory takes advantage of the analog operational principles of the internals of the memory cells so that you can do computation without adding a lot of logic. So it's minimal approach, let's say, by changing the memory to do computation slightly. But those operational principles already exist. Processing near memory is adding extra logic closer to memory. Okay, let's take a look at the first one, processing using memory, with some example. I'm going to start simple. I'm going to talk about data copying and initialization. We do a lot of data copying and initialization in our systems today. And Google has found out that a significant fraction of the cycles in their data centers spent on data copy and initialization, as you can see, just 2 functions actually. But how do you do data copy today? How do we copy a page to another page in memory today? Basically, we have to go through the processor because we are processor-centric. At least the memory controller we have to go through the DMA engine. So this is high latency, this is high bandwidth, cache pollution exists, and unwanted data moment because you may not actually you need the data that you're copying immediately. So this is expensive for even if for a small page copy, 4 kilobyte page copy via direct memory access. It's about 1,000 nanoseconds and 3.6 microjoules. Now, if you show this picture to a child and maybe ask the question, does it really make sense to move the data all the way into the processor whenever I want to copy a page to another page inside the memory? Maybe you will get the simple answer saying that, oh, why don't you do this inside the memory? Because it's much faster that way and you're not moving data unnecessarily to somewhere else where you don't need it. And that's the idea basically in memory copy. It's low latency because we're going to exploit the internal bandwidth. It's low bandwidth utilization because we're not going to move the data on the very expensive data movement part of the system. No cache pollution. I'm not going to talk about that, but you can eliminate that today with DMA. No unwanted data movement, essentially. And I'm going to show you a mechanism very quickly at the high level that takes us 1,000 nanoseconds to 90 nanoseconds, more than an order of magnitude improvement, and 3.6 microjoules to 0.04 microjoules. And the idea is very simple. At the core of it, in DRAM, analog operational principles enable you to do this. In fact, you can do this in real DRAM chips without changing the DRAM interface today, as we have shown and as others have shown before us as well. So basically, the idea is, in order to copy a row to another row in DRAM, you first activate the source row, which brings data into the sense amplifier strongly. And then you activate the destination row, which takes the data from the sense amplifiers to the destination row. Essentially, by using the sense amplifiers as a buffer, you can do the data copying very quickly inside the DRAM itself. So the idea is 2 consecutive activates, negligible hardware cost. In fact, existing DRAM chips can do it if you modify the memory controller today. And that gives us more than an order of magnitude latency reduction, 74x energy reduction on the memory side. And you can do this actually, we have generalized this mechanism. I'm not going to talk about the details, but you can actually get similar results wherever the data resides inside the DRAM chip. And if you're interested, you can take a look at these papers that I mentioned over here. You can do faster copies, you can do small granularities, interbank. I'm going to talk about computation next, but these are the papers that you may want to also take a look at if you want to look at the optimizations that are more recent. But we're thinking about memory as an accelerator now. We want to add specialized computation capability inside the memory, and the memory can actually do this computation very efficiently without disturbing the processor. And it's very similar to a conventional accelerator, except it's much more efficient because it doesn't have the memory bottleneck. Okay, so similarly, we can do in-memory computation. We can do in-memory bitwise operations, majority and or not. I'm not going to go into the details of how we do it, but we essentially exploit analog computation capability of DRAM. Activating multiple rows performs computation, and this leads to between 30 to 60x performance energy improvement in each operation. And you can take a look at this paper if you're interested again. And non-volatile memory technologies that are emerging enable even more opportunities. People have shown this as well. You can, for example, do matrix vector multiplication using analog current mixing. And you can also do similar operations like what we proposed, row clone, as well as bulk bitwise operations in these technologies as well. But these technologies have an advantage because they're non-volatile, so you can operate on data with minimal movement. Okay, I'm going to give this idea very quickly. If you have triple row activation, it gives you a bitwise majority function due to the chart sharing, analog chart sharing principles of the DRAM circuit. So the final state is bitwise majority, which is a great function on top of which you can implement actually real applications. I'm going to briefly mention a paper that we wrote recently on this. But you can also have and or functionality by setting C to 1 or 0. And then you can also add not functionality by taking the data, complement of the data from the other side of the sense amplifier to the array. And we talk about all of this in our paper. If you actually take advantage of those bitwise operations, you can accelerate database queries significantly end to end. And this is from our paper. We show that you can accelerate some important database queries by 4 to 12x, and your performance scales with the size of your data, which is a nice property, as long as you can fit it inside the DRAM chip, of course. Okay, if you're interested in more, there's a lot more information on this that we have written. I'd recommend you take a look at it. This is the most recent work where we showed that you can actually do even more complicated operations, and you can do it as a framework using majority and not functions. I'm not going to talk about it. You can also do interesting security functions inside DRAM, physical unclonable functions and random number generation, for example, by taking advantage of the analog properties of the DRAM chips. Again, I don't have time to go over it. But let me quickly go over the other aspect, processing near memory, even faster than what I have done with processing using memory, so that we don't delay things further. Processing near memory is very interesting because now you can add general purpose computational logic arbitrarily close to memory, basically. Of course, there's a cost equation that you need to consider, but you can have it in the memory controllers, you can have it in the 3D stacked logic layer, you can have it inside the DRAM chip. But the question is why? Why do you want to do this? Because you want to accelerate important applications and make them much more efficient. And one important application we studied was graph processing. Clearly, graphs are everywhere. They're in machine learning, they're in bioinformatics, they're in social networks, they're in representing large amounts of data. And scalable large-scale graph processing, graph analytics is very challenging. As you can see, if you throw cores at it, you don't get benefit because you have frequent random memory access and little amount of computation. So the question we asked was, can we actually take advantage of 3D stacked memories for this? Add logic inside the logic layer in 3D stacked memories, where memory and logic are tightly integrated using high bandwidth, low latency, true silicon via connections. This technology is becoming even better today. We're going to have monolithic 3D architectures going into the future, which is an extension of this, in my opinion. And we designed the system that looks like this. Essentially a distributed system that takes a 3D stacked memory and combines it with many other 3D stacked memories so that you can have a scalable system. But internally inside the 3D stacked memory, you can see that we have in-order cores. And these in-order cores are connected via an interconnect. And you can actually do message passing communication between these in-order cores. And you can partition your graph across the memory, and you can actually operate on the partition graph by sending messages between the in-order cores. So we don't move the data here. We move the computation to the data by sending messages. Again, I'm not going to go into the details of this. There's a lot more detail because it's a full system design. I'm going to give you some results. But this is essentially a distributed in-memory processing system. Communications are done via remote function calls to the in-order cores that house the data. And we have sophisticated prefetching mechanisms that I'm not going to talk about. But the system looks very different from a conventional system. These are conventional systems that we compared to. There's a processor and memory dichotomy. So you can easily say, these are the processors, these are the memory. Here you cannot tell. Here basically every single component is processor and memory at the same time. Processing is done, tightly integrated with the memory, and you combine the components. As a result, very high amounts of bandwidth is available to the processors that we design. And the performance benefits are significant, as you can see. These are averaged across 5 important graph processing algorithms. We get about 13 to 14x performance improvement. Now, later works, this is work from 2015, as you can see. Later works improved our design. They actually came up with very nice ideas. And the performance improvement currently is about 2 orders of magnitude, more than 100x, based on the initial design that I mentioned. And the energy efficiency is also similarly good. It's basically more than 8x. And again, recent work has improved this because we're not moving data out of the memory chip as much as possible. We're getting significant energy efficiencies. Okay, if you're interested, there's a lot more on this. I will very briefly mention that you don't have to change the entire system to get some benefit from processing in memory. In this work that I alluded to earlier that we did with Google, we actually analyzed consumer devices, and we basically looked at these important workloads to understand the bottlenecks. And I gave you already this data point. We found out that more than 60% of the data, total system energy in these workloads is spent on data movement in mobile devices. And we wanted to actually do processing close to memory using 3D stacked memories as similar to what I mentioned earlier. But we wanted to be more realistic. We basically said, we want to offload functions. And then the question becomes, which functions do we offload? And it turns out a significant fraction of the data movement often comes from very simple functions that are in your programs. And we analyze those simple functions, and we design simple low-power cores to execute them near memory, and simple fixed function accelerators as well. Of course, fixed function accelerators are more efficient because they're customized for those functions. In my opinion, having reconfigurable logic near memory is going to be even better. So I think we want to have heterogeneous execution units near memory, cores, accelerators, and reconfigurable logic going into the future. And we showed that you can actually gain, by being careful about what you offload, you can actually gain by more than 2x performance and energy improvement in real workloads like the ones that I mentioned. So just to give you an example, these are the workloads. And machine learning inference, for example, TensorFlow Mobile is Google's machine learning framework. Machine learning inference is very much bottlenecked by data movement. more than 50% of the inference energy spent on data moment, and more than 50% of that data moment energy comes from packing, unpacking, and quantization operations. I'm not going to go into details of what these are. Again, I'm happy to answer questions, or you can watch other lectures. But these are very simple functions to manipulate data that goes into your neural network, or that goes into the next stage of your neural network. And by offloading these operations to main memory, you can significantly accelerate and make energy efficient the machine learning inference. Okay, so if you're interested, there's more in this paper. And clearly, there are other papers that I'm not going to talk about, but I'm going to give you a very quick overview. You can do distributed GPU processing in using processing near memory. And there are papers that are about it, which we don't have time. You can exploit linked data structures, which are at the core of many interesting data traversal algorithms today. And I think this is important going into the future. You can exploit dependent cache misses, exploit prefetching mechanisms. You can exploit important applications like climate modeling. I will briefly mention this again. And approximate string matching, genome analysis, time series analysis that are employed in many scientific applications like astronomy, for example. And you can get significant energy and performance in all of these things that you can exploit near data by reading these papers. You can find out exact numbers. But usually it's more than an order of magnitude compared to existing systems. But to be able to do all of this, I think we need to revisit the entire stack, because this is really algorithm, architecture, device, and logic co-design in the end. But I believe we can get there step by step. I'm not going to exactly talk about how we get there step by step. We need to look at simple things like row clone that I mentioned, simple changes to the system so that we can get benefits little by little. Of course, it's important benefit in some applications, but maybe over time, these benefits will accumulate. That's what I mean by step by step. And if you're really interested, we have written overview papers. This is a more recent overview paper that talks about processing in memory. And this is an older overview paper that talks about workload and programming issues. But the good news is, these systems exist now. We were writing, and other people were writing actually papers about it earlier in the recent incarnation of processing in memory, let's say early 2010s. But now there's a company, UpMem, that has actually produced these chips. They call the DRAM processing units. They have a processor near each DRAM bank, and we actually work with them. These are the memory modules. These are real systems that we ran. And if you're interested, you can learn more about the processor that they have designed inside the DRAM bank. This is a talk that my senior researcher Juan delivered recently. You can take a look at it. And this is a paper that we have recently released on experimental analysis of the UpMem PIM engine. And it turns out there are some workloads where this system is much stronger compared to state-of-the-art GPUs and CPUs. And you can take a look at the paper. We've also released benchmarks, so you can actually do your own benchmarking of the system once you get access to it. I think FPGA-based processing near memory is also important. We've been dealing with 3D stacked memories that are connected to FPGAs, and we see significant benefits for genomics, for example, and weather climate modeling as well. And this is a very recent paper that we just completed that you may want to take a look at if you're interested. And these are real data from real systems, both of these works. And more recently, Samsung announced that they are actually finally developing processing in memory systems. As you can see, this is as early as February, as late as February 2021. And they basically call what they're doing function in memory, which is essentially a near memory processing engine, where the near memory processing engine is really customized for, let's say, what they call AI, but what I would call matrix multiplication, as you can see. So basically, they have near each bank, they have computation units that can do efficient matrix multiplication. Okay, I'm not going to go over this in detail, but this is good news in my opinion. Finally, the industry is actually moving towards these architectures, maybe little by little, but that's good. You change the paradigm, hopefully over time. And if you're interested, we have detailed lectures on PIM, and a much more longer version of this talk is available as an IEDM tutorial, but it doesn't have some of the newer insights that I showed you clearly because of the difference in the date. Okay, so basically, I think I'm almost done. We want fundamentally energy efficient architectures. That means that the architecture needs to be data-centric. We want fundamentally high-performance energy computing architectures. That means that the architecture needs to be data-centric again. So data-centric architectures provide us with energy efficiency, high performance, and I believe more sustainability going into the future. I also believe more reliability and security and better scaling. So being data-centric, being memory-centric actually comes up with a lot of benefits and eliminates a lot of the problems that we face in today's computing platforms. And hopefully they enable computing architectures with a minimal data moment. Of course, there are adoption issues, which we did not discuss. I'm not going to discuss them. Clearly, we need to solve the adoption issues like functionality, applications, software. A lot of these adoption issues are related to software and programming, but there are hardware issues as well over here and the hardware-software interface issues. We try to tackle some of these issues. I don't have time to go over them. Coherence and virtual memory, for example, runtime systems, compilation systems, security, and infrastructures. But I believe all can be solved with a change of mindset. And the change of mindset is essentially shifting our mindset from the processor-centric paradigm to the data-centric paradigm. Okay, again, I think we can get there step by step, but eventually we will need to revisit the entire stack. And if you're interested, we have also released another paper on arXiv that provides a new methodology for understanding data moment bottlenecks and a workload suite, and you can take a look at it. The workloads are also released as open source. And I believe if we do all of this, we can enable new medical platforms, health platforms, new platforms in general. Medical is interesting to me because we have been working on bioinformatics and genomics. And again, I think there's a lot of potential here. And if you're interested, you can take a look at these works. So what we do not definitely have time for is the two other aspects of opportunities for the future. We want data-driven, self-optimizing, self-learning, self-growing architectures, self-evolving architectures, if you will. I'm not going to talk about that, unfortunately. We also want data-aware, more expressive computing architectures where the semantic information about data and computation is communicated to the underlying architecture of the system so that we can have a much more efficient system. And I believe this data-driven and data-aware go along very well with data-centric, because these are really three things that, in my opinion, should enhance all of the architectures. They have good synergies with each other. And again, more info is in this tutorial as well as backup slides. The backup slides have some slides on data-centric and data-driven architectures. So now let me conclude. Hopefully, I've given you examples of how we're not dealing with data today, and data is our major bottleneck. Today's architectures are processor-centric as opposed to data-centric. They're human-driven as opposed to data-driven, and component-aware. They make component-aware decisions as opposed to data-aware decisions. I think it's time to design principal system architectures to solve the data problem, which is our major problem today. We want to design complete systems to be truly balanced, high performance, and energy efficient. And hopefully that will lead us to intelligent architectures. And I think intelligence comes from at least three principles: data-centric, data-driven, and data-aware. In my opinion, actually, we see all of these three principles in nature, as well as the way we humans evolve. I don't suggest that we know everything about humans and nature, of course, but there are some principles that are that we know that are along these lines that make us maybe more efficient and maybe more intelligent than actually our counterparts in machines. We would like to enable computation capability inside and close to memory. And I believe, hopefully I've convinced you that this can enable orders of magnitude improvements and new application and computing platforms, maybe better understanding of nature because we would be perhaps closer to nature, maybe better than it in some ways, and who knows what else. So I think we do need to go towards data-centric, data-driven, data-aware architectures. And maybe we can find better principles for our architecture system designs. I don't claim to know all of the principles again, but I think a distributed system like what we have in the brain is not a processor-centric system. And I believe many people have shown evidence for it, scientific evidence for it. And I believe we need to discover other principles clearly going into the future. But to be able to do that, we will need to think step by step. And most importantly, we need to have open minds. I believe we need to exploit good principles, some of which we know. I've actually talked about a lot of these principles in this talk without naming them necessarily. Some of them I named, I think. But I think more importantly, we need to have open minds such that we can do the paradigm shift. We cannot, whenever we think processor-centric, we should be able to say, this is a remnant of the processor-centric paradigm. Maybe if we think differently in a data-centric way or data-driven way, a data-aware way, we can solve the problem in a much better, much more fundamental way. And we don't have to waste a lot of energy and performance on this process-centric remnant of our thinking. Okay, I will briefly mention the papers that I would recommend and the talks if you're interested. I will acknowledge folks who have supported our research. Thank you, and please keep supporting us. And I will most importantly acknowledge my group who has enabled all this research, as well as collaborators, of course. You can find the list online. And this is my group pre-pandemic. This is my group during the pandemic. During the pandemic is here, actually. If you're interested, you can actually take a look at our newsletters and learn more about the people who have done this work, as well as people who are doing other work that I didn't get a chance to talk about. And all of our reference papers, talks, and artifact software is available online on these websites you can find. Thank you very much. I appreciate your patience, and I'm happy to take any questions at this point.
Absolutely. Thank you so much, Onur. It was indeed a high-intensity knowledge-sharing session for all of us, and it was worth the wait. We were actually looking forward to the session, and what a wonderful session, I must say. Having said that, since you just mentioned about the pandemic situation, how's the situation out there for you guys?
Could you say it again? Oh,
How's
the
the situation
pandemic
out there?
situation.
Yeah,
Oh, okay.
for you, yeah.
It's getting better. Of course, things are opening up a bit warily, but we'll see. Of course, it's a bit unpredictable. Clearly, in all of the world.
Yeah.
I hope things are better. I hope things are better in India.
Absolutely. It's still, again, I think we are facing the same thing, and I think we are sailing in the same boat. So let's just hope that better days are ahead of us.
Yeah, I agree.
But thanks to the virtual world that we are able to connect today. That's the beauty of science and technology.
Yeah, that was I think the benefit. I didn't have to travel because travel is much harder. But this
Absolutely. And I think it's an honor to have you here with us today. So now let's open the room for audience questions because we have received multiple questions for your session. So now I would request Ankit to come in and please put forward the audience questions now.
Sure. Thanks, Minnie. Guten Morgen, Professor. Marhaba.
Merhaba, Ankit.
So have multiple questions lined up, and what a talk. So it's always a privilege listening to you.
Thank you.
I will have to make a selection of which questions to ask. So yeah, going by chronological order across your talk, I have questions like the eraser correction, ECC, basically in memory. Can it help slow down the hammer attack that you mentioned about? Can we have some correction codes built in so that we can fight it out?
Yeah, so that's a very good question. In a longer talk, of course, we discuss all of these issues related to rowhammer. But certainly ECC can help because it can correct some of these errors and it can detect some of these errors. But the ECC is not enough, basically, today, because the existing ECC mechanisms that are employed either inside DRAM chips or in the memory controller can detect one error and can maybe can detect two errors and can correct one error because they're too costly to build otherwise. And we have found that with rowhammer, you can induce more than 4 errors in an ECC code word, essentially. So you need to have a much stronger error correcting code than what we have today to be able to get rid of all of the rowhammer problems. And I think I would argue that that's not an efficient solution to rowhammer because ECC error correcting codes are great to deal with errors whose causes we do not know of. Meaning, usually if you have a random bit flip, for example, retention errors tend to be this way, or soft errors tend to be this way. If you have a random bit flip, it's very hard to solve that problem without something else other than ECC, error correcting code. But rowhammer, we know exactly why it happens. We know that somebody is accessing this row or particular rows very, very heavily. And we can design a leaner mechanism, lower cost mechanism than strong ECC that can actually fix this problem. So in my opinion, ECC, if you make it strong enough, yes, absolutely, it will fix rowhammer. But the strength of the ECC that's required to fix rowhammer would be, in my opinion, prohibitively expensive because I believe we have better methods for fixing rowhammer.
Sure. So next question, actually taking along on those lines, if we actually build a model, a deep neural network based on the access that you're seeing, like if rowhammer is active at some point in time, you're seeing a different pattern than usual. So can we actually predict that there is an upcoming issue that's going to happen?
So that's a good question, actually. That's something we have not looked into. And maybe that's something worthy of investigation. Somehow, I'm not sure if deep neural network is the answer, but some sort of a learning mechanism, let's say, that can detect anomalous access patterns, right? I think that's what the question is getting to. Right. Potentially, yes, potentially. So right now, what's happening is in the solutions that we have developed and some others have developed, we're trying to figure out these anomalous access patterns that are intensive access patterns using not learning mechanisms, but more like Bloom filters, for example, by keeping track of how many accesses you have done to a particular row in an approximate manner, but in a manner that's good enough to actually detect the problem. Learning can potentially be employed here. I don't know. I think it's a good area of investigation. I cannot say it's a better or worse direction. It depends probably on the learning mechanism. But I would recommend the person who's asked the question or anybody who's interested to potentially take a look at what machine learning can bring to solve this problem. In the end, I think the solution needs to be adoptable widely. The solution needs to be low cost. So I would recommend trying to make the solution low cost, whatever learning-based solution it may be.
Sure. Sure. So actually getting along from the slides that you presented, so much of the row hammer attack is, or as you have investigated, is in case of the DRAMs, right? So is some of the newer technologies like the persistent memory, for example, let's say Intel Optane, also susceptible to something similar?
So that's also a good question. Basically, the high level answer is yes. But there's a caveat in the sense that, so for example, there was a paper in ICCD a few years ago that showed that STT-MRAM is susceptible to row hammer. There are papers that show that phase change memories are susceptible to similar disturbance phenomenon, like write disturb phenomenon. So I'm not sure if the disturbance is exactly the same as what we see in DRAM, for example. Hard disks are, for example, are susceptible to write disturb phenomena also. So there's certainly disturbance, hammering phenomena in general, whether it's due to writes or reads. It depends on the technology. But in my opinion, as you scale the technology down to smaller sizes, this electromagnetic coupling happens in all technologies in some way. And people have shown that this does happen in emerging technologies as well. Now, I don't know if particularly Optane is vulnerable to this, because clearly there's a controller that protects Optane, right? Intel doesn't release Optane as raw chips that you can hammer, as far as I know. There's an internal controller that does error correction. There's sophisticated error correction, as far as I could tell, in Optane chips. So they may be correcting some of these errors internally as well. Or their technology size may not be small enough to observe some of these disturbance effects, because even in DRAM, finally we are getting into technologies where row hammer is a huge problem, right? So in my opinion, the short answer is yes, but the other technologies currently have controllers, intelligent controllers, that are trying to fix the problem, whereas DRAM is not having those controllers.
Sure, I guess because you would also need an FTL equivalent thing for Optane, because it suffers from wear leveling. The life of the entire transistors is probably not going to be like DRAM. Like you can store and read as many times as you want, practically, but then Optane has a life. So I'm guessing like that might also be instrumental in protecting it.
Yeah, absolutely, absolutely. Actually, we have done a lot of work on flash memory, SSDs, and we saw row hammer-like effects, read disturb effects in flash memory, much worse than DRAM. But the FTL, flash memory controllers, can fix the problem easily because they do a lot of other things anyway.
Right, right. So well, a segue from what you just mentioned. So from your work in the flash area, so do you also have some recommendations or things like in-memory operations for persistent memories or non-volatile memories?
So, I mean, we are looking into it more so than before right now. But yes, I think certainly it makes sense to look at in-memory operations for flash memories as well as other types of memory. And I think, again, the principles that I mentioned apply for both of them, processing using memory as well as processing near memory. For example, in flash memory or phase change memory or some sort of memristors, you can do analog operations internally, bulk bitwise operations similar to what I mentioned. You could do row clone type of operations. You could also do matrix multiplication like many other works have shown. They built prototypes actually for this. And I think that's a very good direction. But there's also another direction, which is adding computation elements next to the memory. Flash memory controllers are actually very good examples of this in the storage SSDs today. You have ARM processors, you have FTL, and you can add a lot more logic inside there, or you can execute programs inside there. And we have actually been looking into that as well. So I think the answer is, again, yes. And again, I think the processing in-memory types are applicable to all types of memories. And in my opinion, we should explore all of them to find out the different types of trade-offs we have with different types of memories. Because in the end, in my opinion, different types of memories will be part of the solution of the future. And ideally, we would like to be able to do the processing in all of them. We don't want to move the data again all the way to the processors and accelerators that are far away from the memories.
Sure. Thank you. And next question is more like a trend-like thing, because we deal with storage, and what we have seen is, like in storage systems, we have tried to scale up all the way till HCI, where you are putting in the compute and the storage together. But then people are also moving towards disaggregated storage and disaggregated architecture. And you're saying because that the compute and the storage and everything doesn't scale the same for all applications. Do you see that in future when we start having chips, like you mentioned about Upman, they are building and processing into the chips and memory chips. So it would be like a PIM, not a DIM, as an it sits on the memory bus. And but then at some point in time, you would also want, I want more compute, I want more storage, and then different combinations. And then you will ask for a disaggregated architecture around that. So do you see that as a trend coming in?
Yeah, I think there's, in my opinion, that's a good trend also. In my opinion, there's no single silver bullet, let's say. If you want to really scale the system, like have hundreds of terabytes of memory, today we don't have the technology to put that in a single node, right? And I believe disaggregated memory is certainly a good trend. In fact, we have some work on it also. That was one of it was just published in this ASPLOS. I believe disaggregated memory is a good trend for applications that require those huge amounts of memories. Of course, I don't think that the disaggregated memory goes against processing near data. Whenever you have disaggregated memory, for example, you can offload computation to that memory server that stores huge amounts of memory as well, right? In my opinion, whenever we build disaggregated memories, we should also try to move the data as little as possible. If we can ship the computation to the remote memory, for example, we can again avoid the data movement. But today, I think what we're doing in the design of disaggregated memory systems is we have this node, and we're actually moving the data into the node so that we can process it. And the memory server is not doing computation. Of course, I think with RDMA, things change a little bit, right? Things have changed a little bit. But I think we need to push a little bit further so that we can scale up the system and have a lot of memory by disaggregating it, but we can still localize the computation to the data without moving the data. I don't know. Hopefully that makes sense.
Sure. And there were like so many things that we would want to continue listening to you about. I guess in a subsequent edition of our conference, we would want to have you again as a speaker, because I think there was a lot of content you had to trim because of the limited time. So I will save some of the questions due to lack of time at the moment. And thank you so much for joining us remotely.
Okay.
Over to you, Mehdi.
Yeah, I'm happy to visit again remotely, and maybe hopefully in person in the future sometime.
Of course. Hope the situation here as well as in Switzerland is good enough, and next time actually we would like to host you in person in our conference.
Sure, yeah, and feel free to communicate the questions to me if you think I should answer them. I'm happy to try to do that, and thank you for inviting me.
It's a privilege. It's our privilege. Thank you so much.
Thank you, Ankit.
Thank you so much. As Ankit mentioned, it's a privilege for us. And I think it's our honor to have you here. And definitely we're looking forward to meet you in person, maybe next year, hopefully, when things are better. Thank you so much for joining in. And thank you so much for addressing all the questions so patiently.
Okay, thank you very much. Have a good day.
You too. Thank you. All right. Now, quickly, I think this was fun. Super insightful session. I think all of us enjoyed and learned so much from it. I think this has been such a fruitful day. Now, I want all the three speakers of the lightning talk to come back. I hope you guys are here. Archit, Shubhankar, Prashanti, can I please have you on board now? Archit, Prashanti, Shubhankar, are you guys here? Yes, now I can see you. Hi guys, how are you? Am I audible? I think all of you are on mute. Prashanti, are you there?
Yeah.
Perfect. Now I can hear you. So since we missed out on your Q&A due to lack of time, so as promised, we had to circle back to your questions. Also, besides that, we have a very fun segment planned for you guys. It's like a fun trivia rapid fire round. So the rules are fairly simple. All you have to do is, since you know that the app gives you a mute-unmute option, and I'm sure you all have figured it out by now. So when I'm asking the question, you guys should be on mute. Whosoever knows the answer of that respective question quickly unmutes himself or herself and quickly present the answer. So the first person speaking up, we'll consider the person whoever turns up first. Okay, fair enough. Rules are pretty simple. I hope you guys have understood the rules, and it's all just fun scientific trivia questions. Did you guys get it?
Yes.
Yes. Are you guys ready?
Yes, yes.
No, I can't hear it. You didn't have your lunch, did you?
Yes, we are ready.
This is not how somebody who's just had lunch talks. Come on. Are you guys ready? Come on. Tell me. Again, I think either you are on mute or you guys are not talking only. I'm the only one talkative here.
Yes, yes, we are ready.
What about the other two? Come on, give me some energy. Are you guys ready? What about the other two? I can't hear you. I just heard Archit.
Yes.
Now I can hear Prashanti. And what about you? Shubhankar, are you ready?
Yes, I am ready. Am I audible?
Now you're audible. Please, please be loud and clear, and I'm looking forward to this. Also, just for your reference, we'll put every question on the screen for you guys. So consider this as a mini KDC for all of you. So let's quickly have our first question on screen. Can we please have our first question on screen? So your first question is, a collection of lines that connect several devices is called what? Whoever knows the answer, please unmute yourself. Archit, unmute. What's the answer? Archit, are you saying something? Unmute,
Bus.
you're still on mute.
Bus.
Yes, that's the right answer. Congratulations. 1 point to Archit. Super. Great. All right. Super speed, Archit. Congratulations. Can we please have the next question now? So VLIW processors rely on if you know the answer, quickly unmute yourself. If you don't know the answer, we'll pass. Anyone? Should I pass this on?
Instruction level parallelism.
Instruction level parallelism is your answer, Shubhankar. Anyone else who wants to give it a shot? Okay, so let's see Shubhankar right or wrong. Can we please have the answer to this question?
Same thing.
No problem, Shubhankar. We still have a lot of questions for you. Compile time analysis. Let's move ahead towards our third question. I want you guys to buck up. Please pay attention. Focus here with a little more energy. And let's see who gets this one. The access time of memory is dash the time required for performing any single CPU operation. And the right answer
More than. Is greater than or more than.
Okay, Shubhankar, you are right, Shubhankar. 1 point to you. Congratulations. So with this, the score right now is Shubhankar 1 and Archit 1. Prashanti, come on. And team Prashanti, go for it. Data-intensive applications utilize who's answering this one? Archit, again, are you saying something? You're still on mute. Come on, quickly. Should we pass this?
Large memory.
Yeah.
What, Shubhankar, what did you say?
Large amount of memory.
Large amount of memory. So, Prashanti, I think he was a little more fast than you. So come on, back up. Come on. So the score right now is 3-2. Archit, Prashanti, come on. Let's be competitive. Your next question is, a processor performing fetch or decoding of different instruction during the execution of another instruction is called And the answer is?
Pipeline processor.
Can you please have the answer?
Pipeline processor.
Amazing, Shubhankar. Oh my God. Prashanti, you once again, just by a second, I think Shubhankar was faster. Amazing, Shubhankar. I think you are in the lead. Score right now is 4-2. Amazing. Oh my God, I'm so happy. Prashanti, come on. Let's do this. Next question for you guys. For a given finite number of instructions to be executed, which architecture of the processor provides for a faster execution? And the right answer is Shubhankar, are you going for this one as well? Are you going for the hat trick? Archit, mute. Still on mute, Archit. You can type as well, just in case your audio is not working. Although try and mute and mute. Your answer is Numa? Archit? Alright, can you please have the answer on screen? Can you please have the correct answer on screen? Super Stealer. Alright, come on. So we have our next question, which is, which of the following is not a characteristic of parallel computing? Why do I have a feeling Shubhankar knows this? He knows this.
We don't have an option here. I think question is incomplete. Is not a characteristic.
Can we please either switch to the next question or have the options for this? Since can we just switch to the next question? All right, what leads to concurrency? This is the second last question. There's just one more question. Shubhankar is already in the lead. Come on.
Data independence. Something.
Okay. Can we please have the answer on screen? Parallelism. Okay. One last question to go, guys. One last question. Can we please have our last question? MIPS stands for
million instructions per second.
Okay. Can you please have the answer? Absolutely right, Prashanti. Well done. Superb, guys. This was amazing. But we have a clear winner in the house, Shubhankar Suman Singh. Can we please have a huge round of applause, Shubhankar? Well done, and thank you so much, Prashanti, Archit, for showing such a spirit. Can everybody, whosoever is listening, can you just like clap and please congratulate Shubhankar. Thank you so much. IEEE will send you a new iPhone very soon at your house. I hope it's up for that. Thank you so much. Just one question before you guys leave. So, since you have heard of so many challenges in the house, and we heard so many speakers coming in, talking in. So, is there any one particular agenda or subject that really excited you and you thought, I really want to do something in this, or I really want to research more about this? Either of you?
Yes, that was true. So today's talk was really exciting and really interesting. So I had a great day, and I'm completing my PhD soon, and I was only in the academic background till now. Today I had the first experience of having an academy industry collaboration. So starting from the first talk itself, getting to know what are the new architectures that are being developed, or what are the current trends, or what are the new things and exciting things coming. So I liked it very much, because till now doing research and doing something practically matters a lot, and getting taste of things actually being built was very exciting. And especially the last talk from Professor Onur Motlo. So it was very exciting. I always follow his papers, I always follow his students' works, and getting to hear from him live was very exciting.
Great. Thank you so much. Thank you so much for sharing. Thank you guys for coming in. Thank you so much for joining in today. It was a pleasure hosting you guys. Thank you so much. And I hope the audience out there enjoyed their sessions. To all the audience present, to all the participants present in the room, since I promised there's a voucher for you guys, so I know for a fact that you guys have been waiting for it, and I don't want you to go back home without winning that voucher. So we have one question, and this is open for all the participants, all the audience members listening to us today. All you have to do is listen to my question properly and type the answer on the chat box. So this is just one question, one lucky winner who will receive a voucher worth ₹1,000. So this is your chance, guys. Go for it. I am gonna ask one question. Somebody can keep a tab on the chat box from our team. And your question is, I hope, firstly, you guys are ready. Just once again, please show me by the raise of hand since I can't hear you guys. I am asking, I'm putting up my question. Are you guys ready? Super.
Yes.
Okay. I can see people. Perfect. All right. So your question for today is, high performance computing of the computer system tasks are done by, I'll repeat my question. High performance computing of the computer system tasks are done by, and let's see if somebody from our team can check the chat box who answered, whose answer did we receive first, and who has, oh my God, there are so many entries in the chat box. Anybody from my team who can help me find the correct answer and who answered it first? Wow, amazing response, guys. Oh my God, we have multiple answers. Amazing. Ankit, if you can come in and help me find the right answer. There are so many responses here. No, that's wrong.
I think they're sending the answers directly to you.
Oh,
or
I think it's on. It's there on everyone's chat. You guys can't see it.
No, so everyone's I can see.
Yeah. Wow. All right. So I haven't been able to find the correct answer yet, Ankit, or anyone from my team who can just help me look in the chat box. And thank you so much for amazing and quick responses, guys. This is amazing. I'm so excited already. Let's find out who has answered correctly. No, that's the wrong answer again. Ajit. Sanjeev Kumar Pandeyji, that's the wrong answer. Prabhat Saraswat, I hope I'm pronouncing your name right. That's the wrong answer. Can anyone from my team help me? Because I am unable to find the right answer. If anyone can help. Meanwhile, since my team is looking for someone if there is a correct answer. Until then, since we haven't received the correct answer so far, I'm giving you one more chance, guys. I'll just ask you another question so that I give you one more chance, because so far I haven't received the right answer. So your next question, which I'm hoping a lot of people in the room would know this. Please listen to the question carefully. What is usually regarded as the von Neumann bottleneck? We've talked about this today, and I hope people know the answer here. Please put your answers on the chat box. If anybody from my team can help me check the chat box, and whoever has chipped in the correct answer. Yes, come on. Already we've received some amazing responses. Wow, all right. Oh my God, we are receiving multiple responses, guys. You guys are fighting for the voucher. And there will be one lucky winner today. Amazing. All right, I've received multiple answers again. I'm just looking for the right answer. Amazing, 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 amazing. No, that's wrong. That's wrong. All right. So let's do one thing. I have seen a couple of answers, and my team is going through the rest of the answers. So what we'll do is, meanwhile, you guys just stick around. We are sorting all your answers, and we are looking for one lucky winner who has been able to answer and who has managed to answer the question correctly. But for that, I think it will take some time since there are multiple responses and we have to go through it. So meanwhile, while we look for the winners, let me quickly take you towards our next session. And the next session is basically the closing session. So right after the closing session, we'll announce the winner. So let me now quickly just move ahead. And I hope you enjoyed all the sessions, all the talks, all the panelists that came in today and shared their wonderful insights. Now, to present the closing notes, we have the Treasurer, IEEE Bangalore Section, Mr. Prashant Mishra. I hope you are here, sir.
Yes, it's me. Yeah. Thank you,
Hi,
Minnie. Yeah, I'm doing well. Thank you, Minnie. I think we had a wonderful day. We have come to the end of the IEEE Data and Storage Symposium. I cannot say that I have the pleasure of closing it because I was personally following all the talks for the day, and I was glued to each and every one of them. And I must say we had a wonderful listing of speakers, and we had all the who's and who's in the field of data and storage here, right? Now, to summarize the day, I think we had close to around 9 to 10 technical talks, one panel, around 3 lightning talks, and we cannot thank enough, but all the speakers and participants who have made this program extremely successful. In no particular order, let me start by thanking our chairman of IEEE Bangalore Section, Dr. Bindu Madhava, the CEO of Huawei Technologies, Mr. Isaac Deeve, and then thanking Thomas, Arun, Siddharth, Manu Avasti, Badrinath, Abdullah, our panelists, Shakshi, Dirajan, Sivasubramaniam, Archit, Jean, Jaya, Shubhankar, Prashanti, of course, at the end, Professor Anur Butlu, right? So, and thanks to all the participants. I think we had a very consistent flow of participants and traffic for the day. You may not be knowing, I think you're just seeing the WebEx view, but there is alternate view that other people in other parts of the world are also following. So in total, we had close to some 200 participants who are attending the talk. Oh, I'm sorry, some feature plan. Okay. So what I was trying to say is that this is not the end of the series. This is just the beginning of the series, the data and storage series. We plan to have a follow-on series probably in 2 months' time. We'll also rethink the format of it, given that we have a successful format with this series. We want to see if we want to stay with this current format or we want to improvise and improve on this format. And finally, we want to close the year with a large data and storage conference, which will be one of Bangalore Section, IEEE Bangalore Section's flagship events. I'm very thankful to our partners, IEEE Computer Society, and of course, Huawei, who have come along a long way in arranging this program. We had limited time to put this program in place, but thanks to the entire organizing committee and the larger team who typically worked round the clock to make it possible. And of course, thanks to Minnie, who has been wonderful throughout the day and who has been coordinating the entire session end to end. So thank you, and over to you.
Amazing. Thank you so much. Now I hope all the participants today, I think we had close to 200 people in the room today, all the amazing speakers, everyone who took time out of their busy schedule, who gave us your
Minnie, there's an echo
precious
from your
time,
end.
and who's... Sorry?
Both your mics are open, so echo on your end.
Am I audible?
Yes.
Is the audio fine? All right. So as I was saying, thank you so much for connecting today. Thank you so much for giving us your precious time, taking out time from your busy schedule. All the speakers, all the participants, I think we had close to 200 participants today, 200 members in the audience today. I think this was amazing. I thoroughly enjoyed it. And I hope, as promised, you guys also enjoyed it. And I hope as we go back to our homes, or as we shut our screens down today, we go back proud with tons of information loaded and added to our system. And I hope that this helps a lot of researchers here and all the technology enthusiasts here to further pursue and keep looking for challenges and solutions, because after all, technology is never ending, and I think it just keeps updating itself with time. So I think that's about it. And once again, just by the show of hands, please tell me that you guys really enjoyed this and this was amazing. And since we are soon going to be back with another similar fun event very soon in a couple of months, so I hope to see you guys there as well. By raise of hands, quickly, if we can once again have all the audience members here. Amazing. Yeah, everybody, can I see your hands? Wow. Amazing. Now we start like this and we end like this. That's the energy that I expect in the room. This has been amazing, guys. All you people have been wonderful. Now it's time for me to announce our one lucky winner who managed to answer the question correctly. It's your lucky day. And the winner is Abdullah. Are you here? If you're here, please let us know in the chat box. If you can just wave us, it'll be great. I'm just looking out for you. Are you here? All right. And all the other people in the room, can we please congratulate Abdullah? He has answered the question correctly, and of course is the winner of the voucher worth rupees 1,000 in the room. Congratulations, Abdullah. Really happy for you, and I hope this turns out to be like a cherry on the cake for you. And we'll email you the voucher and we'll take your details. My team will contact you. And yeah, that's about it. This was indeed a super insightful day. I love being here, and I hope today, as we turn off our screens, we go back as one big family and then connect back as one big family. People from across the globe came in, talked, shared their valuable insights, and I'm sure all of us enjoyed. So thank you so much, guys, and I hope you further have a great evening ahead. Thank you so much. It's time for us to close the room now. Bye-bye, guys. Thank you. This is me, Devan, signing off for the day.